sir. Thank you.
Okay. Thank you, Abhijit, for the introduction.
Sir, your voice is...
Can you hear me?
Yes.
Hello. Yes. Thank you, Abhijit, for the introduction. And thanks to you and Professor Deepa Venkatesh for organizing this workshop and inviting me to give this talk. And my apologies for not being able to attend in person. But let me get started. So the title of my talk is, as you can see, why is my app not working? Is the application layer to blame, or the network layer to blame, or the optical layer to blame? And for our internet infrastructure, right, the most important thing we crave about is to have high quality user experience. All of us experience what I call the circle of death on a daily basis. That is, you're trying to do something on your screen, there's a circle going round and round and round, and the layperson will say, you know, today the network is slow or the server is down and so on. Okay. But for us, we really want to know what exactly the problem so that we can try to fix it at least temporarily using whatever means, and also devise better artifacts and methods so that these problems occur less frequently or not at all. So the number one problem facing almost all organizations, enterprises, government agencies, etc. today, as well as all of us internet users, is that we have some very important mission critical, business critical applications, and particularly for organizations, government organizations, but we don't have visibility. Who is accessing what? Are they authorized? Are we having data leaks? Are there vulnerabilities in our infrastructure? And these are particularly true for many of the government organizations that I interact with, particularly in the state of California, where I'm located. And we refer to this also as situational awareness. Are we aware of what is going on in our infrastructure? And then more towards the user experience, why is the application slow or getting slower? What are the choke points? And with adoption of cloud and migration of mission critical applications to the cloud, for example, in my own university at University of California, Davis, several years back, when one of the most important applications, the student information system, was migrating from on-prem to the cloud, our CIO and her team were getting... Hello? Yeah, our CIO and her team were getting... Hello, is somebody also speaking on this line? Yeah, please mute. Yeah, so when things are moving to the cloud, certainly there are great advantages of the cloud, right? We have CapEx and OpEx savings, and we don't have to worry about many of these things when everything is working fine. But when things are not working well, we have introduced additional locations where if problems occur, they become harder to track and figure out what's going on. So the number of assets keep on increasing, where performance problems might occur, dependencies might happen. And by dependencies, I mean, if you recall several months back, 7-8 months back maybe, Facebook and Instagram and WhatsApp were down for a large group of users. And after significant amount of checking, it turned out that the application servers were just fine. The network paths to the application servers were also just fine. But there was some dependency problem in the sense that there were some DNS servers that had been hacked, and those users of Facebook, WhatsApp, Instagram that dependent on that DNS server or servers for name resolution were getting the circle of death. And they are thinking WhatsApp is down and Facebook is down and so on, but that was not actually true. So figuring out these dependencies, which are also very dynamic and can change on the fly, is also very, very important. This problem of mission critical applications not working and lack of visibility is exacerbated by equipment getting older, or infrastructure getting older, designs being old. And as I mentioned, with the migration to the cloud, we have introduced more vulnerability points and reduced our visibility of the infrastructure. So what we really need is what I call a holistic visibility. So for any organization, for whatever mission critical applications they have and whatever users they have, they ought to have full visibility of the entire IT infrastructure, not only on-prem, but also in the cloud. Only that part of the internet that is relevant to deliver this mission critical services to the employees of that organization. So the desired solution is need full visibility of all assets used by mission critical applications, and we need performance monitoring and analytics and diagnostics in real time. I'll skip information about myself. The slide deck that I have is more for like a 1 hour presentation, but I know we are down to like 25 minutes. And, so I'll skip slides and perhaps then sections. Okay, so frequent complaints we hear when you walk into any office today. Hey, SharePoint is not working. Office 365 is down. My WebEx, Skype, or Zoom is jittery. The video is frozen. The audio is barely hearable. There's echo. ArcGIS is slow. ArcGIS is a mission critical application, one of our civil engineering type clients. I cannot access the patient's records for a hospital information system. I have no clue who is accessing my financial management system, and if somebody is breaking in. And in this regard, as Abhijit also introduced, I'm founder and president of Analytics. So Analytics has deployed its solution in various places. So for one of our clients who have a financial management system, which is accessed mainly by administrative staff, 8 a.m. to 5 p.m., Monday to Friday, it is very easy to create a user profile. So we can use user behavior analytics to figure out if something foul is going on. And we have seen accesses of this financial management system from rogue domains, which I'm not going to name right now. And usually the admin staff for a typical connection have a certain amount of input and output data amount. And suddenly we see a 500 times exfiltration. That is, somebody is trying to steal stuff from this financial management system. So these things are very important to figure out. Additionally, when I migrated the front end of my application to the cloud, the app stopped working. So traditionally, many of these applications were designed so that front end and back end are on-prem or in close proximity. And when the latency in communication between the front end and back end increases, based on what the application is and how it's designed, it can cause problems. And in general, any business critical application is slow or not working, and the issues are becoming more and more severe as more and more of our important applications are based in the cloud. So desired solution is we want to determine and visualize in real time, drilling down to any particular user as well. If the problem they are facing is in the application layer or the network layer or in the physical layer, optical layer. We want to detect anomalous activities. We want to pinpoint the type of the problem, the origin of the problem, the location of the problem. For example, is it some application transaction that is slow? Do we have a congested network link? Do we have some router interface that is dropping excessive packets? Do we have some aging fiber that is having that is demonstrating increase in bit error rate over time? Do we have a slow or a hacked DNS server, etc.? So in this regard, as you can tell, we need very powerful monitoring and analytics across these multiple layers, across application and network and optical. And most solutions that we have today have a very siloed view in the sense that they look at only application layer data to figure out application slowness and so on. And we want to reduce the time to diagnose such problems and also SLAs from days to hours or from hours to minutes and so on. So from an end user perspective, who is having bad user experience, they don't really care where the problem is. Their issue is, hey, just go fix it. Okay. So in this regard, let me elaborate on the first part that you see here in the outline: applications, network, and optical cross-layer analytics and multiplayer analytics. I'll skip network evolution, and if I have time, I'll touch on some parts of the third point here on advanced network analytics. I see I have only like 10 minutes left. Okay, so why is my app not working? It could be because of some slow app issues at the application layer itself, in the sense that the application servers have to communicate database servers. There may be problems with the application code in the servers where the application is deployed, and so on. And we have tools that can figure some of those things out. But the application could also be slow, or access to the application could be slow because of issues at the lower layers of our protocol stack. For example, at layer 3, we can have congested link. We can have packet loss. At layer 4, we can have TCP retransmissions because of packet loss. We can figure some of these things out through network monitoring. Similarly, at layer 1, we can have signal degradation in optical fibers because of physical layer impairments, aging fiber, getting brittle. And if we can actually do trend analysis through optical performance monitoring, maybe over the past, 6 months, we might find that some fibers are deteriorating, and in terms of the signal to noise ratio and bit error rate and so on. So it is important to be able to detect where such problems are and manage them accordingly. Now, at layer 7, for our application layers, keep in mind that some applications may be delay tolerant, but loss intolerant, whereas some other applications may be delay intolerant, but loss tolerant. For example, for our current Zoom connection, right? We cannot really afford any significant delay, but some loss may be okay. Whereas some other applications, maybe no loss is acceptable. but some delay is okay because they're not necessarily real-time applications. So in this regard, then, the network layer monitoring tools can tell us, like SolarWinds and HP OpenView in the yesteryears, they can tell us on which link we have how much congestion, on which router interface we have what kind of packet loss rate. That is not good enough because we know some applications can tolerate packet loss, right? So it's therefore very important that we look at application-centric issues with respect to networking and user experience and service to users. All right. So here we have this cross-layer analytics diagram. So we need to look at information that we can get from the application layer, from the network layer, and from the physical layer or optical layer. And this is where a lot of important and exciting problems lie. Okay. And this is what the topic of my, the title of my talk is addressing. Why is my app not working? Is it because of these issues of application layer or network layer or the optical? So in this regard, I am showing this, again, the protocol stack. For performance issues, we have these APM tools called application performance monitoring tools like AppDynamics, New Relic, Datadog, Dynatrace, etc. Similarly, from again, user experience or application performance perspective, we have these NPM tools, network performance monitoring, like SolarWinds and NetScout, which prevent the transport and the network layer issues. You can see that each of these categories of tools provide a siloed view of the infrastructure. And in parallel to performance, we have the security tools. And we find that performance and security are very, very intertwined. Just like I mentioned a little while back about Facebook, Instagram, WhatsApp being down, it was a performance issue from a user perspective. But deep down, it was actually a security issue because some DNS servers had been DDoSed, and the application users were depending on those DNS servers for name resolution, and hence were getting the circle of death because they are able to access the application. So security tools also can be categorized as those that are more focused on the application layer, like Palo Alto and firewalls and so on. And then we have also these network detection and response tools like ExtraHop, ProLight, which are focused on the transport and network layer. So you can see all of these tools are each providing a siloed view of the infrastructure. And earlier I mentioned about these dependencies, right? I actually have been mentioning about the dependencies several times. And what is needed is really going forward a holistic view of holistic observability, a 360-degree view of the entire infrastructure that comes into play when somebody is trying to access some mission-critical application. This is not only from enterprise perspective, but also from an end-user perspective that you and I, when we are trying to, do whatever, online game or taking online exam or doing online trading. We don't want somebody to be disadvantaged because they are in a geography where the network infrastructure is slow. So here I'm showing that this solid line that we have drawn is what we do at Analytics. The solid, whatever, rounded box. And we can actually extend it below to the physical and link layer as well. So as long as we have monitoring information available from any of these layers, we can create the appropriate, dependency information and analytics and so on. So let me repeat to some extent, so if we have, let's say, aging fiber that is dropping, that is having higher and higher bit error rate as time progresses, that might manifest into, at the network layer, some router interface is getting blamed for higher and higher packet loss rate. And we might be tempted, and actually this is what people might be doing, is to replace the router interface, thinking that it is the router interface that was a problem, but the new one is not going to solve your problem, and you're going to continue to see a high packet loss rate because it is due to issues at the physical layer. So you see why it is so important to have a very, very integrated or a holistic view of issues at the application layer and the network layer and the optical layer. Okay. And the challenge also is that we have very heterogeneous networks. We have multi-domain, multi-layer, multi-vendor networks, each of which might have their own proprietary management software and so on. Okay. All right, let me skip the network evolution part. Let me just skip these slides. Okay. And I'm going to actually emphasize a little bit more of what I have been saying. So this is your typical infrastructure that I refer to as the application-centric infrastructure. So for a company or an organization, they can have many offices. So there's a main office, there's some branch office, there are users that are connecting to this main office, branch office. Some could be mobile, some could be on-prem, and they're connecting to the internet, and then they're accessing the applications that are hosted in the cloud. While doing so, some of their network functions could be in the cloud, like DNS. Some could be on-prem as well. LDAP, Active Directory, etc. Active Directory might be on-prem. And then maybe some third-party applications for authentication and so on. Okay, so this is what the distributed IT infrastructure looks like. And it is also dynamic in the sense that if I have a mission-critical application of, let's say, Office 365, I'm an organization of 50,000 people. Maybe at 8 a.m., I have only like 1,000 people connecting to the application. But as the day progresses, my workload can increase, tenfold or higher. So in the morning, when there are few users, the host of the service, they might deploy just a couple of virtual machines or a couple of servers in one data center to take care of the workload. But as the workload increases 10 times as the day progresses, a lot more VMs and a lot more servers and perhaps multiple data centers have to be deployed. And so the endpoints are becoming dynamic. So therefore, it is very important for our solutions, to be able to keep track of, where the users from main office, branch office are going. And as the endpoints are getting more and more distributed, more and more dynamic, it is creating a more and more chaotic environment. And from this chaotic environment, we need to create determinism. We need to figure it out. Yes. Hello? Yes. I know I should stop, right? So let me just stop. Hello? Yes. I'm going to stop here, okay? And take any questions. Abhijit, are you there? I can't hear you. I can't hear anybody.
So we would like to now conclude your talk, sir. And
Yes,
sir,
yes.
there's a momentum. So, sir, on behalf of the organizing committee of the AOC workshop and IT Madras, there's also a memento that will be that we would have presented to you in person, but they would like to send it to you, or I might carry it.
Yes, yes. Okay, no problem. Thank you very much. Hello? I've
Sir.
again lost the audio. I don't see any
Thank
video.
you.
I've lost the audio. Okay, I see video.
Yes, sir. Thank you. Thank you very much, sir.
Yeah. Okay.
Thank you, sir. Thank you.
Okay. I should get off. I should stop sharing and.
Yes, yes, sir. You can stop sharing. So thank you.
Okay. Thank you. Thank you very much for the invitation. And it was a pleasure to talk to the audience today. Okay.
Yeah. Thank you, sir. Thank you.
Okay. Okay. Bye-bye.
So now we'll move on to our
back at my so 10 years. In the 60s, DFP laser, high fidelity single wavelength laser, was also from physics. WDM muxing, Newton knew about it. Of course, we improved it. Fiber was developed by Corning. This is the same. Am I audible at the back? Yes, thank you. Fiber was developed by Corning, the same company that makes your, dinnerware. But all of this was around, but the key development that enabled long-distance communication was amplifiers. And this was very recent, like late 80s, early 90s. And I was lucky that, in the lab I was working with there at IBM, we had the first optical amplifiers coming from BT Labs. So this was like fiber and lasers. But still, everything was done by physics, and materials. And with that, optical networking started. We did 10 gig, 40 gig, lots of lambdas. Undersea was deployed in 2000. Okay, EDFAs and Raman amplifiers. It's our own CV Raman. So often mispronounced as Raman. Okay, communications technology had no role to play. In fact, my boss Paul Green at IBM used to say, all your communication technology is not required. All of it is obsolete with optical communication because we can do 10 gigabits and we don't need anything. He says amplitude shift keying is not the right term. It's on-off keying. We just switch the laser on and off, and everything else is physics. So whatever you studied, is wasted. But that changed around 2010 or 12 when you got to 100 gig. So 100 gig needed coherent technology, right? And the first time, everything that you electrical communication engineers studied became relevant. So coherent, we knew how to do coherent in RF all the time, from essentially the beginning of all of the wireless communications, microwave communications. RF was always coherent. And we also knew how to do polarization multiplexing. In fact, by the way, virtually all of your mobile signals are and the polarization multiplex. You have horizontal and vertical polarization, and you can actually multiplex and get spatial multiplexing gain. So these techniques were brought in, and this is actually what enabled you to go from 10 gig to 100 gig. If you ask what's the revolution that got 10 gig to 100 gig, it's really coherent optical transmission and reception. And coherent has really come a long way in the last 10 years. So coherent is about 10 years old. So around 2010 or 12, as you can see on these charts, the density is gone up. Earlier you could get on the front panel 100 gig around 2010. So nowadays you can get about 3200 gig on a front panel. So in telecom, you always have a 19-inch rack on the front panel. So you can get about 3200 gig interfaces. So density has gone up dramatically. Power consumption also has come down from about 90 watts per 100 gig to about 12 watts today. Okay. We need a lot of new modulation schemes to get more and more, to go from 100 to 200 to 400. Actually, today, you can go to about 1.2 terabits, and I'll be talking about new modulation schemes shortly. Now, the challenge in optical communication is capacity and distance at the same time. So usually there's a trade-off. So if you do high capacity, I should have said bit rate and distance, because the capacity you should really measure as a product of bit rate and distance. So it's called capacity on this chart, but really bit rate is a bit. So if you can get, let's say, 100 gigabits, but if you can get it over 2000 kilometers, then we say it's 100 gigabits into 2000 kilometers, whatever the math is, right? But if you get 600 gigabits, usually you cannot get 2000 kilometers. You can only get about 100 kilometers, right? So there's a trade-off, and we usually measure it by the capacity distance product. So here, up until 5 years ago, the chart is a little dated, it's 2020, but you can see. So the first line says that you have 54 terabits is the total capacity. Okay, by the way, this is number of wavelengths. So you have a large number of wavelengths, you're doing 54 terabits total, and you did this over 9,000 kilometers. Okay, so it's an undersea link. This is kind of the largest undersea link we could do about few years ago. So it was 54 terabits over 9,000 kilometers. For this, you use 2 bands, and this band business will become relevant. So it turns out that you can only amplify signals in about 35 nanometers, right? And that's the bandwidth here. And you have C band and L band. So totally you have about 9 terahertz of bandwidth. It's a lot of spectrum. It's on fiber. And with this, you could do about 50 odd terabits over 7, 8, 9, 10,000 kilometers. And you do amplification both based on erbium doped fiber amplifier, which are the oldest, 30-year-old amplifiers, as well as Raman amplifiers. But to do this, in addition to, coherent, you also need error correction. And in some sense, the ability to do long distance communication at very high capacities is also been driven by Moore's law, because we couldn't do the signal processing that we are doing today few years ago, right? 20 years ago, we couldn't do it. So it was not only coherent that came along in 2013, but it was also signal processing capability due to Moore's law that you could do like error correction at 100 gig or error correction at 600 gig or 1.2 terabit today with very complex error correction codes. The most powerful known turbo codes, which get you pretty much close to Shannon capacity. So this is how we got here through a combination of coherent and error correction. You are all too young, but when I was in college, connecting to the network meant going through a modem. Okay, so we used to have modems which had 2400 baud, right? 2.4 kilobits per second. That's the speed you got with modems. And then, getting 9.6 kilobits or 56 kilobits was a big achievement. And you got 56 kilobits modem, which was the highest capacity at the time, through a copper pair from your home to the exchange, was the most complex communication problem. All the best minds were working on it. And we were a few dB, 1 dB of capacity. And David Forney, who was like the leader in the field, professor at MIT, came up with this constellation shaping. So if you're familiar with QAM, you'll see the constellation looks like the bottom one on the right. So that's not the right constellation. You sort of need to have a Gaussian constellation. So this gave us another 1 dB, 1.5 dB gain, which adds to the top of the 10 dB gain we got from error correction. So this is sort of almost the latest advance in optical communication, is to use constellation shaping to squeeze out that last dB of gain. So in my view, all communication theory has come full cycle in 30 years, except everything's happening at terabit rates instead of kilobit rates. Now I'll turn to another topic, which is amplifiers. So clearly we can do terabits per wavelength, but unfortunately, if you do a terabit per wavelength, it occupies more bandwidth. So you're really not getting capacity gains. So the only way to get capacity, and one good way to get capacity gains is if you could use more of the fiber bandwidth. So this is a fiber, loss attenuation versus wavelength. So you can see that fiber, you could use several 100 nanometers of fiber. There is fairly low loss, except for this water peak, but even the water peak is removed. So why can't you use 400 nanometers? You can't, because you cannot amplify. You could only make amplifiers in this 35 nanometer C band. And then they came up with another amplifier for the L band, but together it gave you 35 plus 35, 70 nanometers, but not hundreds of nanometers. So, material scientists, physicists have been working on finding other elements like erbium, and they're all, rare elements, which can amplify in other bands, and they did find them. There's praseodymium, bismuth, thulium. So if you use these elements, you can amplify in the other bands, except none of these technologies have developed to the point where it's commercially available. But this is one way to increase the available bandwidth on the fiber and get much higher capacities. The other way is a semiconductor optical amplifier. So this is sort of the same technology used in lasers. It can amplify over 100 nanometers, which is way better than the 35 nanometers. For a long time, we didn't use semiconductor optical amplifiers. In fact, even now we don't use them. That's because in semiconductor amplifiers, your bit rate has to be very small, because of something to do with carrier lifetimes. So you could not use it at 10 gig or anything. You could use it at a very low bit rate. But one of the innovations, and I've not read up much on this, it sort of came to my attention very recently, is that you can overcome this problem by using a very large number of low bitrate channels. Okay, so instead of doing 40, 80 wavelengths, you do 10,000 wavelengths, okay, of very low bit capacity. And to me, this is interesting because this is what we do in cellular communications, OFDM. So if you do wireless 4G, 5G, we don't know what 6G will do, but it might still do the same thing. So we have a large number of 180 kilohertz is what you do in 4G. So this is OFDM come back. So it's very interesting that coherent, error correction, constellation shaping, and OFDM, everything that you're doing in the 4G, 5G world is coming at very high rates into the optical world. Let me spend a few more minutes on modulation. Okay. So I told you this trade-off between doing 100 gig and 600 gig, right? Or so if you do 100 gig, you can do a long distance. And if you do 600 gig or a terabits, you can only go through the metro. So this is a very complex chart, but I want to tell you that, so this is the signal constellation. So signal constellation, I'll assume you know what QAM and signal constellations are. If not, you have Wiki. Okay. So if you want to go very short distances, you can use 64 QAM or 256 QAM. So this 32 QAM on the top left corner. Okay. But if you want to go very long distances, like 10,000 kilometers, so the left axis is top is 100 kilometers, bottom is 10,000 kilometers. And here is the, sorry, something blocked my, okay. How do I get to this? Yeah. Okay. So if you want to go long distance, you do QPSK, and then in the same bandwidth, you can go 10,000 kilometers. If you want to use the metro, you use something like 32 QAM. So you can get 600 gig, but you go short distance. Now, carriers, service providers are, let's say, like to optimize a lot. Okay. So they tell you, so I don't want to go 1,000 kilometers where you can get me, let's say, this 8 QAM. Neither do I want to go 200 kilometers. I want to go something in between, like 400. And I want something between 16 QAM and 8 QAM. So you could actually do that because you want to get highest capacity out of your link. These links are like Delhi, Bombay, or Chennai to Delhi. And you want to get the last, a few gigabits out of that link. So you can actually do hybrid modulation where you alternate between different modulation schemes. Okay. So you can, for a given link length, you can get the highest bit rate by a combination of these technologies. Okay, so that's really the only point I want to make. And based on that, the spectral efficiency will vary. So if you're short distance, you get 6 bits per symbol. If you're long distance, you get 2 bits per symbol. Okay. Today, what's the state of the art in communication modules? Today, the latest is you can get a 1.2 terabit pluggable module. That's one of the providers is Acacia, which I show on this right. And this can do 1.2 terabits if you're doing short distance, 50 kilometers, or it can do undersea, 400 gig if you're doing long undersea communication. So all of this is packed into this module, and this is kind of the latest advance. So we get today, and this builds in amplification, tunable optical filters, everything into this. And you can get it in C band or L band. So this is the state of the art in coherent modules. After modulation, let me spend a few minutes on fiber technology. So fiber, for a long time, you transmitted one signal on one fiber, okay, which is fair. But when you wanted, let's say, you put many cores of fiber, many fibers into a big bundle. So the cable that you see on the streets usually has 192 fibers or more. You can get 864. That's kind of the record. And all of these fibers are based on silicon dioxide. Okay? So virtually no progress has been made in making fibers with other materials. Why would you want to make? Because silicon dioxide has loss, which is about 0.2 dB per kilometer in the lowest loss, which is a very low loss. So which enables you to go something like 80, 100 kilometers without amplifying. If you think about it, it's quite stunning, right? You turn a laser on and off, 80 kilometers later, you can still receive the signal and nothing happened in between. It was just glass, total internal reflection through glass. But there are other materials which can have even lower loss, like maybe 0.01 dB per kilometer. But none of that, and that's been around for 30 years, but we have not made progress using any of those materials. So if you're a material scientist, you can look at making non-silica fiber. You'll be alone, not too many people are working on it, but that is one thing. Okay. So for some time, and I think this is still an interesting question, we hit a wall. So on one single mode fiber, we could not get more than about 100 terabits, in the RBM window, in the 35 nanometer RBM window, we kind of saturated at about 100 terabits. Normally in communications, if you increase the power, you get more signal to noise ratio, you can do better. And then, you're only limited by Shannon's theory. but that theory allows you to get more power and therefore get more capacity. Here, we could not increase power. It's not that we can't make high powered lasers, we can, but we hit it, come into non-linearities with the fiber. And so we kind of hit a wall. We couldn't get more than 100 terabits on a single core of fiber, about 35 nanometers. So for many people believe, and they call this the nonlinear Shannon limit, but if you are a communication theorist, and that's my challenge, I don't think this is proven that you can't get more than 100 terabits. But anyway, if you assume that for now, how do you go further? Okay, to go further, of course, you can put multiple fibers, but the disadvantage of putting multiple fibers is that's nothing. I mean, that's like, it's really completely independent systems for everything, right? For what you want to ask is, for a single fiber, which is 125 microns in diameter, can I do something clever? Can I put multiple cores of fiber, right? So that's what people start to do, and that's called space division multiplexing. So you put multiple fiber cores into the same standard 125 micron fiber. So fiber, I'm assuming, is 125 microns in the cladding, and there's a core, which is like a few, so can you fix that? Yeah, okay. There's a core, which is about, 8 microns or so. So the next technique, which is relatively recent, 5 years old, is to put more cores into a single, into the same cladding of 125 microns. And then there are a couple of ways. You can either keep these cores far apart, in which case there's not much coupling, or you can keep them close together, like in this right picture, where the modes couple, and then you do signal processing to recover, right? So it's sometimes funny that keeping them separate is not the best way. Getting them to couple and then, do some fancy processing, gives you more capacity. So I won't go through this, but I'll tell you what we can get with this. Oops. Now, whatever you did, okay, fine. So I call this the Olympics of optical transmission. So I told you we hit 100 terabits as a sort of a plateau. So now the goal is, can we reach 1 petabit, okay, for long distance communication? So here on this, I have, just look at the top graph. The total data rate is in terabits per second. So 1 petabit would be the top line, 10 to the 3 terabits per second. You kind of reached it, but for like a couple of 100 kilometers. And this is also cheating. So if you look at the open ones, they use fiber, which is more than 125 microns. If you just take the solid symbols, so you limit 125 micron fiber, and you want to get more than 1,000 kilometers, we're still not there. We could not reach a petabit. So we are kind of in the 100, 200 terabit range still, even with multiple ports of, even with space division multiplexing. So reaching 1 petabit at say over 1,000 kilometers is still a goal that is worth pursuing. With short distance, we crossed this 1 petabit. So with 19 cores, you could reach 1.7 petabits, but for a distance of 60 kilometers. So for short distance, you're over 1 petabit. But for long distance, you are well short of this 1 petabit limit. So if you're looking for challenges, get 1 petabit from Chennai to Delhi. Okay. So let me summarize. I know I'm a little bit early, but I want to touch on one more topic, and there's no harm giving the organizers another few minutes. So to summarize, in terms of optical fiber, we have progressed in putting multiple cores or silica fiber and getting higher capacity. There's also another interesting thing. Fiber is made of glass, and light travels slower in glass. It's only 200,000 kilometers per second, as opposed to 300,000 kilometers per second. And this is too slow for some people. Who you might ask? It is too slow for stockbrokers, okay? Because they want to trade faster than the next guy. And if you can trade a very small fraction of a second faster than your neighboring broker, you get to make billions of dollars, okay? And this is serious, it's not a joke. In 1990s, there was a microwave link from New York to Chicago. These are the two major trading centers. Okay, Chicago is where all the options and futures get traded, and New York is where the stocks get traded. And there's a microwave link with repetition every 20 kilometers, only to get 300 kilometers per hour speed, 300,000 kilometers per second speed over free space as opposed to fiber. Okay. So now people are looking at hollow core fibers so that you get this extra speed of light. So for some industries, light is not fast enough. Okay. New material I already spoke about. So there is loss. If you could reduce this loss, get rid of all the amplification, you could do 1,000 kilometers without amplifiers, it would be a dream, but this remains a barrier. Optical amplifiers, EDFA 35 nanometers is the biggest limit that's been holding back the industry for 30 years. We can't get an amplifier to work larger than this. If you put multiple amplifiers for different bands, that's really not solving the problem because you might as well put multiple fibers. Okay. So what you really want is one amplifier, even if you got all the praseodymium and bismuth and thulium to work, it would still mean 4 or 5 different amplifiers to use the entire bandwidth. So what you want is one amplifier that can amplify the entire bandwidth because long distance communication was really revolutionized by amplification. All other elements of optical communication were there 20 years before amplifiers, lasers, fiber, multiplexing, but it's the amplifier which made it long distance, right? And if you want to use all of the bandwidth, you need amplifier which can amplify the entire bandwidth. Semiconductor optical amplifiers are very promising. They could amplify 100 nanometers. So we may need to relook at them, but this is just started in the last 2-3 years. So really not much progress in optical amplifiers in 30 years since EDFA. Capacity improvements. You can improve the capacity on a single wavelength. You know, we've gone from 100 to 600 to 1.2. I think people are now looking at 3.2 terabits per second single wavelength. You also need to provide higher capacity in the access, okay, because access is limited to PON, 10 gig. So maybe you need coherent PON optics. But single core fiber is the most efficient because I already mentioned for optical amplification. So the total capacity over single core of fiber has not improved beyond 100 terabits in maybe 20 years. Okay, so how to improve this with, maybe communications. So if you're a communication engineer, you tried everything now, the highest error correction, coherent, trellis shaping, but you've not solved the nonlinear problem, which is hard for communication people because you don't know how to deal with increasing power and the fiber and nonlinearities. But what is the ultimate limit of sending on one fiber? Is it 100 terabits or more? Is still an open question. I know I have a few more minutes. I have one more slide. Okay, 1 minute. So here we have an advanced optical communication workshop. There's a large test bed, being set up, led by IIT Madras. 5G came, but didn't make an impact other than draining the power on your phones. 6G is coming up. So maybe you got 5G only because you're in 3.5 gigahertz, you get more spectrum. Otherwise, in all the other bands, 5G gives the same performance as 4G. But people are buying new phones, new networks are being set up, 6G will come up. One thing to note is because of all the higher and higher bands being used for 5G and 6G, the network is more and more optical. Even in 4G, virtually all of the backhaul is optical. In 5G, 100% of the backhaul will be optical. And whenever 6G comes or 5G penetrates, the wireless will be limited only to the last 100 meters or less. This is already true in millimeter wave. It's almost like Wi-Fi. So really advanced networks being built up and users using 5G and 6G will depend a lot on fiber optic communication. So the advanced optical communication testbed is just right in time. So you need to fiberize macro, micro, every building, every dwelling, every rural home. So what I like to say is fiber should go wherever electricity goes. So if a rural home has electricity, it should have fiber. So this will drive the 5G and 6G will drive actually the market for fiber optic communication as well. How big is the market? Over the next 5 years, added up over 5 years, it's over $90 billion worldwide. India is only about 3 billion, but maybe it's conservative. If we fiberize a lot, we could be a much bigger fraction of the 90 billion. The component market, and I know in this testbed, a lot of people are developing components, is expected to be 20 billion over the next 5 years. Our share is probably 0. It's not measured today, but I think it's a great opportunity for Indian companies to make advantage of all the technologies is developed in this test bed and build up both a system, ecosystem to develop, to get a share of this 90 billion market. Maybe we can get 10, 20%, and the share of the component market, like auto components are big industry in India, even though we are not a big portion of the world's car market, and get a share of this $20 billion component market. I'll end here. Thank you.
Thank you. Thank you very much, sir, for such an enlightening talk of covering the entire spectrum of technologies and challenges in the area of optical networks. So, sir, now on behalf of the organizing committee and IIT Madras, sir, we would like to present you with a memento.
Thank you, Abhijit. I love this banyan leaf, which is plated. It's a very nice thing. Thank you.
Thank you, sir. May I now request Sri Deendayal Toshniwal, Deputy Director General of DOT, to join us on stage for honoring our session chair. I request Dr. Deepa Venkatesh of IIT Madras to just honor on behalf of. We told actually. Thank you, ma'am. Let's hear from our collaborators who couldn't attend in person.
Good afternoon. My name is Darko Zipar, and I'm
I'm very hopeful that this will prove very positive experience for everyone, and new technology will come out of it. That I'm pretty sure about that as such. So I think the collaboration between the industry and the university is really very necessary. But anyway, I will tell more as you ask me further questions on that. So go ahead.
Yeah, my name's Andrew Lord. I lead British Telecom's optical and quantum research, looking at all aspects of optical fiber transmission, and including quantum technologies running over optical fiber. I've been involved with the group here for probably 10 years. It started with a PhD by Bikit Mitra, who came into my lab and into my team several times, and then it's carried on from there and built into a bigger program of work. Most recently, a PhD by Rana, who's working very closely with us, focused on mainly optical network optimization, optical network modeling, maximizing system performance over optical fibers. And yeah, we're looking forward to at the moment a visit from Rana to continue the collaboration with both with BT and with Aston University. Also, we have a very high-profile conference paper at ECOC in Glasgow in October, which Rana is coming to give. I think this is a really strong initiative in a really important area. When you think about optical fiber, some people assume that this is something that has been effectively finished, but actually it's the opposite. Optical fiber communications is just starting, and there's no replacement for it. So this has to work, and it will be in place for the next 100 or 200 years. And so to start this initiative now is a really good idea. But initiatives have to collaborate with multiple partners around the country and around the globe to build expertise and to share expertise and capabilities. Otherwise, it's very, very difficult to get momentum. And so I think this is a really, really strong idea, and you know, wholeheartedly support it.
My name is Massimo Tornatore, and on behalf of the Telecom Engineering Group at Politecnico di Milano, I really would like to convey my best wishes to all the organizers of this workshop on advances of optical communication, led by IIT Madras and funded by the Department of Telecommunication of the Government of India. I was invited to record this message by Professor Abhijit Mitra. I had been collaborating with Professor Mitra since 2018. When we were both visiting scholars at the University of California, Davis. It is a great pleasure to send this message today. Best of luck in the organization of the workshop.
Who needs to be on?
Oh, yeah.
Good morning, ladies and gentlemen. Honorable Minister of State for Communication, Shri Devosin Chauhanji, our Director, Professor Kamakuti, and other distinguished guests and honorable delegates. On behalf of IIT Madras, I extend a warm welcome to each one of you. We are honored and delighted to have the presence of esteemed Minister who has graciously spared his valuable time to be part of this special event on Atmanirbharta in telecom sector. I request Honorable Minister Shri Devosing Chauhanji, our Director Professor Kamakuti ji, Member Technology Madam Gunjan Dave ji, CEO C. Shri Rajkumar Upadhyay ji, and AOC Testbed Project Lead Professor Deepa Venkatesh ji to kindly come on the dais. I first welcome Professor Deepa Venkatesh, Professor, Department of Electrical Engineering at IIT Madras, carrying out research in areas of optical communication and related technologies since 2009. She is the project lead for the Advanced Optical Communication Testbed funded by the Department of Telecommunication, Government of India. I kindly invite her to grace the stage and deliver the welcome address and introduce us to the testbed. Professor Deepa.
Respected Minister of State for Communication, Shri Devosing Chauhan, Professor Kamakoti, Director IIT Madras, Member Technology, Madam Gunjan Dave, Shri Rajkumar Upadhyay, CEO C. and other dignitaries from C. CDAC, ISRO, DAE, DRDO labs, representatives from the industry, our HOD, Head of the Electrical Engineering Department, deans, faculty colleagues from IIT Madras, IIT Bombay, IIT Delhi, IIIT Delhi, and other institutes, PhD scholars, postdocs, R&D engineers who are visiting us, and my dear students. Good morning, and a very warm welcome to the session on Atmanirbharta in the telecom sector. It is indeed an honor, sir, to have the Honorable Minister himself to grace this workshop. Thank you, sir, for taking your time out of your extremely busy schedule. I take this opportunity to thank Member Technology, Gunjan Dave Madam, who has been with us since the beginning of the workshop and guiding us on how to go about the workshop and the consortium itself. Thank you, Madam. Also thank, welcome Sri Rajkumar Upadhyay, who is a CEO C. who is guiding us as the implementing agency for this consortium project. Welcome, sir. Professor Kamakoti is from one on our own. He doesn't need a welcome. This workshop is conducted under the aegis of the Department of Telecom. And let's move on to tell you about this session and what this testbed is about. Broadband internet and instantaneous connectivity to the rest of the world has now become a basic, or we can even say an essential service, almost similar to power and water. Most of our homes and offices have an additional utility line that is coming in addition to the power line and the water line. which is the optical fiber. 4G and 5G are the technologies that provide mobile connectivity, and these wireless technologies ride on the assumption that fiber connectivity is available to interconnect all the mobile networks in the world, thus making the availability of optical fiber connections ubiquitous. The landscape of optical fiber network is actually much broader than the mobile networks. Antennas to the base stations, connectivity happens through the front hall. The hyperscale data centers, both within the connectivity between the data centers and within the data centers, they get connected through optical fibers. Fiber to the home has become an essential service. All these access services get tied to the rest of the world through the metro and the core networks, and they eventually end up being the global fiber network. Radar systems and satellite systems have also started independently using and relying very largely on free space optical communication and optical fiber communication link, and photonic processing has become an emerging technology today. We are witnessing a large capacity scaling in these access networks, and unlike the wireless systems, there is no clear demarcation between the generations. The capacity scaling techniques used in the core networks maybe 10 years ago are moving to the metro and to the access networks. The demand for capacity is only progressively increasing. In wireless, we talk about 3G, 4G, 5G, and so on, where G stands for the generation. Whereas in the world of optical communication, we talk about 10G, 40G, 100G, 400G, 800G, where G stands for gigabits per second. So I will not explain the detail, but just to give you an idea of how the technology has been progressing over the years. In a single optical interface, we are at a point where we are at close to, in a single optical interface, we are close to about 400G. Recently, there was talk about 600 gig and gigabits per second and 800 gigabits per second from the international players. But optics enables us to multiplex further. So it enables us to scale in terms of wavelengths. So you have wavelength division multiplexing, space division multiplexing, other technologies where the optical channel can be used, and optical channel is much more well-behaved than a wireless channel, much more predictable than a wireless channel. And that is why we are able to increase the capacity. Optical line terminals, optical fiber, optical networking units are some of the networking equipment today made in India and even exported. However, with this rapidly changing bandwidth requirements and the emerging requirements for the 6G, there is a need for a rejuvenated R&D effort in the optical communication domain. Under the TTDF scheme established through the USOF, the Department of Telecom has funded the formation of Advanced Optical Testbed Consortium, consisting of academia and industry partners towards indigenous development of devices, subsystems, and networks towards actually making a testbed which will be complying to standards and ready to market. And in this testbed, we would be covering different domains of optical network, and we would be having a goal of creating an ecosystem for indigenous technology development. There are 3 academic institutes, IIT Delhi, IIT Delhi, IIT Madras, an R&D center, ERNET, and industry partners who are listed here: Signalchip, Signaltron, SFO Technologies, Sterlite Technologies, SASMOS, HET, Confluence. All of them are being funded for developing different aspects of this testbed. We also are glad that other prominent industry partners, Now Wireless and Tejas Networks, are a part of this consortium. We are taking a 2-pronged approach in this testbed. We would have a state-of-the-art testbed with commercial off-the-shelf items with devices and subsystems. And we will also parallelly have indigenous technology development in partnership with the industry and these would get tested against the commercial state-of-the-art test bed. It will have elements catering to current and futuristic requirements. It will provide a platform for validation of all the products developed, compatibility and interoperability. It will rejuvenate the R&D towards translational technology for futuristic implementations, leading us towards patenting and standardization. Some of the key elements are multi-core fiber field deployment. Multi-core is a new type of fiber where in a single cladding, you could have multiple cores, 4 cores. And this work package is done between Sterlite Technologies and IIT Madras, where a 4-core fiber in a single cladding would be deployed in the IIT Madras campus. There will be both underground and aerial deployment in the cabled version. And this, if we are able to make it in time, this would be the first in the world. We are also having a significant activity, a large composite part of the testbed. We are reserving our resources for the build of transceivers. Now, this transceiver build is combined between Signaltron and Signal Chip and IIT Madras. Each one of us is contributing to different elements of the transceiver. The chip will be made, designed here. The retimer chip will be designed at 28 gigabaud. And eventually we hope to get a target of QSFP modules shown there. These are commercial modules. And we will hope to get our own QSFP modules at running at 100 gig, stretch goal at 200 gigabit Ethernet. In terms of R&D effort on capacity scaling, we have a mighty goal of ultimately reaching 12.2 terabits per second in one channel with 96 gigabaud signaling rate with polarization multiplexing 16 QAM, 4 cores and 4 wavelengths. We have a significant effort along with our 5G testbed for making the remote radio unit much lighter in the sense in weight as well as in power with analog transmission in the front hall. Initial efforts have started, which have given very promising results. And in a year's time, we'll be able to integrate this. And this becomes very relevant for the 6G efforts going forward. The components and subsystems required for the testbed, for the futuristic testbed, which are multi-core couplers, will get locally fabricated. RF transceivers, which would be an integral part for the radio over fiber systems for 5G and 6G, that will also get developed. Components like optical frequency comb, reconfigurable filters, which are required for slightly futuristic networks, will get done during this project. There will be a significant effort on networked Li-Fi that's done by IIT Delhi. RF transceivers is done by SASMOS, and the passive components are done by SFO Technologies. In the networking domain, we will have IIIT Delhi looking at futuristic networks when you have cooperative operation between C-band and L-band. ERNET is adding a node to the existing quantum network and looking at network aspects, controller aspects for the quantum link. And Confluence is looking at making devices like parameter. These are futuristic devices with very low noise figure amplifiers and also for building our own indigenous homodyne detectors. So that was the snapshot of what are the activities. We really perceive this testbed to be the go-to place for all the service providers, equipment manufacturers, component manufacturers, network planners, startups can keep adding to the list. This must be the go-to place in India. We will find resources to solve the problems that not are just Indian problems, but also eventually get into a mode of Atmanirbharta. In addition, also looking at export of all our products and solutions that are developed. So to create an ecosystem for indigenous technology development, it will address both high volume and as well as technologically niche products. We will have national facilities, not just in IIT Madras. IIT Delhi is also establishing a parallel testbed, which is open to academia industry for R&D and performance tests to provide platforms for IPR generation, contribution to standards, provide platform to solve the India-specific networking problems. So thank you. And we really hope to have more interaction and collaborations, not just during the workshop, going forward. This is only a brief introduction. I now request Honorable Minister Devusingh Ji to kindly release the book of abstracts for this workshop. Can I now request our director, Professor Kamakoti, to address the gathering?
Let's have this.
Friends, a very, very hearty welcome to IIT Madras campus, IIT Madras Research Park. This day is a very, very satisfying day for particularly me, because I just see this as nothing but preparation for 6G. The entire backhaul that we envisage in 6G, I think we are now starting to prepare for this. Hearty congratulations. And sir, Honorable Minister, your presence here only for this workshop today, I think adds a lot more of encouragement to us, and very big welcome to you. And we will surely, on behalf of all the stakeholders, I assure you that we will make this a great success, sir. Friends, I just want to start. I just took permission for talking for 5 minutes from Deepa. I just want to start where COVID essentially has accelerated the digital adoption. And probably first time in the recent history, we see that our requirement is start of making a demand on the infrastructure. Today, we see a lot of adoption, even about live, sending live videos or video streams from rural parts to, different parts of the world, just to tell what is happening in a small function happening in a rural village. I think the demand for bandwidth is increasing, and that is where, and there is more of digital adoption, even in the area of education, where we are seeing a lot of online training reaching to the villages. Just from this education sector, we are seeing this demand, and I'm sure in many more sectors, including health, agriculture, etc., we will be seeing an overall increase in the in different ways by which we can use communication for doing certain socio-economic activities. So first and foremost, we have our friend Upadhyay ji here. Let us start by congratulating BSNL for the 4G indigenous development. We have several stakeholders here. I also see Kumar, yes, and C. Congratulations, sir, and we wish you all the best. And we really want to see your core upgrading to the 5G at the earliest possible time, so that India has, no, the world has the cheapest but the most effective 5G. We are now in the path of doing a great price discovery, wherein we were having all black boxes everywhere, but now we know what is the cost of actual production. I think this will give us a very deep insight into what it means to scale in terms of economy of communication. And for that, this indigenous Atmanirbhar development of 4G is going to be, and is indeed, a turning point in the history of telecommunication of our beloved country. So let me again congratulate you, sir, and we wish all the best. And I want to see the 4G in Chennai. So, right. So the next important thing, now that we are taking this consortium, our 5G effort, again, a big thanks to Department of Telecommunication and the Government of India for having batted for our standard in the 3GPP, and we have harmonized it, and we have brought in our technology into the ITU standards. And this was again a very big Mahabharata battle that we had, for several months together to take this to the 3GPP and get it into the ITU. But then we had actually proved that a bunch of institutions, along with CVIT Summit, we were able to push a standard and able to convince an international standards union to basically adhere to this standard. Now, this has given us the confidence that we can go and make much, much bigger things in the coming times, specifically in the area of 6G. Now that this optical testbed has happened, now we see that this is a complete stack. There are a lot of things that are available today. There are a lot of people who are now willing to participate. We see a large industry participation. But friends, we must commit to deadlines. This is my request. And we are going to be the project management unit. Yes. So as a PMU, that I'm heading an institution which is a PMU, it is my humble request to all that we must commit to deadlines. We must give the heart and soul and see this project is successful. There's nothing called failure here. Second thing is that there are certain gaps where we are now going to take the commercially off-the-shelf components, and all these gaps must be filled with some research and development projects in our respective academic institutions. And all these technologies should go either to an Indian startup or Indian company, or we must form our own startup companies which will handhold this. So this must lead either to transfer of technology to Indian companies, or it must become a startup within our academic institution. And from day one, this has to be nurtured and this need to be put in place. Otherwise, again, we will again go with this maximum indigenization should become more and more maximum, and that is very, very important. And I request all the stakeholders to please keep this in mind and let us have all the technologies into this place. And I also believe that when we are going for the 6G backhaul, there are a lot of things that we need to patent. All our competing countries, if I may use that word, have hundreds of such patents already in place. I think we must protect our ideas. So everything that is basically you feel that an idea is patentable, let us now make an earnest attempt to patent it. We have robust mechanisms in the educational institutions which can enable this patenting. So we have an AI-based complete automated workflow in IIT Madras, which can help you, file a patent within a week. So this is what we have achieved. Last year, we had more than 240 patents that almost every working day we had a patent. And this time I am now, humbly requesting my Dean ICSR to have 365 patents this year, 2023, and 366 next year, because being a leap year, we need one more. So this is the standard that we want to push. And I really want these patents to be filed, these ideas to be protected. If we aspire to become a world leader in 6G, the quickest adopter of 6G, which we need to plan from now, it is very, very important that we take acute care, and deadlines are very important. And the attention to the quality and accuracy of what we do is also very important. With this humble request, I wish that we will have one more launch here in the earliest point of time, where we have a world-class testbed with many other world partners across the globe now coming and attending this and using our testbed, and a 6G launch from IIT Madras. With these very noble thoughts and big ambitions, I again invite all the consortium members and all the participants for this workshop. And I wish you all the very best, and let us make our country proud with lot more of Atmanirbhar technology in one of the most emerging field, the communication field. Thank you very much.
Thank you, Professor Kamakuti. We are privileged to have Srimati Gunjan Dave, Member Technology and Digital Communications Commission, Ministry of Telecom, to address us. To introduce Madam, she completed her graduation and post-graduation from IIT Roorkee. In 1987, she joined the Indian Telecom Services and dedicated more than 3 decades of her career to MTNL Mumbai, serving in various capacities. From March 2022 to April 2023, Srimati Dave served as Senior Deputy Director General for Gujarat Licensed Services Area overseeing Gujarat and Union territories of Dadra and Nagar Haveli. During her tenure, she led the successful launch of 5G services in Gujarat and implemented the CBUD app along with other government initiatives. Continuing her upward trajectory, Srimati Dave assumed the role of Member Technology at Digital Communications Commission, Ministry of Telecom, starting from June 1st, 2023. In this prestigious position, she is responsible for initiating policy decisions, driving technological advancements, and strategic decision-making in telecommunication sector. Let's extend a warm welcome to Srimati Gunjan Dave ji to share her valuable insights.
Honorable Minister of State of for Communications, Shri Devu Singh Chauhan ji, Director IIT, Professor Kamakoti ji, and other esteemed guests on the dais, and all the dear participants, a very good morning. Namaste to all of you. Since yesterday, we have been listening a lot of technical talks on the advancements in optical communications and the need for it. So I feel very honored to be a part of this workshop, and also happy that I am one of the instrumental officers in DOT who is sponsoring this optical communication, advanced optical communication test bed in IIT Mumbai, IIT Chennai. Now this, since yesterday we have been hearing that optical is the future, which is very rightly so, because all the newer technologies, 4G, 5G, 6G, etc., all are now based on optical, more and more optical. And if we see from the various use cases like IoT, so many devices are getting interconnected and generating data in real time, and for that we need lot of server capacity also. So for the backbone, optical communication becomes all the very more important to provide the bandwidth and the scalability. Also, if we see there is a growth of cloud computing and data center. So the basic backhaul connectivity for all this is optical communication. So it becomes very important that we go in for more and more advancements in the optical communication technologies. And moreover, as we go towards the terahertz, so we know that optical is the only way to go forward. So advancements in optical communication becomes very important. Now, if we see the government's vision of Atmanirbhar Bharat, then it calls for indigenous innovation, self-sufficiency, and global competitiveness. And in this context, the significance of this advancing optical communication becomes very important. And by nurturing homegrown research and innovation, manufacturing, that is the only way that India can not only meet its demands and also become an exporter of the technology. So if we have to become global leader, then we do need such test bed type of facilities and more collaborative efforts. And another very important thing is security. So when we are going for the design of new equipments, so it's very important that we have this concept of secure by design. So, and that is one of the ways to have secure systems. And rather than working later on to prevent the security and cyber breaches and implement other security measures, it is very important that we start from the beginning itself. Also, being self-reliant in the new sectors, it not only fosters economic growth, new jobs, and also reduces our dependence on foreign technologies. Now, to achieve Atmanirbhar Bharat, it is very important. One very important thing is to have the intellectual property and patents in the field of technology. So now, when we are talking about optical communications, so it patents not only protect innovations but also foster a culture of continuous research and development. And it is very important that we also know how to protect our patents, and the knowledge of IPR Act is very important. So, in fact, as sir very rightly told, that you have very strong patent filing system in IIT Madras. So I feel it becomes very important that it is that the students are also and researchers are also aware of the IPR Act. So we can introduce some sort of small training in that part also, that people are aware about about their rights. DOT is also working on a framework to promote and support IPR filings, and we are working very closely with DPIIT in this direction. Now, another important thing is which government has been promoting is to reduce the digital divide, and especially in rural areas. And as we know, optical communication has the power to reach the connectivity in remote regions, enabling very high speeds, promote all the socio-economic activities and e-governance services, digital education, healthcare, and other things. So by empowering rural India with all these connectivity tools, we can actually unlock the true potential of India and drive inclusive growth and uplift the communities. Now, standardization is another important aspect, and it was discussed in very detail in yesterday's workshop by various esteemed speakers. And as India aims to be a global leader in optical communications, it is vital that we actively participate in the standard forming bodies discussions and contribute to the development of standards. And now it's very important to translate research into products and solutions. So active collaboration with the private sector partners is essential, and testbed is one of the such efforts where private partners are also collaborating with the academia to participate in the advancement of the technology. So, and collaboration with various research bodies and different institutes, test beds. This is very important because it fosters knowledge enhancements, knowledge exchange, resource sharing, and creating a supportive ecosystem for research and development. And as it has been already pointed out earlier also, that in this test bed formation also, collaboration with the industry, private industry, and different IITs is also going to be there. Finally, we need strong connects with other projects which are being supported by TTDF. So that is the way to unlock fully the potential of various projects of vital importance which DOT has been promoting. So in the end, I just conclude that advanced optical communications hold immense potential to revolutionize the way we connect, communicate, and advance as a society. This workshop and the testbed will definitely set the right tone for research development in this field and lead India towards a developed India 2047. Thank you.
Thank you, Srimati Gunjan Daveji. I request Dean ICSR Professor Manu Sanathanam to please come on the stage and give a token of love from IIT Madras to Srimati Gunjan Daveji. As we continue, it gives me great pleasure to announce the presence of our distinguished guest, Shri Devasin Chauhan Ji, the Honorable Minister of State for Communication, Government of India. Shri Devasin Chauhan is originally from Navagam village in the state of Gujarat. He obtained a diploma in electrical engineering from the Government Polytechnic College in Porbandar, Gujarat. He worked as an engineer in Akashvani Kendra, an organization under the Government of India, for 13 years. Subsequently, he left the government services in 2002 to join the public life as a politician to serve the people of India. Shri Devasin Chauhan Ji won Vidhan Sabha elections from Mathur constituency of Kheda district of Gujarat in 2007, from where he was re-elected as member of Legislative Assembly of Mathur in 2012. He was further elected as a member of parliament in 2014 and then in 2019 from Kheda constituency. He served as a member of Parliamentary Committee on Water Resources and Defense. He has also served as a member of Consultative Committee of the Ministry of Communication and Information Technology and Ministry of Food Processing Industries. He has undergone a short course at King's College London, which was organized by the British High Commission. He assumed the charge of Union Minister of State for Communication on 7th July 2021 in the Council of Ministers headed by the Honorable Prime Minister Shri Narendra Modi. I kindly request Shri Devasin Chauhan Ji to grace the stage and share his vision on Atmanirbharta in telecom.
एडवांसेस इन ऑप्टिकल कम्युनिकेशंस के वर्कशॉप में आज के स्पेशल सेशन आत्मनिर्भरता इन टेलीकॉम सेक्टर के विषय में मंचासीन प्रोफेसर डॉक्टर कोमाकोटी, डीओटी मेंबर श्रीमती गुंजन दवे, श्री आर.के. उपाध्याय सीईओ सी.डॉट, प्रोफेसर श्रीमती दीपाजी वेंकटेश जी, मेरे सन्मुख उपस्थित श्री आर मित्तर जी, डीओटी के ऑफिसर्स, आईआईटी के ऑफिसर्स, प्रोफेसर्स एंड डियर स्टूडेंट्स। आत्मनिर्भरता मतलब सेल्फ रिलायंट। अगर कोई व्यक्ति नहीं होता है, अगर कोई देश नहीं होता है, तो इस व्यक्ति का एक्सप्लोरेशन भी होता है, अपमान भी होता है और देश का भी वैसा ही स्थिति होता है। जब कोई देश 75 साल की यात्रा के बाद भी अपने आप को सेल्फ रिलायंट नहीं कर पाता है, तब इस देश की प्रोग्रेस को बहुत बड़ा असर होता है। फॉर्चुनेटली अनफॉर्चुनेटली हमारे देश में कोविड-19 का एक पेंडेमिक आया और इस पेंडेमिक ने पूरे विश्व को हर तरीके से बदल दिया। और इस पेंडेमिक के बाद ऑनरेबल प्राइम मिनिस्टर श्री नरेंद्र भाई मोदी जी की गवर्नमेंट ने भी महसूस किया कि सेल्फ रिलायंट कितना महत्व का होता है। आज आदरणीय मोदी जी के नेतृत्व में एनडीए की सरकार ने 9 साल कंप्लीट किया। उन 9 साल के पीरियड में सेवा, सुशासन, गुड गवर्नेंस, सर्विसेज और गरीब कल्याण का बहुत बड़ा काम हुआ है। लेकिन इस तीनों जगह, चाहे ई सर्विस देना हो, टेक्नोलॉजी के माध्यम से गुड गवर्नेंस करना हो या पॉवर्टी एलिमिनेशन का काम करना, इसका सबसे बड़ा आधार इस देश में कोई रहा हो तो वो हमारा टेलीकॉम सेक्टर रहा है। आदरणीय मोदी जी ने हमें 2020 में आत्मनिर्भरता के लिए टेलीकॉम सेक्टर को मार्गदर्शन किया। उन्होंने बताया कि भारत की जो टेक्नोलॉजी है वो आज भी इंपोर्ट हो रही है, मैन्युफैक्चरर विदेश से, हमें उन पर आधारित रहना पड़ता है। तो क्यों ना हम अपने आप को सेल्फ रिलायंट करें। और उनके मार्गदर्शन में, उनके आह्वान पर टेलीकॉम सेक्टर में पिछले 3 साल में इतना बड़ा काम किया है। और ये काम करने के लिए टेलीकॉम सेक्टर ने जिस तरीके से एकेडमिया, इंडस्ट्री, सबको एक तरीके से इकोसिस्टम बनाया, यहाँ तक कि फंड की तो कोई लिमिट ही नहीं रखी। हमने पीएलआई लेकर आए। पीएलआई मैं पर्सनली देखता हूं, मुझे मालूम है कि 30 कंपनी को हमने शॉर्टलिस्ट किया था। और 30 कंपनी को शॉर्टलिस्ट करने के बाद 1 साल के बाद पीएलआई के जो कंपनीज थी उन्होंने बोला कि हमें डिजाइन लेड में आप पीएलआई करिए, R&D वर्क के लिए पीएलआई करिए। तो हमने डिजाइन लेड पीएलआई भी लाए। हम पीएलआई के बाद DCIS में भी करीब 42 कंपनीज को रिसर्च और इनोवेशन के लिए हेल्प कर रहे हैं। और पीएलआई, DCIS के बाद हमने TTDF, टेक्नोलॉजी डेवलपमेंट फंड, इसके लिए स्पेशली 500 करोड़ रुपए का एक अलग आवंटन किया, जो केवल टेक्नोलॉजी में डेवलपमेंट का काम करेंगे, उनको हम हेल्प कर रहे हैं। और मुझे बड़ा गर्व होता है ये बताते हुए कि C.DOT की टेक्नोलॉजी, इंडिजिनस टेक्नोलॉजी में हमने 500 करोड़ दिए थे, लेकिन आज बड़ी गर्व के साथ कहता हूं कि 4G इंडिजिनस अब इस देश में हो गया है। अभी अभी 15 जुलाई को 200 साइट्स पे हमने 4G इंडिजिनस लगाया है। मैं CEO RK उपाध्याय और इनकी सारी टीम को बहुत बहुत अभिनंदन करता हूं, बधाई देता हूं कि आपने कड़ी मेहनत करके, कड़ा परिश्रम करके, क्योंकि C.DOT एक ऐसी संस्था है। जब मैं नया नया मंत्री बना तो मेरा जैसे हर PSU में विजिट होता था, तो मैं भी गया। तो PSU में विजिट करने के बाद मुझे रियली ऐसा लगा कि इतना एक उत्साह का वातावरण है, वो देश के लिए काम करना चाहते हैं और उनको फंड नहीं देते हैं। तब शायद 62 करोड़ के आसपास था। मैंने बोला आपको जितना पैसा चाहिए हम देंगे। फर्स्ट ईयर में हमने 300 करोड़ C.DOT को सैंक्शन किया था, और इसी का ही परिणाम है आज जो साइट्स हम देख रहे हैं 200 4G 5G भी बना लिया हमने। और 5G आई पहले था, लेकिन अभी तो हम 3GPP ITU के साथ हमारा स्टैंडर्डाइजेशन हो गया। और 5G में इतना काम हुआ है कि वर्ल्ड के कई कंट्रीज ने 5G में काम किया है, लेकिन फास्टेस्ट रोल आउट आज 300 डेज में 3 लाख 5G का साइट किसी कंट्री में नहीं है, केवल भारत में है। ये फास्टेस्ट रोल आउट 5G का हम देख रहे हैं। आदरणीय प्रधानमंत्री जी ने अभी 22 मार्च को विजन डॉक्यूमेंट 6G के लिए रिलीज किया, और हमें बताया कि अभी हमें आगे जाना है, हम 4G 5G से नहीं। उन्होंने ये भी विश्वास प्रकट किया था कि हम बना सकते। और मुझे ये कहते होते आनंद होता है कि 6G अलायंस बन गया है। 6G अलायंस के बाद, भारत 6G अलायंस के बाद हमने 6G टेस्ट बेड बनाया है, जो भारत की टॉप IIT मद्रास में शुरू हो गया है। IIT मद्रास के लिए तो मुझे ऐसा लगता है 2-3 दिन स्पेयर करना चाहिए। जिस तरीके से यहाँ का वाटर कन्वर्जन देखता हूँ, यहाँ का इंक्यूबेटर्स, यहाँ का स्टार्टअप, मोर देन 400, ये बिल्डिंग हर तरीके से ये टॉप है। और मैं अपने आप को गर्व महसूस करता हूँ कि मैं इन बच्चों के सामने हूँ जो देश की टॉप IIT में पढ़ रहे हैं। अब IIT 6G में काम कर रहे हैं, शायद समीर भी कर रहे हैं, लेकिन हमें बहुत जल्दी, जैसे हमने 4G 5G में तो शायद लेट हो गए थे, लेकिन हमें ये एकेडमिया, यूनिवर्सिटी, स्टूडेंट्स, अब जो भी डीओटी के हमारे अधिकारी हैं, डेडिकेटेड ऑफिसर्स हैं, उन पर मुझे भरोसा है और मेरा ये आत्मविश्वास कहता है कि शायद 4G 5G में हमें लीड नहीं कर पाए, लेकिन 6G में अगर वर्ल्ड में लीड करेगा तो इंडिया करेगा। क्योंकि ये न्यू इंडिया आदरणीय प्रधानमंत्री जी के नेतृत्व में जिस तरीके से हम रिफॉर्म्स कर रहे हैं, एक तरीके से ईज ऑफ डूइंग बिजनेस कर रहे हैं, ईज ऑफ लिविंग, सिटीजन सेंट्रिक, इंडस्ट्री सेंट्रिक रिफॉर्म्स हमने किया है। हमने प्रोसीजरियल भी किया है, हमने हर तरीके से रिफॉर्म्स किया है, स्ट्रक्चरल रिफॉर्म्स भी किया है। तो ये एक सरकार है जो ओपन है, ओपन माइंडेड है, जनता की समस्याओं को समझकर उस समस्याओं को निराकरण करने के लिए जो जो व्यवस्था करनी पड़ती है। क्योंकि सरकार कोई भी आए, सरकार अपनी पॉलिसी बनाती है, सरकार गरीब कल्याण या देश हित की कोई भी समाज हित की पॉलिसी बनाए, लेकिन उसको एग्जीक्यूशन करने के लिए, उसको जमीन तक पहुंचाने के लिए आज वैसा माइंडसेट भी जरूरी है और टेक्नोलॉजी भी जरूरी है। आज हमारे देश एक तरीके से रूरल इंडिया में सबसे स्ट्रॉन्गेस्ट टूल जो रूरल एरिया की सोशियो इकोनॉमी को चेंज कर सकता है वो है टेक्नोलॉजी। और टेक्नोलॉजी में हम अपने आप को आत्मनिर्भर भी बनाएंगे और वर्ल्ड लेवल का टेक्नोलॉजी बनाएंगे, एडवांस टेक्नोलॉजी बनाएंगे। और ये एडवांस टेक्नोलॉजी और इसके साथ जब हम 75 साल में हैं, अमृत काल में हैं, कर्तव्य काल में है, देश अब अपना कर्तव्य काल में है, देश चाहता है कि हम अपने टेलीकॉम विभाग के सारे, चाहे यूनिवर्सिटी, एकेडमिया, ऑफिसर्स, हम सब साथ में मिलकर इस देश का भविष्य बदल सकते हैं। क्योंकि 5 ट्रिलियन इकोनॉमी में 1 ट्रिलियन इकोनॉमी टेक्नोलॉजी के कारण है, 1 ट्रिलियन इकोनॉमी। और वह बहुत जल्दी हम अपने आप को वर्ल्ड की 5th के बदले 3rd लार्जेस्ट इकोनॉमी देख रहे हैं। बहुत जल्दी हम जर्मनी, जापान को पीछे छोड़ रहे हैं। तब अगर 3rd इकोनॉमी बनना है और वर्ल्ड की 3rd इकोनॉमी बनने में अगर कोई कंट्रीब्यूट कर सकते हैं तो आप कर सकते हैं, हम कर सकते हैं। क्योंकि देश केवल कोई फ्लैग नहीं है, देश कोई मैप नहीं है, देश देश के नागरिक होते हैं। प्रत्येक नागरिक अपना कर्तव्य निभाए। आप और हम जैसा इस देश की प्रति कमिटमेंट के साथ काम करेंगे वैसा ही हमारा देश बनेगा। और आज इसी मोमेंट पे मैं ये आशा करता हूं और आपसे भी अपेक्षा करता हूं कि बहुत जल्दी हम देश की जो अभी ऊंचाई है प्रगति को, उससे और ऊंचाई पे ले जाएंगे। आप सबका बहुत बहुत धन्यवाद।
Thank you, Shri Deva Singh Chauhan ji. I request Honorable Director of IIT Madras, Professor V. Kamakuti, to please give a token of love from IIT Madras to Shri Deva Singh Chauhan ji. As we come to the conclusion of this remarkable gathering, I have the honor of welcoming Dr. Rajkumar Upadhyay, Executive Director and Chairman of CDOT, the Center for Development of Telematics. Dr. Rajkumar Upadhyay has Masters from IIT Roorkee and PhD in Corporate Strategy and Policy from IIM Bangalore, and a certificate in International Public Policy from Syracuse University in USA. As an officer of Indian Telecommunication Services of Government of India, Dr. Upadhyay has made significant contributions in various capacities. His previous association was with Doordarshan and All India Radio as ADG, where he headed the South Zone of Doordarshan and All India Radio. With great pleasure, I invite Dr. Rajkumar Upadhyay, CEO of CDOT, to deliver the vote of thanks and share his valuable insights with us.
Honorable
Minister of State for Communication, respected Devusing Chauhan ji, Member Technology, Madam Gunjan ji, Professor Director IIT Kamakoti ji, Professor Deepa, Project Lead, and who is running this AOC project, distinguished guests from industry, academia, startup, research scholars, ladies and gentlemen. I think there was I think I'm looking much taller perhaps because of this. I'll reduce it. Yeah, now it's more comfortable. Yeah. Ladies and gentlemen, very good morning to all of you. I think it's really an honor and privilege to be here among this August gathering. Honorable Minister touched upon Atmanirbharta and how the government has shaped the policy of research in this country. Our Honorable Prime Minister launched this mission of Atmanirbhar Bharat. And I remember when I joined CDOT in 2020, I think that time there was a message that can we do something? Is it possible? Do we, there was no belief that this can be done. But Honorable Prime Minister and the guidance of Honorable Ministers, I think we got courage to say that we can do it. And today the results are in front of everybody that we have launched our 4G in Punjab, and soon it will be launched all India, pan-India basis. And it would have not been possible without the support of Honorable Minister of State, Honorable Minister of Communication, and the Prime Minister. Today we are done 4G, and I think there was a point by Professor Kamakoti that we should do 5G quickly. Sir, I would like to tell that the core which is in Chandigarh is already 5G NSA, and by end of this year we'll make it 5G SA. As far as the radio is concerned, we have delivered, thanks to Tejas, which has come up with the 4G radio. And for 5G radio, there are multiple competitors. CDOT is coming out with radio, Tata's is coming with radio, Jio is coming with radio, Lekha, Regenes, Sukta, Signaltron are coming up radio. So radio will have enough competition. Core also will have enough competition. 5G will be done by CDOT. 5G SA is being done by Tata, 5G SA is done by Jio. At least three, I know where the cores are getting ready, and there will be startups also. So in Atmanirbharta, I think the point here is the Atmanirbharta is required for two reasons. One is the economic perspective, there's the security perspective. Economic perspective, definitely creation of jobs, improving socio-economic conditions of our citizens, but there is an angle of security. As security is becoming very, very important because of the malwares, backdoors, it is very important that we have our own technologies. And DOT has taken definitely great strides in terms of announcing DCIS, and with the support of honorable ministers, we got TTDF, which is 500 crore fund. CDOT has its own policy, CCRP, CDOT research, CDOT collaboration research policy. We have Avishkar scheme, we have COI scheme, and multiple schemes. And all these schemes were possible because of the support of the honorable ministers. And in fact, I remember Sir joined immediately after joining, within a week, Sir was in CDOT, and he asked, what is your problem? I said only one problem, humko fund chahiye. And I think uske baad humko fund ka aaj tak we have absolutely no problem. In fact, now we are being asked, why are you not able to spend? That is the question. Earlier we are saying we don't have money. Now the question is, why are you not able to spend? So money has not been a problem at all. And I think we have done good work in terms of, not only developing technology, but becoming a facilitator of the whole ecosystem. Because as CDOT, part of the government, our job is facilitator of the ecosystem, and we'll continue to do this job. AOC testbed we have done. Now the another testbed where we are implementing and see the 6G testbed given to IIT Samir. More testbeds will come, and more and more funding is happening. And this particular fund, what Sir said, 500 crore. And Sir, thank you so much. This is a running fund, means every year it will come. It's not one-time fund. So every year a lot of money will come, and money will not be a challenge with the support of the honorable minister. That money will not be a challenge. We'll be able to fund the startups who come up with a very good technology. Respected Honorable Minister, Sir, I thank you for gracing this occasion, motivating all of us, motivating the whole ecosystem. You found time in spite of your very hectic busy schedule. Thank you so much for blessing us. Thank you for gracing this occasion. I also thank member technology Gunjan Dave madam, who has been driving us technologically from DOT and solving all our problems, whatever we face day to day. I thank Director IIT Kamakoti ji for gracing this function. I also thank Deepa madam, who has been, we have been in touch with sweet and sour sometime, but ended in sweet finally. Because initially we had issues of how do this in terms of distribution. Maybe the policy when it was made in a straight jacket manner, and finally we had to tune, and we are happy that we are working with such great institutes, IITs, so that we produce technology for this country, not only for this country, I'll now very proudly say for the rest of the world. Where we need to concentrate is standardization. The first requirement is standardization. We need to be present in all the standardization bodies. We push our standards, filing patents, and finally producing products out of all these projects in a TRL 9. Like finally the outcome of all these projects, whether it is AOC, 6G or any other technology for which we are funding, should result into products. So I also thank all the distinguished guests of the dais. I thank industry, startups, other participants. I thank one and all, and I wish a great success to this particular conference. Thank you so much.
Thank you, Dr. Rajkumar Upadhyay ji. I request Head of Department of Electrical Engineering, IIT Madras, Professor Nagendra Krishnapura, to give a token of love from IIT Madras to Dr. Upadhyay ji. So thank you all. We will now proceed to the exhibition area. I request all to wait in their seats until all the delegates have left the auditorium.
Speaker name. I think in okay. இருக்கா இன்னும் கொஞ்சம் கார்டு செகண்ட் இதுவே
Is my screen visible? Am I audible?
Sir, can you hear us?
Yes, I can.
Okay, sir. Now it's the break time. Once the persons or we will start at 11:30, sir.
Okay, okay.
Okay, sir. You can stop your screen sharing.
Sure.
Thank you, sir.
Yeah.
Mr. Krishnaswamy?
Mr. Krishnaswamy?
Yes, I can hear
Sir,
you.
are you? Yeah. Sir, is it audible from here?
Yeah, I can hear you loud and clear.
Sir, can you hear us?
Yes, I can hear you. Can you hear me?
Okay, yeah. We'll just check the audio as well as the slides once.
Okay, all right.
Can you please present and check?
Yeah, let me do that.
Yeah, thank you so much.
Can you confirm you can see it?
Sir, can you move to the next slide, please?
Okay.
Yeah, perfect, sir. Voice okay then. Can you just speak for like a few sentences
Sure.
just to check for the echo?
Yeah, this is fine. I'm sure you can hear me. Is that okay? Testing 1, 2, 3.
Sir?
Yeah, can you hear me? Looks like there's a delay.
Sir, can you please speak for a minute? Not a minute,
Yeah, I
few
am
words.
speaking. Can you hear me or not? I am speaking and I can hear a little bit of an echo. Can you hear me?
Yeah, now we can.
I'm getting a lot of echo though.
Can you just
I'm getting a lot of echo. How about now? Is this any better?
அது unmute பண்ணாதீங்க.
Can you? How about now? Can you?
இப்பதான் அவருக்கு கேக்குது.
If I can hear myself, then it seems to be working, but I'm also hearing an echo, but not right now though. Are you able to hear me?
மியூட்ல இருந்தா எப்போ கேக்குது. இப்போ அவங்களுக்கு மியூட்ல
மியூட்ல இருந்ததுன்னா ஆடியோ வந்து ஸ்ட்ரீமிங்க்கு போகாது. அன்மியூட் பண்ணுங்க. இல்லையா அவங்களுக்கு மியூட்டே பண்ணலையே.
I'm speaking right now. Can you hear me?
அன்மியூட் பண்ணுங்களேன்.
Can you hear me now? Can you hear me now? Hello, 1, 2, 3. Hello. 1, 2, 3. Testing 1, 2, 3. Can you hear me?
Yes, sir. Yes.
You can hear me. I'm getting a lot of echo though.
Yeah, your video is also visible.
How about now?
Yeah.
A lot of echo.
Yeah, we are just figuring it out. Sorry for that.
Why is it so hard? How about now? Are you able to hear me?
Yeah.
But if you speak, I'm getting a lot of echo again. How about now? Testing 1, 2, 3. Testing 1, 2, 3.
Yes, sir. Can you hear me?
Yeah, I can hear you.
Yeah. Seems like there is some issue with the audio here only, but we can clearly listen to you.
So that should be fine.
Okay. I
Do
can
you
hear
have?
you fine, and this is fine. I can hear you now clearly without any echo, and you can also hear me. I'm guessing, right?
Sorry, sir.
Can you hear me clearly right now?
Yes, we can hear you perfectly. So do you have any video on your next slide or something?
I don't have any videos.
Okay, fine. So you'll be just talking, right?
Yeah, I mean
There is
one
no.
animated. There is one animated one which I could.
Is an audio required or something for that?
There's no audio required for that.
Yeah, okay, then it should be totally fine.
So can I just play that for a second? Let me see if that works.
You stopped playing. Yeah.
Can you see the animation come through there?
Yes, we are able to. Yeah. Yes, sir.
Okay.
Perfect.
All right.
Yeah.
Okay.
Yes.
All right. I think we're good then.
Thank you so much, sir. Thank you. We'll start exactly at 11:30.
Okay. All right.
Thank you so much.
All right. Take care.
Yeah. Mr. Hardik Soni, are you on call?
Yes.
Oh, okay, sir. Sir, would you please mind if we can check the audio and video once? Can you please
Sure.
share your slides so that we can just see whether it is getting synced or not?
Yes.
Okay.
I think I'm audible, right?
Yeah, you are audible perfectly.
All right.
Can you share the screen once?
Sure.
Yeah, sure. Thank you.
Is the screen visible?
Yes, sir. It's visible.
Thank you.
Can
want
you
me-
just try moving to the second, third slide or something just to. Can you move to the second slide? Yeah, it's coming correctly. Yeah, thank you, sir. Thank you. So we'll start the session around 11:30. I hope
right,
you
so-
both will be on call. Yeah.
Okay, we both on the call. All right, fine.
Yeah. Thank you so much.
Check. 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 நான் இங்க வந்து பேசுறேன் கேக்குதான்னு மட்டும் பாத்து. Can you hear me? எப்ப அடிக்குதா? நான் இங்க வந்து பேசுறேன் கேக்குதான்னு மட்டும் பார்த்து. Can you hear me?
கேக்குது கேக்குது. எக்கோ வரல வரல. ஓகே.
நான் இங்க வந்து பேசுறேன் கேக்குதான்னு மட்டும் பார்த்து. Can you hear me?
கேக்குது 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 கேக்குதா? எக்கோ வரல வரல. ஓகே.
நான் இங்க வந்து பேசுறேன் கேக்குதான்னு மட்டும் பார்த்து. Can you hear me?
கேக்குது 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 கேக்குதா? ஹலோ செக். Hello, check. Yeah, okay. The person who is that. That time you can just turn off.
Can you hear me?
கேக்குது மேரி, உங்களுக்கு கேக்குதா? ஹலோ
Can you hear me?
Yes, yes, we could able to hear you.
Okay.
என்ன சொல்றீங்க நீங்க?
Can you hear us?
Yes, sir. Yes, sir.
Yeah.
Can hear you.
ஆமா.
அதனால இப்ப இபி போட்டு இங்க இருந்து வச்சிருக்கு. அந்த HDMI அவுட் க்ளோஸ் பண்ணியாச்சு. நீங்க அதை ஓபனே பண்ணாதீங்க. அந்த லேப்டாப்போட ஆடியோவே வேணாம். பிரசன்டர் பேஸ்னாலும் இந்த ஜூம்ல இருந்து உங்களுக்கு வெளில வந்துரும் ஆடியோ.
சப்போஸ் பிரசன்டேஷன்ல ஏதாவது வீடியோ ப்ளே பண்ற மாதிரினா
பிரசன்டேஷன்ல
இங்க இருந்து பண்ற மாதிரி இருந்தா நம்ம இல்லனா அங்க பிரசன்டேஷன் போட்டு அதுல வீடியோ ப்ளே ஆச்சுனா
அப்போதைக்கு மட்டும் ஓபன் பண்ணிப்போம்.
கேக்கும். ஏன்னா அந்த மைக் ஆன்ல இருக்கு.
Straight away, we will move on to our next session, session 6, titled as FSO and Li-Fi and Implementation Challenges. May I now invite Dr. Abhishek Dikshit, Associate Professor at IIT Delhi, to conduct the session and introduce the speakers. Thank you.
Good afternoon, everyone. So this session is on Li-Fi and FSO, and we heard a lot about these two technologies yesterday. So these technologies are definitely in news, and we have two speakers for the session. We have Mahesh from Google X, and we have Hardik from Nav Wireless Technology. Both the speakers will be online. So Mahesh, are you there? Are we audible to you?
Yes, can you hear me?
Yes, absolutely. So let me take this opportunity to introduce Mahesh. Mahesh leads Tara at X, Alphabet's moonshot factory. Tara is moonshot to bring affordable, high-speed, high-capacity bandwidth to underserved communities around the world by using a new approach to wireless optical communication technology or beams of light. Before founding Tara, Mahesh headed the manufacturing and supply chain for Project Loon, which used floating balloons in the stratosphere to augment cellular connectivity. Previously, Mahesh worked at Apple, managing a portfolio of strategic products from concept to launch, and a decade at Motorola as a product manager, where he brought WiMAX and LTE product to market. Mahesh holds a Bachelor of Science, a Master of Science in Electrical Engineering, and MBA from Northwestern Kellogg Graduate School of Management. Welcome, Mahesh. We are eager to listen to you. The stage now belongs to you.
Thank you. Thank you, everyone. Hello, everyone. I hope you can hear me very well. My name is Mahesh, and I'm the founder and general manager for Tara, a project inside X. Formerly, we were known as Google X, or Alphabet's innovation engine. I'd like to begin today by thanking the Department of Telecommunication and IIT Madras for organizing this workshop and inviting Tara to come share our progress in developing terrestrial wireless optical communication. And I'm grateful for this opportunity. Now, our mission at Tara is to expand global access to affordable broadband using wireless optics. And we ask a simple what-if questions for all the projects here at X. And what if everyone in the world can be connected to the internet? And what opportunities can we really unlock? Now, this electromagnetic spectrum slide should be no different for many of you. But over the past few decades, the world has been upgrading our wireless network from 2G to 3G to 4G for every 10 years, pacing towards higher and higher frequency in search for faster speeds and more bandwidth. And last October, at the India Mobile Conference, Prime Minister launched commercial 5G services in India, which operators are now rolling out across the country. But as many people in the audience now know, conventional solutions in the RF spectrum alone cannot support the world's accelerated demand for data. Tara's wireless technology leapfrogs this to the optical domain near the visible light. We are operating at 193 terahertz, and we are trying to deliver future-proof capacity. So as the world goes from 2G to 3G to 4G to 5G, you're going to get across a band inside the electromagnetic spectrum where it's difficult for you to communicate any energy. That's often referred to as a terahertz gap. And that's exactly what we're trying to leapfrog over. And at this 193 terahertz frequency, the beams are so narrow that it's nearly impossible to intercept or interfere, thereby adding security to the data transmission. This optical spectrum remains largely unexplored, and it's ripe for wireless technological innovation. Now, Tara's optical links can be used for rapidly bridging gaps in the middle mile broadband infrastructure and to expand high capacity networks from a fiber point of presence. Today, our technology is capable of transmitting up to 20 gigabits per second bidirectionally over distances of up to 20 kilometers with line of sight. And we operate in the 1535 to 1565 nanometers, which is near the visible light. It's lightweight, it weighs about 13 kilograms and minimizes your tower footprint. And over the lifetime of our links, these links can be deployed and redeployed on towers, rooftops, even walls of existing infrastructures. This high throughput WOC, or wireless optical communications, sometimes also referred to as FSO, meets the growing demand for the future operators and can also avoid the cost of upgrading legacy networks. Now, each one of these units consumes just 40 watts of power, about as much as an incandescent light bulb, and can be run on renewable sources like a simple solar power. These terminals are also transmitting laser beams, which are class 1M, eye-safe, so no humans or any living organisms or birds or anything else that are crossing the beam path are harmed. And because the light is propagating in free space, we can traverse from city centers to remote towns to even distant islands without having to dig or trench and lay fiber everywhere. In other words, zero waste over the beam path. So, over the past few years, we've been commercially operating with telcos as well as ISPs around the world, servicing hundreds and hundreds of communities with this high-speed bandwidth. And we are excited to share a little bit more about what we've learned to date. Some of the common ways our operators have been put these links to use is to connect remote communities and villages by extending fiber backhaul. They're also using this to augment existing radio or RF frequency capacity. They're also using this to make their network more resilient and increase their overall availability. And they're also using this to cross difficult terrains and challenging geographies like river crossings, or it could be railway crossings, or anywhere where even simple right-of-way is going to be a hurdle. And these terminals can be daisy chained in order to create a very high capacity backbone from metros to remote towns. We started out back in 2017 in Andhra Pradesh by connecting remote villages over there. And that's it's the seventh largest state. And we started out there, but we've been since expanding in other parts of India. And we've extended this to the hearts of metros like Pune, Bangalore, Mumbai. And Airtel has been one of our early partners and learning partners. And through the pilots that we worked with them, we've gotten valuable feedback and improved our technology over these years. Earlier this month, we announced our partnership with Airtel to roll out these links all across India. This is going to be one of our largest deployments of links in India to date. And we're looking forward to supporting Airtel in its rollout of its 5G network infrastructure, as well as connecting remote areas. And I think that they can play a critical role. Well, let me give you another example of one other ISP that we worked on. This is in Uttar Pradesh. And I'm going to switch to a different screen here to kind of show how we've been able to kind of rapidly deploy this. So as you can see in this map, we started out near Delhi. It's a place called Bagpat, Barot, and Muzaffarnagar. These three towns that were hungry for bandwidth. There was very little bandwidth available in these locations, but whatever was there had to be extended. And so we installed 3 FSO links, or 3 wireless optical communication links in Bagpat, Barot, and Muzaffarnagar. And in Muzaffarnagar, we started to further expand once we have installed that connection using a combination of fiber and wireless optical communication to serve other communities closer to that, like Kuteshwara and Deoband and other places. And what ended up happening is that we quickly ran out of bandwidth that was available in this area. So rather than just waiting for fiber to come to this place in order to increase the available bandwidth, we found that the closest fiber point of presence was all the way down closer towards New Delhi in a place called Loni. And so from Loni, which is about 150 kilometers away, we've been able to fetch bandwidth using a daisy chain of wireless optical or free space optics links of 150 kilometers back to back and connecting all the way to Muzaffarnagar. Now, when we did this, something interesting happened. Some places there was already existing fiber, aerial fiber that we were able to utilize in order to complete this link. However, that aerial fiber was very unreliable. And our free space optic links was far more reliable than fiber optic connection itself. So we've been able to use our walk links as primary and making fiber as the backup to those locations. Now, as you can imagine, when we fetched bandwidth from Loni or New Delhi all the way to Muzaffarnagar, we not only just got 1 gig of capacity, we got 10 times more. We got 10 gig of capacity that we were running through all this backbone, which created an interesting opportunity for us. We now have this entire circuit on 10 gigs, so we've been able to use RF to further connect additional towns all along this entire route. And we've been able to bring additional communities online in such a short period of time. In fact, this whole process of fetching the bandwidth and connecting all of these communities took only 3 months. So that tells you how fast we can use wireless optical communication in combination with existing fiber, as well as RF to kind of expand and connect remote places all around the world. So that was Uttar Pradesh. Now let me go back to my deck and share a few more examples. After the aftermath of the pandemic, Digicel deployed Tara links to provide faster speeds to their mobile broadband subscribers who are experiencing congestion on their multiple microwave links. Those big dishes are the microwave links, and you can see them installing this small Tara terminal, which gets enough capacity to serve this entire tower, not just augmenting those 1 or 2 microwave links. The data usage surged, and just within the first 6 to 9 months of service, our links have been able to deliver over 700 terabytes per week using our FSO terminals. We also established a hybrid network architecture, thereby reliably adding to the radio infrastructure in order to improve their the performance of the links even during adverse conditions, but providing 20 gigabits per second for the vast majority of the time. And over the past few years, the Tara team has been deploying these links in partners in 13 countries around the world, across countries such as and continents like Africa, Australia, Middle East, Asia Pacific, and just beyond India. So these deployments have given us some really good insights. They have informed us about our technical developments and has helped us refine and reduce our costs in the Tara technology so that it can become an affordable part of the global connectivity solution. What we learned from deploying these hundreds of links around the world is to expand the benefits of WALK accessible to more people. We need to vastly reduce the cost structure and the complexity. So what we did is we started to take a closer look at what is driving the complexity of our current systems. It's bulky optics, mechanical steering mirrors, precision optics for accurate alignment, for tracking and communication. And we wanted to simplify this significantly and integrate our terminals, which is currently the size of a traffic light, down to a single photonics chip, and to bring it down to the size of a coin, which is what we are working on right now. So our work is deeply inspired by the technical developments in the RF world. Just like RF, which has a phased array, we have a phased array in the optical sense as well. And we are shrinking the key components and the functionality within our current terminal into a single photonics integrated chip or PIC, if you want to call it. It's smaller than the size of a coin, as you can see on the far right. The chip is built using the same processes that used for making tiny integrated circuits that we use currently in our phones or computers, and provides an opportunity to take a step change in optical design, removing all moving parts and providing a path for rapidly scaling to terabits per second of data in the chip of the size of a pea. The number of elements in the photonics chip means that we can have more narrower beam and the ability to point and track over larger angular range. So let's take a closer look at this chip. I'm going to walk you through these 4 stages. It's only a handful of components. First, the light enters in, and step number 1, where from fiber, it gets coupled into the chip or to the system. From there, it's being split into multiple different rays, number of emitters, if you want to call it, through the edge tree structure. Then it goes to the 3rd stage, which is a phase modulator. This is a critical one, which introduces microscopic delays in order to change the phase of the light that allows us to then emit it right in the center. You see the aperture. That's where they are able to, and the light is being emitted perpendicular to the plane of the slide that you're seeing right now. And this entire beam path is bidirectional. So not only does it emit, it's also able to receive and demodulate the signal in the same focus. So the picture on the right-hand side, the animated GIF that you see, you can see the beam coming in and out of focus as soon as the phase modulator kicks in. So it's diffused initially, but as the phase modulator aligns, you're able to get a more focused beam path and are able to demodulate the light more accurately. So this is not just a function, that is actually a microscopic zoom in of a pitch of our product or for chip. And we have now integrated that into at a bench level in the lab. We have successfully tested this chip-to-chip communication over short distances, up to 60 meters indoors. And our next step is to take this outdoors and then put it into the real world testing. And we are excited to share more update on the progress that we are making in the coming years. So just to recap, Tara is commercially operating with ISPs and telcos around the world. We're a technology provider, and our links are serving very high capacity traffic over the middle mile infrastructure, both in urban as well as rural communities over a wide variety of use cases. In parallel, we are working to simplify and reducing the cost dramatically of our wireless optical solution system, and it makes it accessible for people more closer on the edge. We believe that some of the technology that we've used in these cases is beyond just the telecommunication space. And if you're interested in learning more, partnering, or exploring additional use cases for controlling light, definitely please do reach out. You can contact me at the email that I've listed above at mkr@extra-team, or also the Tara team at tara-team@extra-team. And we are really excited to share the development in the space, pushing on low-cost, coherent architectures and PIC technologies, and expanding the application of wireless optics around the world. Thank you for your time.
Thank you, Mahesh, for a nice presentation. Time for some questions.
Yeah, sure.
Anyone? Yep.
First of all, thank you for giving very good insight into PIC development. I would like to ask one question. Can I know what are all the limitations in the PIC which you have developed in terms of beam steering?
Yeah, so the limitation really comes in terms of the number of elements that we are able to pack. So currently we have a fewer number of elements, but just like transistor technology, we think that we will be able to pack more and more hundreds and thousands of these PIC elements in there. So it's really directly a correlation to the number of elements that we are able to pack. And the foundry technology and the semiconductor processing technology is what is really the limitation factor right now. But I do think just like we've been able to pack transistors over time, we'll be able to pack enough number of elements to almost operate this to a point to multi-point configurations in the future.
If permitted, I would like to know the order of the packaging elements.
I'm sorry, I didn't catch that.
Whether it is hundreds or tens or thousands.
Oh, it's thousands, and our hope is to go to tens of thousands.
Okay, and is it possible to steer in real time?
Yes.
Okay, and visibility?
So the visibility is it's function of whether you without having any optics, you should be able to go hundreds of meters, but with optics, you should be able to go kilometers.
Okay.
And it is going to be subject to environmental conditions. And but without any optics, you should be able to go for several hundred meters.
And you could completely eliminate the mechanical steering. Am I right?
That is correct. That is correct. Just like hard drives eliminated mechanical moving parts and went to SSD, in the same way, we should be able to eliminate and move to a completely solid state steering.
Okay, thank you so much.
Okay, my question is, what is the performance in presence of rain? When you have rain,
so yeah,
the system performs. And second question is, when you use it as a repeater, repeat it across the length, how the performance degrades or how it works?
Yeah. So let me answer the first question on rain. So just like any other wireless solutions, they are subject to environmental degradation. But compared to radio frequency, especially at 70 and 80 gigahertz, we tend to do slightly better than RF solutions, especially if in heavy rain conditions or moderate to heavy rain conditions, we tend to do better than any RF solutions. However, our biggest challenge is fog, where the light disperses, where the attenuation is almost 100 dB per kilometer. And so those are the areas that we try to avoid, or we try to work around it using RFS backup or fiber as backup, or using meshing solutions. So your second question was, sorry, did I answer your first question though, first of all?
Yeah, perfectly. It answered. And second question was, when you across the length, for example, you don't have the visibility, you have to use it as a repeater. So how the performance? Or
yeah. So the performance or the latency of a system is less than few milliseconds, essentially through the terminal. So when you're using it in daisy chain format, you are essentially limited to the performance associated or the latency associated with these milliseconds as they add up over the link. But we have not been able to, we've installed like 12 or 13 of those in daisy chain configuration. We haven't seen any degradation in terms of latency of the system. And however, as you can imagine, if there is an availability impact in any path of the link, then it affects the overall link path. So just like fiber, if you have redundancy or an alternate path of completing the ring, you will be able to overcome that. But because we're transmitting at the speed of light, we are not seeing much of a issue in terms of latency, other than mostly processing delays.
Thank you.
This project, we want to extend the range. Suppose we want to use it as hundreds of kilometers between the balloons. Will it be a viable option for us to use? Why it has not been proven in the loan project?
Good question. This technology, in some sense, originated from Loon. I was working on Project Loon at the time before starting this project. And we did use this technology between balloon to balloon over hundreds of kilometers away. And when you are at 20 kilometers up in the stratosphere, you don't have the weather impact like the way you have it on the ground. So you technically can go a lot more further. And the last week we were able to demonstrate those hundreds of kilometers, and we did very high speed connection between those two balloons using this free space optic terminals. What we have done now is the challenge we had with putting it on balloons was not necessarily the free space optics, but it was everything else around it, keeping the balloons afloat, keeping the techno-economics of having a cell tower essentially floating over various countries and navigating overflight permissions. It's all the things around it. But as such, the free space optics technology itself was pretty robust and solid. And that's one of the reasons why we brought it down to the ground, eliminating all the complexity of floating a balloon and floating a tower, but just putting it down onto the ground on a pole and being able to relay these connections over.
If we forget about an economical reason, so technically, is it okay?
Yes.
So what is the order of power you are using in Project Loon?
Well, Project Loon is history right now, but the free space optics terminals on the balloon was using the same 40 to 60 watts of power, less than a light bulb.
Okay, thank you.
I have a short question.
It's a very
Yeah.
impressive, Dr. Magesh. Can you tell me what is the steerability of that mechanical mount which you are converting into the hardware that pick? I mean, steerability
Yeah, so
solutions, range and
well,
resolution.
we're shooting plus minus 3 degrees is what we're shooting right now. And that's basically our plan to kind of keep it closer towards that.
Okay, thank you. Thank you.
Do you plan to use structured light in any of your, do you have them in the current implementation, or do you plan to use them in the future implementations?
Not right now.
Is that something because you think technologically it is not feasible, or?
Happy to discuss this offline. I think we seem to be getting good amount of traction with the way we are approaching it right now. But if you have additional insights, I'm happy to sync offline on any advantages that you see.
Deepa Venkatesh, IIT Madras, will catch up.
Okay, thank you, Deepa.
Time for 2 more questions. So I can ask you one question. So have you tried to measure the channel? What is this coherence time and what is this probability density function? Can you give some insights on that, or is it too technical?
It is too technical for me, but I'm happy to follow up offline if you have. Exactly, I'm not sure exactly what you're trying to get at.
Have you tried to use some error control codes in your?
Yes, we do have FEC and we do have ARQ in our systems right now.
Are you using HARQ mechanisms also? Hybrid?
Too technical. Yeah. Too technical for me, but I'll follow it up with my engineering team.
Okay, sure. Any last question?
Hi, Mahesh. Just a quick question. I would be very glad to know Google Tara's views on standardization of FSO technology, like if you are looking into it or your thoughts on it.
Yeah, I would be happy to talk about that. I do think that there is a need for standardization of this. You can't solve, look at the number of service providers, number of technologies out there, number of standards that's out there to connect the people that are connected right now. And yet half the world is still unconnected. And I don't think just us alone are going to be able to solve all of that problem. So we're very much open for standardization with the right set of teams and protocols on doing this. Because we do think that this is definitely the foundations of not just 5G or 4G, but 6G and beyond. And I think we've heard enough through this conference about how critically important optical communications is. And so we'd be very much happy to collaborate on some kind of a standardization towards this path.
Hi, sir. This is Gyandeep. What was the maximum power we can transmit in the FSO? Let's say 10 kilometers in the clear weather.
So we are restricted by our EDFA. We have a 1 watt EDFA in our system. And so we basically are trying to limit it to ICFT limits. We have not tried to crank that up. Anything beyond the 1 watt that we have limitations of our EDFA.
Okay, sir. Thank you.
Because of ICFT limits.
Okay, so on behalf of the organizer, I would like to thank you, Mahesh, for patiently answering all the questions and for giving us a nice presentation. We have got a memento for you, which we will ship for you. So I request everyone to clap for Mahesh and for giving this nice presentation. Thank you.
Thank you. Thank you, everyone.
So now let us move to the next speaker. So next speaker is Mr. Hardik Soni. He is CTO and co-founder of NAV Wireless Technologies Private Limited. NAV Tech is a global leading technology and solution provider of wireless and information communication system with its own R&D facilities, manufacturing base in Gujarat, India. The company offers a comprehensive suite of products and services in the domain of optical wireless technologies and transmission system to its global customers. NAV Tech is one of the pioneering companies in the world who provides optical wireless technologies, Li-Fi FSO made in India products. So Hardik, now the stage belongs to you. Many thanks for giving this presentation.
Thank you. The screen. I hope that the screen is visible and I'm audible.
Yeah, perfect.
So thank you. Thank you all, and very good afternoon to everyone for this beautiful good afternoon season. Right now, I'm extremely sorry, first of all, that I'll not be able to present physically due to a very heavy rain in Gujarat. But thank you so much for providing an opportunity to go online and having this presentation to be done. Well, I'll just give you a short brief about who we are. So basically, as we're known as a No Wireless Technologies Private Limited, based in Gujarat. We do lots of research in an optical wireless technologies domain. We do have our own set of facilities to design and manufacture the complete ecosystem to come up with a product in this area. So it's completely homemade home ground that we have established in Gujarat state in Ahmedabad city. We largely work on the communication sides. We also work on some electricity project which is required to be transmitted wirelessly. So we are exploring that as well at our end. We are also working in electronic tattoo for an healthcare monitoring system to monitor the vital signs on the particular healthcare side. These are the couple of research and work that we are doing on the particular domain to come up with a product. As a company, we are largely focused on optical technologies. So we have a product which is currently commercialized by us for an outdoor transmission system. We are also working on indoor access system as well, using a visible light called light fidelity for indoor access system as well. So this is all about outdoor communication using an optical wireless system. It is basically largely known as a free space optical communication. We all are familiar with the number of deployment has been done so far in Indian market globally, having this free space optical communication. Basically, in this free space optical domain, we can use a visible LED lights as well for a shorter distance, and we can use the IR near to visible area, which is called 718 nanometer to 16 nanometer wavelength bands can be used for a long range communication as well. Well, light travels faster than compared to a glass. It is faster than the glass travels, so it is known as a light speed. So it's we can say it's a light speed communication. So that's basically a free space optical communication that we all are familiar now. Based on this technology, we have a product which has been commercialized in 2019, and the product has been designed by us. There are two models that are available right now. One is a 1G that can transmit the data up to 10 kilometers. And we have another product which is a 10G that can transmit the data up to 5 kilometers. Both the products has been designed and developed by us. Now I'll just give you a short brief where the product has been installed so far. So these are the couple of key installations that has been done by us in different terrain of the Indian market. One is Guwahati, which is in Assam, that we have deployed for more than 2 years now. We also did some installation in Ladakh. We also did some installation in Gujarat. Couple of installation based on the telecom network as well called BSNL. So now these are the 2 years of experience having this kind of technology to be implemented in the real environment. So what are the problems and challenges that we have faced so far, and how to overcome those problems and challenges? So this is a very practical challenge that we are facing so far in the market. So let's take an example that you install this product on a particular place of 40-meter mast or a building, and if you feel a swing of the bigger tower because on the high wind. So how to handle that particular part of the vibration which is there in the particular mechanical part of the entire system? So I'll share an example that that happened a couple of months back. We have installed this product on the mast which is a 14-meter tower, and suddenly monkey came up and then they misaligned the entire device. So how to handle that kind of practical scenario that has been faced in this particular technology? So this is the first problem that has been required to be addressed to protect the device to not to misalign on a mechanical part. Second is the pointing. So when the device is aligned to each other, there are lots of vibrations and the jitter happen on the particular building or infrastructure. That also happen on the some mechanical components or electrical parts are misbehaved. So the pointing loss is also the key challenge needs to be addressed in this entire technology. And of course, atmospheric turbulence, which is fog, rain, and all this is basically a challenge for this particular technology. So how to mitigate this problem that has been faced so far? There are many steps can be adopted, and we are working on it. One is you can see there are different two ways to handle this kind of the turbulence that actually happen between the two communication channel link. You can handle this on a physical layer, or you can handle this on a network layer. So we are currently working on both the layers to overcome the challenges that have been faced so far in the real environment. And I'll speak more about the current development that has been done at our end. So we are currently working on adaptive optics basically to handle the most of the turbulence actually happen on the real environment based on the weather conditions and different zone of the Indian market. So thanks to currently new electronic parts are available on a waveform sensor side, which are good enough to design entire system to handle the turbulences in the real environment. So if I talk about, this is the overall architect of the entire system has been designed by us to overcome the turbulence in the real environment. And of course, to move forward on this is our roadmap to overcome the challenge that have been faced so far. One is we are working on the vector beam with the IIT Delhi to overcome the turbulences, turbulence resilience beam transmitting system. We are also working on the quantum key distribution for a defense area to provide highly secure channel for a communication link. Now for a mechanical part, when I say the monkey came into picture and then, they misalign the entire device. So how to handle that? So we are also working on the PAD, which is, a pointing acquisition tracking system, which is the mechanical design that will be, placed on the particular structure building. And one is a mobility device, which can be aligned to automatically each other and can provide a communication. So these are the areas where we have planned to come up as a roadmap of development of the entire technology, more robust, so it can be deployed at larger scale in the market. So we welcome all the players, all the researchers can join hand with us and can lead the India globally for advanced optical communication system. Thank you. Yeah, so that's what the technology and the challenges that we have faced, and we are working on the roadmap plan.
Thank you, Hardik, for this presentation. Any question? Yes. Can someone pass the mic?
So you had a picture which had Guwahati and Gujarat. So what was the typical uptime observed on those practical installations?
So, these are the key installations has been done. So if I'll talk about the particular region that we had so far, one is, for example, Guwahati, where we found lots of rain throughout the year. The product has been there since almost around 2 years. So uptime that we have calculated is around 92 to 93%. So that's the result that we have received in the most rainy environment in the particular northeast part of India. If I talk about Gujarat, where we deployed this on the India-Pakistan border, which is a saline area, which a desert, which normally it's very heat, very windy, and the rain is also sometimes very hard. So that's again a different channel, the low zone, low altitude. But over here in this particular zone that we have achieved around 89%. So that is again a challenge that we have faced. If I'll talk about on telecom sector side, where we deploy this product on the high-rise mast tower like 100 meter plus or 40-45 meter plus tower, where we'll feel the swing of the mobile tower. So we found an issue of around, uptime is around 93 or 94%. That is the result that has been achieved so far. So in all totality, we are achieved around 92 to 93% availability of the link.
Okay, thank you, thank you.
Hello, sir. I have a next question to you. So, have you deployed any Li-Fi based project like you have deployed in Assam, Ladakh, and Gujarat?
Yes, so I'm sorry not to cover that particular part in the presentation, but yes, we started the first project that has been deployed by us in Gujarat state with one of the hospital, which is G+3 building, where we deployed an indoor access point to all the ICUs in the particular to monitor patients' vital signs and transfer data to a doctor's cabin. So that is there, and that is there more than 3 years now. So we have deployed this indoor Li-Fi access system more than in AIMS hospital in Uttarakhand as well, and in Gujarat and in Madhya Pradesh as well.
Okay, sir. And another question is that in Li-Fi, that non-line of sight scenario is difficult to handle. So you must be only considering line of sight, or you working on considering the components of non-line of sight also?
Yes, so the deployment has been done is line of sight. So we are currently working on developing for the non-line of sight scenarios as well for an indoor access system.
The intelligent reflecting surfaces could be one.
Yes.
All right. So hope to work with you in future and connect with you.
Sure, sure. Most welcome.
Hello. As you talked about your system, most of the installation are fixed actually. Okay, point to point. How do you see this prospect of this technology for on-the-move communication, especially between two aerial platforms?
That's what, that's the roadmap of our entire developing this product to go into the mobility side. So when I said a pad, which is a pointing acquisition tracking system, which is really required to have the technology to be communication to be established between two moving platforms. So that's the roadmap that we have it, and we are working on it to design a mechanical part and the electronic part as well, to provide one is static and another is moving, or both the objects are moving, and then provide establish the communication throughout the moving areas. So yes, that's a real use case scenario. Even if it is not talking about the mobility side, when I said, this product has been installed on a fixed infrastructure, say example, a building or a particular on mobile tower, over there is a lots of vibrations and there are lots of swings based on the turbulences and other disturbances. So over there also this auto mechanical and auto alignment system is really required. So yes, we are working on it, and probably in coming years we'll be coming up with the product to be installed on mobility vehicles on aerial side. Sorry.
So at present, actually, if I talk regarding the PAT, do you have some kind of some kind of model or some kind of system available with limited functionality for PAT with respect to this FSO link?
So yes, we are working on it, and we have some prototype already developed, and we are testing currently in real environment scenarios. So the answer is yes. We have some prototype already developed, and we are under the testing in the real environment.
Hello. Yeah. Hi, Hardik. Myself Pankaj. So actually, in my college there, actually, I had like this kind of system design in my project. So it was rejected by my college that this is not economically viable, because like as you in your presentation also said that its range is around 10 kilometers. So 10 kilometers, we need a specific infrastructure for detecting a receiver, transmitter, and also if I will use the wireline like fiber optics cable or like any other cable, so it will be more cheaper than this technology. So I want to understand, because you are working in this, so will you just compare about the economical figure, like how cheap like it is beneficial for us.
True,
Thank
true. So see, since the technology is now good enough and mature, and it's really, doing good in the real environment. So if I talk about the commercial part of the entire technology is little bit higher of having this product to be, replaced on a microwave side. But yes, if I'll talk about an optical fiber to be laid down on a particular, say, example, from one point to another point to 10 kilometer, the cost of the optical fiber is almost, say, around 500 rupees per meter. So if I'll talk about 10 kilometer, it will go up to a 50 to 60 lakh rupees. So compared to that cost of investment, along with the time of required to be laid down optical fiber, compared to that, this FSO system is more cheaper and more economical viable nowadays. That can, reduce the most of the half of the price of the entire, ecosystem laying optical fiber. So it's a complement to optical fiber where the optical fiber is not able to reach, and the cost is really important. And yes, it will further go down on a more economical way where we have more adoption, before adoption, we require to have designed the system to mature enough to handle all the problem that has been faced so far that has been discussed. So yes, so currently, yes, it is up to 20 kilometer calculation. It's justify the cost of having this product to be in place.
This adaptive optics, how to what level it is able to mitigate the channel impairments, or
So,
it is other way?
No, I mean, it's really helping us a lot in terms of the newly upcoming wave sensors have been available in the commercial market. So we have been, getting a good result out of it. We not have fully completed this part of development, but this is the roadmap of going on to have more turbulence-free transmission system having this adaptive optics. So yes, it's good effective. It's very effective.
Can you talk about the bandwidth? How much bandwidth it can handle?
So it's an optical channel. I mean, there is a limitation in terms of having a receiver sensitivity to be received at the other end at the distance. So it is purely dependent. So it's not a correlation between a bandwidth which can be capable. Optical channel has a bandwidth capabilities to go up to 100 gigs as well. It is more on designing the entire system to be capable enough to carry that much bandwidth to X location wirelessly, having all the turbulence in between. Having this adaptive optic side development that will help us to increase the bandwidth up to 1 gig to a 10 gig for a 10 kilometer distance. Currently, we have a system that can provide a 10 Gbps for up to 5 kilometer only. So we wanted to increase that 5 kilometer range to a 10 kilometer range, and that's where we are having this kind of AO system to be implemented to achieve the higher bandwidth. So that is what we are looking for.
Thank you.
Hardik bhai, thank you for your presentation. Just since you have a lot of experience in installations, I will ask two questions. That see, what is the coupling loss from free space to receiver? What kind of loss you have experienced? One question. Second question is, what kind of stability you need in the receiver so that the kind of loss you can forgo? This angular terms, can you tell me? And percentage wise, what is the loss here?
So I know we need to have 2 degree to be very precise to be how the receiver side to be pointed. So to be loss side, it's quite huge loss currently based on the vibrations that has been faced so far in the Indian terrain due to weather impact or mechanical challenges on a particular high mass towers and buildings. So yes, it's a quite big loss that we have. And that's the reason that it is correlated to the availability of the entire link that is not more than 95% as on date. So it's around 92% that has been achieved on the because of this losses occur based on the turbulence that we face.
Thank you. Only thing is, can you tell me in the angular terms you are attributing to vibration? Vibration finally what happens? It's a beam pointing goes every. So what kind of pointing stability you require so that you can sustain your communication?
Sure, sir. I would like to give you all further more detail on the offlinely. So we'll connect over there, sir. You are most welcome to visit our lab also, sir.
Hello.
Yes, sir.
Rakesh Ranjan. Actually, I wanted to know do you have any work or plan to work the implementation of this WOC for the VANET kind of infrastructure, vehicular ad hoc network?
It can be done. I mean, we don't have any plan as on date, but yes, it is possible and it can be done, sir.
I think we can use these things, this idea of WOC for the localization of the vehicles or to transfer the message. I think so.
Yeah, it is possible. I mean, I'll just say, I mean, it's open platform, but I'll not go in much detailed discussion. But we try to use the existing infrastructure which is on a vehicle. Those are the LEDs of the headlights and tail lights. And we did some, kind of real environment tests and one of the authority of Indian side. So yes, it is possible to mount this device on a particular side, but the entire technology, whether it's a visible side or an invisible side, it's the pointing and I mean acquisition and tracking in real all the time of the communication channel is very critical, very critical. And development, that's our roadmap development. Once we are completed with the entire pack system and it's proven and then tested, so it can be deployed any of the application scenarios, whether it's mobility or vehicle or in a naval side, anywhere. I mean, the pointing pad system is really critical infrastructure, which is required to have this product to be go in all the environment scenarios.
Thank you.
Hi, sir. This is Gyandeep. What is the receiver sensitivity for your 10 gig system?
So, sir, I'll share the complete technical details in the group, and you can have it. Because we have different sensitivity receivers based on the environmental condition, geographical condition in the market. Because currently we are on the development side, so I'll share the complete data set with you, sir.
Sir, second question: what kind of photo detector you are using? It is free space based, either fiber coupled? I mean,
so it's a fiber coupled basically.
So what is the coupling loss you are encountering? My question is that because we have a bottleneck of like maximum power transmission, that is the biggest bottleneck what I felt during my research.
Yeah. So I would love to connect you offline and to discuss more on this point, because it's quite a lengthy discussion which is required to understand the pointing loss on the fiber coupling side.
And sir, one more question: what is the divergence loss you are facing? Actually, sir, this is, I mean, because this power is the biggest bottleneck, so that's why I'm asking, because
I mean, it's all is correlate to each other. I mean, it is required to have more offline discussion on detailed side. If I'll answer in one line, it will not be justified to you. So let's connect offline. I will be happy to answer you and help you out in that.
Thank you. Thank you so much. Yeah, definitely I will mail you on your.
Sure.
Hardik, may I ask you one question?
Sure.
Someone told me since 2000, FSO is like a big elephant. The technology is there, but it is never being used since then. Right, 23 years after FSO become a prominent technology, or seemed like a prominent technology in 2000. You are a startup and you are very courageous that you are starting your development in FSO technology. And the investment in this technology by telecom operators is also not there at the moment. So what's your plan? When do you think FSO will become a real dominant force in telecom industry?
Obviously, there are two, three questions that you ask in totality, but yes, the answer is having this technology be adopted in a larger scale is going to be happen very soon, when the availability of the entire technology will be acceptable to a telecom network, which is 99.9% or 100%, just like an optical fibers. To achieve that is a complete ecosystem needs to be built. So far, it is proven that the technology, in 1860s, the technology when Graham Bell actually used the photons to transmit the signal for few meters, that it's proven that the optical channel can be used as a communication channel wirelessly as well. But over the period of since last 23 years, the other infrastructure of the entire technology is evaluated and it's working. I mean, going on in the research side and across the globe. So the components are really available. Previously it was very costly. Now it's not that costly that to worry about the investment part of our side. So we as a company is ready to have further investment on the development of this entire FSO system to achieve a 99.9% of ability of the entire product, along with the backup channel of RF to be get integrated as well to increase the ability of the entire link. And once that is there, I see it's a huge market for our telecom players, and they can straight away adopt it. So that it is the right time of having this kind of workshop to be collaborated and inviting all the interest and research associations together at one platform and design entire technology to go into larger scale in real environment rather to just be a part of some prototyping or some POCs done so far. So that's the roadmap that we can do it together.
Thank you, Hardik. It is very comforting to listen to you that you are also optimistic on this FSO like me. So thank you again. I will like to thank you from on the behalf of the organizer. We have got a memento for you, which we will ship to your place. So thank you so much. May I hear a big round of applause for Hardik?
Thank you.
Thanks. Thanks, Hardik. Bye.
Thank you, sir. May I now invite Dr. Balaji Srinivasan, professor at IIT Madras, to join us on stage for presenting a token of appreciation to the session chair. Thank you, sir. With no delay, let's start our next session, which is a panel discussion on patent and indigenization, challenges and solutions. With immense pressure, may I invite Mr. Avinash Agarwal, Deputy Director General Radio at Telecommunication Engineering Center, to conduct the session. I would also like to invite the panelists, Mr. Balaji Srinivasan, Mr. David Koipale, Mr. Himamshu Hasnis, Mr. A. Raja to the stage. Mr. David Koipale is on his way, will be joining us shortly. So we'll start the session.
Hello. Yeah. So good afternoon, and I think this is the last session before lunch. So welcome all the panelists. I have the opportunity to introduce the panelists, Professor Balaji Srinivasan, Mr. A. Raja from the Patents Office, and Mr. Himanshu from Signal Chip. So instead of reading through your biodata, I would request all the panelists to kindly briefly introduce yourselves. Then we will proceed with the discussion.
Yeah. Am I audible? Yeah. Hello. So I'm Balaji Srinivasan. I'm a professor in the Department of Electrical Engineering at IIT Madras. I'll start with a disclaimer. I'm probably the least eligible to be sitting on this panel. Primarily done academic work, but on the other hand, I think I've been brought in here to bring an academic perspective. So I have some messages for the students in the audience. So look forward to sharing them in the course of this discussion.
Good afternoon. Myself is A. Raja. I'm working as Deputy Controller of Patents and Designs in the Patent Office Chennai branch. I think I have I'm going to complete 20 years of experience in the patents. And today, most probably, this session would be a lighter moment since so far you have been discussing about technology, and discussion of all these things. Now we have to have how it has to be protected and what are the implications if it is not to be protected. So that is going to be a discussion today. Thank you.
Yeah, hello. I'm Himanshu Khasnis. I'm founder and CEO at Signal Chip. Signal Chip is a fabulous semiconductor company, and in the last 1 decade, we have built the first 4G, 5G chipsets from India, and we have filed some patents as along that course. So I'm kind of happy to be part of this panel, and I'll try to share my experience as per this one. Thanks.
Thank you. So in fact, the topic is patent and indigenization challenges and solutions. And we'll be talking more about the advances in optical communications. But before we come to this specific topic, let us just have a general discussion. And maybe many of us are not very much familiar about the. Okay. So welcome, Dr. David. So we were just about to start the discussion. It will be great if you could kindly introduce yourselves to the audience.
Good afternoon. It's a pleasure to be a part of this panel. I'm David Koilpillai, a faculty member in the Department of Electrical Engineering. I've been at IIT Madras since 2002. Prior to that, I was working at Ericsson in the research department in the USA for 12 years.
Thank you. So in fact, we have a very diverse panel and a balanced panel because we have two esteemed members from the academia, then we have from the industry and from the patent office. So we, and I'm from the government, but we are looking after the standards pass and also like monitoring of patents. So I think we have a very good representation of different verticals which are related to this. Just to give a brief background that yesterday also there was lots of talk about there was a specific session on standards, and then in the morning session today the Honorable Minister and others also talked about patents and need for indigenization. In fact, some targets were there for domestic manufacturing and research. So in that context, just to give some background about TEC, that Telecom Engineering Center is the standard setting organization of Department of Telecom. So while we are drafting certain specifications and standards, we are also representing the country in ITU for telecom related and related ICT related things. Recently, based on directives of the government, we have started monitoring patents also, specifically for telecom domain and focusing on emerging technologies. So we'll be talking about that also as we move forward. So before we start our first question, I would just like to know from the audience that how many are the students, if they can just raise your hands and so that we know that. Okay, so quite a few are students. Others are also from the academia or from industry, like anyone from the all those who are related from the academia side. So quite a few, in fact, more than half of them are from the academia background. So it will be very good to understand that how many of us are very much convergent with the patent filing or patent publishing process, because what I understand is that most of the time the students, even the professors, the researchers, they are more comfortable in publishing research papers, and whether the challenge in filing a patent is there or is it a lack of awareness? So, Professor Balaji, your views.
Sure. Yeah, so we are in the business of furthering the goals of science and technology. So that's the primary objective of what we are doing as far as research is concerned. And in fact, when a research scholar is entering our campus and is pursuing this master's or PhD, what we ask them to do is to publish research papers. So the passport to get out of campus, the way they earn their degree is by publishing research papers. So that actually becomes the sole goal of the student coming in, right? And of course, we can deliberate on this, whether we should allow patents to be part of this equation and so on. But nevertheless, I think as research guides, we have the responsibility of educating the students on the importance of actually having patents, or in general, you could also have copyright on things, the piece of code that you guys write and so on. And specifically, I think it is very important for students to understand that patents and IP in general are becoming the new currency, especially from a startup perspective. The valuation of the startup itself is actually being based on the number of patents or the IP that they possess. I was fortunate. When I went to school at University of New Mexico in USA, I was part of a setup where the university had hired this science and technology cell. There was one company who was sitting right next to our campus, and their job was to not only patent all the novel aspects, the IP that we generate, but also market that patent and generate revenue for the university. So, like I said, like the patents are becoming the currency, the new currency that are being dealt with. And so just after, I know all the research scholars would recognize this terminology, the research proposal seminar. When you embark on your PhD, you do a research proposal seminar. That was attended by one of the attorneys from that science and technology cell. And right after that research proposal seminar, he sat down with me and said, you said all these great things about what you're going to achieve. And you said so many novel things are going to come out of that. So why don't we talk about, patenting all of this? And I was like, really? I didn't think it was, that big a deal at that time. But he told me one important thing, that is, to file a patent, especially there's something called a provisional patent. To file a provisional patent, you don't have to get all the results. It has to be just an idea you have at that time. And by filing the provisional patent, you are just making sure that that idea is assigned to you. There is a priority date that is established for that idea. So we went on to do that. And I'm happy to say that most of those things, it actually set off a series of patents. So by the time I was done with my, a PhD, we had a set of patents which were marketed successfully, and it generated revenue also for the industry. So that was a great model, I thought, where research scholars could be exposed to this idea of patenting right up front, and there could be some commercial value derived from this.
So, yeah, Dr. David. So I would just like to further ask on what he said, that is there any rule or thumb rule that what should be as a student or a researcher? So whether they should publish it or whether they should file a patent, like what is a eligible case for filing a patent, and what should be published, or whether we should first file a patent and then publish? So kindly elaborate.
Thank you. I'd like to pick up where Balaji left off. Yes, a research student is expected to publish. I think that is one of the key things. But maybe I'll speak to the students directly. Here are the steps that you will follow when you want to do research. You will pick a topic. You will do a literature search. You will see what others have done. And then if there is a particular approach that has not been tried, then you start to work on it. All that is same in a patent also. At that point, when you say that, okay, I have a better way of solving this problem, that's where we should ask the question, is this something that is patentable as well? And I think Balaji referred to it, saying that, yes, that is an important decision. It is not either or, it's not publish or patent. As Mr. Agrawal said, we can do both. And I believe that we have come into a time frame where it is important for students to also consider, academic institutions to consider. Having said that, I would say that the starting point is for faculty to be sensitized on what are patentable ideas, how do you go about doing the patent. So we'll talk a little bit more about it. But I agree with Balaji. I've sort of taken it one step further, saying that the processes are not different. In fact, there comes a point where you can make a decision.
So maybe Mr. Raja.
Yes, actually, as for the Patent Act is concerned, once you published, you are perished. So since it is killing the novelty of your own idea, your own, the invention. So as Professor Sir has rightly pointed out that why don't you think about the patenting? Patenting should be the first criteria as far as the academy or the research people or the industry is concerned when there is a scope for patentable subject matter. And if you are going, there is no, as Professor Sir also said that you can do, line by line. In parallel, you can do the publication as well as the patenting processing through provisional application. And the Patent Act has a 6 months time period from the date of publication to file a provisional patent or to file a complete specification. As Sir rightly pointed out, you don't have to write the complete specification or the description about the entire invention. As prescribed to the Patent Act as a complete specification, you can write 2 or 3 pages of write-up and file a priority date, file in the patent office with a priority date. So the even if the student is been giving the to IPR cell or IPR department, and if the IPR department is not listening to you, in such scenario, you can file a patent on your name. And during the course of patent prosecution, you can convert or you can assign your patent to IIT or the education institution. That is also possible. As far as the patent filing procedure is concerned for an individual or for a government funded institute, it will be like the finance is nothing but less than 10,000, starting from Form 1, Form 2, Form 3, Form 5, Form 9 and 18. And as far as the publication is concerned, if you are filing everything in a patent office with all kinds of documentation or project report, or it is similar to the kind of project report, it will be published within 18 months automatically. Even if you are filing, even if you are not filing Form 9. Form 9 is a form which is used for records for early publication that will be published within a month in IP journal, as per the Gazette of India. So you have the provision. What I'm trying to say, even if you are missing the publication in your academic institute, you have the provision that Patent Act enacts, gives you the help that your application will be published in a IP journal and it will be known to the public. Only the abstract will be published. So you can go in tandem with the publication as well as the filing of a patent application.
So, Himanshu, I will come to you a bit later. Let us first understand the fundamentals that is more important for beginners like us also. So one more question, Mr. Raja, and perhaps both Balaji and Dr. David can add, that usually we are publishing a paper when we have an idea, and usually we have validated it through some experiment or through some simulation and others. Is it required for a patent also that we have to validate the idea, or if we have an idea, then also we can go for a patent filing?
No, actually, as far as the Patent Act is concerned, ideas as such is not patentable under Section 3 of the Patent Act. So you have multiple patentability criteria under Section 3 of the Patent Act, wherein the frivolous inventions, the DNA sequences, and cloning of human beings, mathematical methods, and computer programs, all these things are not patentable. Even though it is an invention, it is not patentable. But the idea should be in an implementable format. As Professor Sir rightly pointed out, if you have an idea, file a provisional application, you got 12 months time period to make it as a provisional to complete. And if you're not able to make it out, you can have multiple provisional specification till you get the idea to be in the implementable format, or if you are very well thorough that it can be converted into a product or into a kind of service, then you can take a time of a 12 months period to convert from provisional to complete specification. So that kind of leverage or timelines is given for the Patent Act is concerned. But the Patent Act, as far as the Patent Act is concerned, timelines are very much important. If you are missing the timelines even by one day, then it is gone. So that is the that is a strict rule followed by the Patent Act.
So, Professor Balaji, would you like to add, like if we have an idea, I have an idea, but I have not validated it till now, so I will not be able to publish a paper.
Right.
But should I file a patent?
So when to even file the provisional patent, you have to be judicious about it. Like Mr. Raja pointed out, you are given 1 year time period to validate your idea and develop some, experimental, or even if it's theoretical, there's got to be a very sound foundation for that. So to develop that foundation, your time starts ticking, and you have to finish that within the 1 year period. Now, if you think your experiment is going to take at least a couple of years to set things up, and you need that much time to get into the proof mode, then you may want to actually hold back your idea a little bit. Maybe the provisional can be filed just 1 year before when you expect the results to come out, right? So you may want to be judicious about filing the provisional as well. Instead, in fact, I mentioned that provisional should be a no-brainer, but nevertheless, you have to be aware of the fact that you have only a 1 year time period to file the patent. So you need to, ask yourself the question whether you have enough time. And I would like to just amplify what Professor David just now mentioned. Every journal that the research scholars go to today, when you, try to submit a paper, the first thing they ask is, what is the novelty or impact of your work? So when you're defining that those are the claims of your potential patent as well, right? So you have to be aware of that. So if you are at that stage, you may very well get into the provisional and follow up with a full patent specification.
So, you would like to add something?
Maybe I'll add something which is complementary to what Mr. Raja and Professor Balaji has said. As a student, the question probably in my mind is, what is patentable? In the sense that, I have come up with some results. I've actually verified it. In the sense that I have now proof that it works. I have a reduction to practice. Now, is this patentable or not? Very often, people like us, engineers or who are trained in technology, look at something and say, well, this doesn't look that significant, doesn't look that earth-shattering, so maybe not patentable. But in the definition of patent, and maybe I'm sure Mr. Raja will expand, help us understand it better, what is novel and non-obvious, and non-obvious to someone who is skilled in the art. And believe me, many things of what a student considers obvious is actually not obvious in the context of a patent and is possibly patentable. So that is a message that I would like to leave with you.
One more doubt in most people's mind is that it's a very costly affair. Like in our office, we usually come across various representatives of various multinational companies, and then they hire attorneys and all those, and then they charge in lakhs of rupees. So is it mandatory that I have to hire an attorney? How costly is it, or can I do it on my own if I'm doing for the first time? So maybe Mr. Raja and then maybe Himanshu ji can also add.
As far as my knowledge is concerned, we always, I mean, who is going for the officials who is going for creating an awareness for IPR thing. We always suggest, even though the audience might be having some patent attorneys or lawyers or advocates who might be sitting in getting their business into that patent filing procedures, I always suggest that the inventor or the person who is involved in the invention or the idea behind that, he is the best person in the world who can design, who can write, who can draft the complete specification on his own by doing kind of some good amount of homework through Google Patents and Google Scholar. So it's like, as David sir rightly pointed out, it is like, it's the replication of your documentation, a replication of your thesis work. It starts with the background of the invention, like summary, and what are the things involved in that, and what is the technical background, what is exactly the improvement you are doing it, what is the technological advancement in that, what is a novelty with respect to your other existing system. Even if it is there is no novelty, what is the technological advancement with respect to inventive step. So that if you are claiming it as such as a whole, then I think the inventor as a person can write or draft the complete specification on himself. And the patent office, after filing it, like sir was pointing out, whether financially is viable or not. As far as the Patent Act is concerned, the recent amendment rules in 2020 and 21, they have divided into some number of 8 categories of applicants: natural person, SMEs, startups, and government institutions, education institutions, government funded education institution, government department. So these people are falling under the category of natural persons whose filing fees will be like, with the combination of Form 1, 2, 3, 9, and 18, it will be less than 10,000 only for filing of a patent. But of course, Form 18 has to be filed with, it will fall under the 10,000 only. And this Form 18 is nothing but the request for examination. You are requesting the patent office under Section 11 and 12 of the Patent Act. It has to be examined and investigation report has to be given. So with respect to Section 21J and non-patentability criteria, the patent office will give you the complete examination report. Then the further process will go on, and most probably within 1 to 1.5 years, you may get the final patent certificate that will be generated. And it's not like, sometimes it is time consuming. Of course, getting a patent, you should have a patience. Of course, some people used to pronounce it as a patience. Of course, you should have much more patience to get a patent certificate. Since the Patent Act is designed that timelines are important. So we are in the process of, the Ministry of Commerce and Industry and the CGPDTM, we are in the process of reducing the pendency rate from 1.5 years to 1 year, less than 1 year. And we have granted patents within 100 days also with the expedited route. So there are different routes are available by paying extra fees, government fees, assigned government fees. We can get the patent prosecution as early as possible, get the certificate or get it disposed as early as possible. So it's better to work out on your own for filing a patent drafting. And then if you are not satisfied, the concerned person or the patent attorney, or before moving to the patent attorney, you can very well talk to the IPR department of your own academic institution. Then you can come out with an idea whether it can be drafted through patent agent or attorney or whoever it is like. So that is what my personal opinion and suggestion towards the students and faculties.
Himanshu ji, your views?
I think at the outset, I think it's doable as an individual on yourself. But I think I would like to differ with what Raja sir told with due respects. What we have found while I was earlier in my earlier career in MNC, where we filed many patents, and even as of now in Signal Chip we are doing, there is a Indian Patent Office set of rules, but you end up also mostly filing a US patent and many times an international patent as well. So by the time you finish all these things, there is a lot of paperwork you have to go through. So would I like my designer to be doing that? The paperwork portion is something that I would look at as this one, and I would not probably want to do that. So usually what happens is you will work with a patent attorney and he will work closely with the technical innovation is brought out by a document which the inventor himself comes, and typically all these companies have some format where we internally do that. That does not really worry too much about what is the actual claims wording that you have to put in. But then by the time it actually goes from there to filing a patent, typically there is a couple of months of rigorous discussion that happens between the attorney and this. And the language over there is extremely legal, whatever goes into the patent. Sometimes we have seen that, is this my idea itself kind of a thing, right? But that happens because the way the claims are drafted. Ultimately, even if you claim some 20 different claims, you may be awarded 6 out of it or 5 out of it. So a patent attorney knows in general what this is. And even before that, what you have to probably do is a prior art search, where you go and actually search if there are other patents which have come in. Many times, most of us are working in the industry and in academia on similar problems at the same time. So you end up having some idea which probably somebody else got and you don't know about it, kind of thing, right? So there's a bit of danger also here. I wanted to add to the previous point as well. Why it's important to immediately file is, in case you don't and somebody else does, then you will have to pay royalty to them to do your own idea. So it's always better to go off as soon as possible also. But then, so when we draft these claims, it gets fairly technical and fairly legal. So that is one portion of it. And we have seen many objections coming specifically from international patent offices on the kind of language used. Okay, you change 2 words to some other 2 words, they will allow you. Otherwise, it will not be the case. So these kind of things, we may not have the expertise also to figure how to put this up together. So in general, we find it easier to work with a patent attorney. And when that comes in is where the cost actually goes up. Both in the Indian context or US context or even the international context, the actual fee that the patent office itself asks for is not that big. Okay. But you end up hiring a patent attorney, and there's a price in India, it's expensive. In US, it's even more expensive. I mean, we know the way it goes. So figuring out what the cost of this is a critical aspect. And also there is another thing, if I'm correct, at every 3.5 years or 7 years, a patent comes again, even if it is granted to you, you need to still maintain it. You need to again pay fees and stuff like that. And also if a examiner finds that some of your claims are not, typically they will say that this is already present, like what Professor Koilpillai told. Somebody says this is all there, right? But then you have seen the novelty in it. Someone has to go present to it, and that will have timelines, that will have rules on how you can actually go present it back to the patent committee there. Will we be aware of all these things? I personally feel it's difficult to be aware of all these things. In larger companies, we will usually have a department which is internally legally qualified, and they do the work. So in smaller companies, it's always easier to work with and that expense goes into many lakhs. Just for your.
So coming to closer to our topic, you wanted to say something?
Yes, I just thought I'll just add one comment to that. As Mr. Himanshu said, that having a patent agent who understands the technology and is able to draft using the correct legal formats in terms of independent claims and dependent claims, I think there's a tremendous advantage. But I think to the point that made by Mr. Raja, it cannot be that we just write some document and then throw it over the wall for somebody to figure out. I think it's very important that we also understand what is the language of a patent, be able to understand how it should be presented. So I think the aspect of having the patience to read and learn about the patent terminology, I think is very important. So that's one point that I wanted to add. The agent is definitely an asset, but our knowledge of patent language is also very important.
So now,
just one quick comment about that. The other value that a good patent attorney can bring is, as inventors, we are too much tied into the specifics of the idea. We say it has to be this form, this way, and so on. And the patent attorney, if it's a good one, they ask a question Why can't it be like this? Why can't it be like that? They broaden the scope of the patent, and that actually adds a lot of value to the patent itself, right? You may be limiting yourself to a very small thing. And of course, I've seen a lot of lousy patent attorneys also who are like, I have to work harder than them to actually get the patent in shape. They completely mess up my idea. But there is a process to actually find the good patent attorneys. And once you do that, you stick on to them.
Okay, so in fact, now let us come closer to our topic. One thing that our Honorable Minister Office wants us to do is to track patents that are being filed by Indians or Indian companies or Indian academia related to advanced technologies, emerging technologies, specifically to 6G also. And you might have been reading in newspapers that sometime back there was a statement that now we have more than 200 patents related to 6G. Before that, it was around 100 patents or so. But now that task is with my division in TEC, and we are like tracking three sides: our Indian Patent Office, US Patent Office, and WIPO. And then we are looking for certain keywords, also looking for certain academic institutes and certain R&D institutes to track which patent could be considered as a 6G patent, like which have been filed or which have been like published. So in last 3 months, we have done this work and we have prepared a dashboard also. But our experience is that it is very much like manually searching different websites, looking for different keywords. So are we doing the right thing, or is something missing? Like, can it not be possible that there is some attribute and then we say that it is 6G or related to 5G advanced or something like that? So I would first request Mr. Himanshu to share that if like you are doing some work which may be qualified as related to 5G advanced or 6G, but perhaps in our tracking, we might have missed the work done by your organization. So how can we track patents filed by India or Indian companies, applicant country India, related to 6G?
Yeah, I think a generic approach would be like what you're trying to do, right? You're going and searching based on some keywords, right? So, and which may not be bad, because if I feel something is relevant to 6G, I will make sure it's there in that patent application. So there are many patent reports which come where people do they have this search engines which go behind and data mining engines which go and pick based on those. Okay, but as since you are from the government itself, one method may be to just make sure that if anybody files and it is 5G or 6G, they actually inform you in some manner, basically that this is a 5G or a 6G essential patent that I'm putting in here. And that same provision is there even in the, for example, if I think my patent is a standards essential patent, I can actually go and tell the same thing to 3GPP as well, that this is a standards essential patent, or even in IEEE.
I will come to SCP later,
okay,
because I am we are just tracking patents. SCP is something we'll discuss later. But like,
if it is general particular domain, I think we will have to live with options like searching, or we can try to do a voluntary disclosure to the government also that this is under this kind of a thing. We can think of some mechanism like that, but otherwise, I think
can I ask Mr. Raja that is it possible to have at least 2 attributes in the submission form itself? Like we have that broad category, it is related to telecom, and some subcategory like where we are saying it is related to advanced optics or 6G or 5G or anything like that. Is it because right now I think there are so many columns which are related to applicant country, synopsis, and all those things. But is there any particular attribute or a column related to this?
Just interjecting there, because I think I mean, as you are speaking, because any patent we file even outside or here, we are mandated to first file it in India. So I think probably while filing here itself, if we ask them to provide that information, that may be something.
Yeah, that's what I mean. There are no different columns. Actually, the form one is self-explanatory, which is going to be filed by the individual applicant, which gives you a lot of details about the title of the invention. The title may be like, it may be different, but with the title, you can't judge that it is related to this particular technology or 5G or 6G or whatever it is like. But by going through the drafting of the complete specification, it starts with the title. It starts with the background of the invention. What is our background? What is the field of invention? In that field, what is the exact technology you are applying? What is your exact invention? And what are the previous existing systems or previous existing?
Sorry to interrupt. Now, my specific question is that it may not be in the subject, it may not be in the abstract.
Okay.
Because there may be very specific like methods and procedures for this and this. So is it possible to add at least 2 attributes or fields or columns, whatever you call it, in the application form itself, which is searchable on your website through the different filters to be applicable, where we can identify it is related to telecom, and then within telecom also it is related to, say, advanced optics or like that. It is not there, I think, right now.
It is not there as of now. It is not implemented in the form one, but the search strategy includes that you can search the entire complete specification. The keywords, when you type in the keywords, the relevant keywords, if you are putting it, it will search the entire complete specification of all the entire database of all the patent things, and it will fetch you the desired results. But the keying of the relevant keywords is that is the we have to learn on your own. Like, so in that thing only, as Mr. Himanshu was saying, that the patent attorney will guide you in good manner. Like, so as an individual, we may not be having the much idea about the relevant keywords. So the patent attorney will be drafting in such a way that it may be related to 5G, but the relevant keywords may be different. So he might be having some knowledge about the synonymous keywords or relevant keywords. With the keywords only, he can fetch the data as your requirement.
So for our tracking, we still have to do that manual process only, that is search for different keywords.
Yes.
Okay. Okay, so in advances in optical communications, lots of topics were discussed yesterday also, in the morning also. Future transceiver, fiber technologies, free space optics, Li-Fi, photonics integrated circuits, QKD. So where does India stand as far as indigenous technology and patent filing or patent granted in this as compared to the rest of the world? Maybe starting from Balaji and then.
Yeah, well, unfortunately, not really at the state of the art. So we're still lagging behind, I think, primarily from the infrastructure point of view. Some of the major laboratories around the world, the kind of equipment that they have and the level of deep thinking that they're able to get into based on, the experimental validation of some of their ideas, they are much further ahead than where we are. But there is a place to start for everything, and I believe this particular project that we are running right now is a very good start, because it's one thing to have an idea, as we talked about, but it's another thing to actually put that idea into practice and validate that idea. And that requires tremendous investment in terms of the infrastructure. And, by establishing that infrastructure here, I think we are going to be in a good position in the years to come.
Yeah, I think he kind of told it right. But there's definitely a general gap in not just this particular field, across the industry where we are. The number of patents that's filed by Indian companies, Indian academia, and this one is significantly lesser than what is being done in the rest of the world. But there is a silver lining there also in a different manner, that in the last few years, we have seen year on year, we are filing more patents as a percentage compared to what was being done. So I think this gap is going to get closed, but even if you see the amount of patents that the Indian Patent Office has approved also, it's significantly higher in the last 2-3 years, in fact. Okay. But there is I mean, in general, we have seen the West has always been filing patents. They have had a research, I mean, there's a gap, they have gone ahead. We have seen a lot of patents coming in, especially the 5G field when we saw, a lot of patents came from China. Okay. It appears like there is a concerted effort from the establishment there to get more and more patents into the field, which has made it push through. Okay. So we are responding, we are coming in, but there definitely is a large gap in these, and it's somewhere it is set. I don't know. I mean, if I'll digress a little bit, maybe it's a little bit in our psychology is also our feeling. The age-old story of J.C. Bose not patenting his radio and Marconi doing it later. Yeah. And I mean, I don't know how true this is. Apparently, J.C. Bose told Tagore that, how can I hold Ma Saraswati in rains? I mean, it's supposed to be told to everyone. So maybe we don't have that or something like that. But I think now we are more savvy. There are more startups coming from academia. So where research is happening, there is a value being seen for ideas. I think this has to happen more and more. And I think a place like AOC testbed or 5G testbed are perfect places where this can be done. And definitely some amount of strategic support is needed from the government as well, so that even the small companies don't hesitate to put in. By the time we close a patent, it goes somewhere about 7 to 10 lakhs of expense if you have to hold it through. Now, if you have to do a lot of it, it's a reason. But as a startup mentality, I think India itself has to look at it like that, because in an established company, usually people scrutinize a patent application a lot before even going out. Whereas in a startup, they want to have more out, because it, as he told earlier, it adds to a value. I think as a country itself, we should see it like this so that we can get more and more.
Professor David.
I would like to add one point with respect to that Indian patents. In the last quarter of 21-22, as per the annual report, Indian nationals have surpassed the foreign nationals in filing the number of patent applications. And recently, I've just had a search query with respect to Internet of Things. It was surprising. I don't know whether the technical people you might be may not be surprised. Internet of underwater network, which was granted. This is what the title says, and I have not gone through the entire title. I mean, it was granted to NIT Patna. So this kind of awareness has been created through Patent Office and CGPRTM, and all the academia and the research people, they are putting all their efforts into that filing of Indian patent applications. Right? So that is also happening. Like as Himanshu rightly pointed out, we are in the process of disposing as many as, the patent offices are disposing as many as FERs and disposal of patent to be granted also. It is all, we are doing it in a rapid rate. Like. So we had a lack, we have a lack of manpower. So that is because now the manpower has come, and because of the manpower, we are doing it in the faster rate so that the benefit will go to the applicant, and the applicant as an inventor will become a patentee once it is granted. So I think we are moving in the right direction with respect to the indigenization or the Indian patent filing is concerned. This is the 21-22 data, and 22-23 data is being prepared, and it goes a tremendous growth, especially in the case of optical communications, not in optical communications. As far as the communications applications is concerned, in 21-22 itself, 3,800 applications have been filed, and which is surpassing the computer-related applications. After 2020, the computer-related applications have gone into a big leap, and these communications in 21-22, the number of applications has taken the lead. So it shows that we have a very good growth. Of course, 72, 75, 80 to 85% of applications have been filed by MNCs or the other than Indian nationals. So that is also a concern, but still this 15% is rapidly increasing to 20 to 25. I hope it will be more than that because of the, we have a robust IP ecosystems based on our ministry's recommendations, and with the help of all the IITs and academia, we are going to achieve in future.
So I think we have very less time now. Let us quickly go through what are the challenges and what solutions can the panelists suggest related to both patents filing and as well as the challenges in Indianization or domestic manufacturing of all those technologies that we have discussed for the last 2 days.
So I would like to propose to the audience two important suggestions. One is we start monitoring, supposing I'm interested in a particular aspect of 6G, start monitoring patent applications that are happening in that area. That means that we would have to look at as the patents are being filed and granted, field of invention, background of invention, object of invention, basically to get an idea. So we get an idea of who is filing, what topics they are filing on, and so that knowledge has to be built up. So we have to do that. Having said that, we also need some mentoring of people who are filing of patents, particularly in a project like this, where we can handhold a person who is filing a patent for the first time to help them through the process and the steps. So I think the mentoring and the monitoring of what is going on in the field are two important areas.
Yeah, I think in general, I think one point is how we convert a lot of these patents into actual products which bring in a larger revenue and economic value to the country. I think this is one angle we need to work on. In that, I think sometimes a two-way industry, academia, consultation, and co-working may be a good idea to go in this. One is to take a patented idea and find how to get a market to that, how to make a product out of it, or maybe in a longer time, figure out with the help of industry what's a problem that needs a new solution, and even drive our research through that kind of an angle. So it's a two-way thing. So that I think is one critical stuff. And in general, I feel the patent ecosystem here itself has to increase. I think in India we have about, if I'm right, I looked up at some 600 people who are actually examining the patents. Okay, whereas in US I think it's 8,000 people, and in 13,000 in China itself, if you look at it, right? So I think that ecosystem also has to grow along with that. We should make more people come into that. Maybe it's a good career opportunity for many people who are technical and have some skills on legal side. So I think that is one thing that we should probably work on, try to cover that gap as well in this one. So these would be my couple of suggestions in the.
So this consortium that is being discussed, I think that will bring the industry and the academia together and will be like helping in this direction.
There is one specific thing I was thinking, maybe in this consortium, in AOC consortium, Deepa ma'am is here. Maybe we can have some patent expert who is kind of guiding all the companies, one or two. I mean, maybe based on where somebody is in Delhi, maybe we can have someone in Delhi, someone in Chennai, and someone in Bangalore as part of this, guiding us and kind of constantly telling us, hey, file this idea kind of thing. I don't know. Something that we can do.
Your thoughts?
The solutions, like we are actually not into the enforcement. First, the challenge is enforcement and litigation. The enforcement of IPR and the litigation is a very costly issue, and enforcement is very difficult as of now. Since the judiciary people also, may not be having much idea about the IPR. Maybe they'll be having a little about the IPR, but once the litigation process goes on, some kind of technical person has to guide them to dispose the case so that the patentee will get the right hold. Even after getting the patent certificate also, he will not be in a position to use it properly, since it has been opposed by somebody else or third party. So this is going to be the biggest challenge. And recently the IPAB has been dissolved, Intellectual Property Appellate Board, which is looking after this litigation, all these things has been dissolved, and all the high courts are managing. They have started a separate IPR department. They are looking into this litigation process. And recently we have seen in the last 3-4 months, something around 150 to 200 patent litigations are under process. Even after it is granted, refused, the applicant is in the process of reviewing those patents. So this is one of the biggest challenge, and the court can, the High Court can go for under Section 115 of the Patent Act. They can appoint a scientific advisor who can help the judiciary people in solving the technical things. So this may be the solution. And as far as the patent office is concerned, we have already created under the umbrella of National Intellectual Property Management, NIPAM. We have covered almost in 2021, 2022, 6 lakhs, more than 6 lakh students have been covered. Students, faculties, and industry people have been covered to spread the awareness about like a field of invention on what are the patent filing procedures, what are the nuances involved in that patent filing procedure, all these things like. From across the 2,300 educational institutions. So this is one of the solution from the patent office side. And as far as the challenge is concerned with respect to patent drafting, I think I request the patent attorneys or the individuals to go for a good patent drafting so that, it surpasses the novelty, inventive step and the non-patentable criteria so that it makes our job easier so that you'll get the patent as well. And also, in collaboration with the business. So that is what I wanted to mention here. Thank you.
Professor Balaji.
Yeah, so lots of challenges in this. One thing I would like to recollect is when I was a much younger faculty here at IIT Madras, there was this company who had approached us and said, we'd like to, convert your ideas into IP and we'd like to, make revenue out of all of that. And the big picture, right? There was just one nice green picture that they put out. And so we fell for that. So we actually gave them our ideas and they said they are evaluating those and so on. And what we didn't realize is this company, it's a multinational company. They have presence all across the world. And they are basically taking this idea from this lab, combining with this other idea from the other lab and other idea from the other lab, and they make IP blocks. And these IP blocks are then used to go after whoever is the best in the business and that who has got the best portfolio in the business, they go after them. And mind you, these people don't do anything other than collecting ideas, right? They're not actually the ones that are actually doing the work. They just collect ideas and push them as blocks. So in sort of a predatory manner, right? This we need to avoid as far as this particular consortium is concerned. And I appreciate Mr. Himanshu mentioning that, and I would like to second that. We should actually have a person or an entity that is actually actively looking at, I was talking about before you came, Deepa, I was talking about the Science and Technology Corporation back in my graduate school days, which was actually actively looking for IP among that lab or a consortium and on a monthly basis, and they were collecting all the data and they were helping in, making the patent as well as marketing the patent, right? So we need to look at, we can start with our IP cell, but maybe we can look at some other patent attorney who can do this, who can actually get their skin in the game. So they should actually invest money in collecting all this idea so that when they actually market it, they can get their share back. That sort of a deal we should do. And that is very important. In general, the problem in India is Ma Lakshmi and Ma Saraswati, they don't go along with very well with each other. So the people that have, it's not like people don't have money to invest. They have lots and lots of money to invest, but they don't know what to invest on. So how is this problem solved in the US or Europe or any other place in Japan? Is they have a middle layer where there is somebody to do due diligence on an idea. They are basically able to say, somebody wants to invest in this area. These people say these are the people that have the ideas, and they are able to go down there and pare down all the risks. They completely do a risk assessment and they say, this is the kind of returns you can expect in this many years or this many years and so on. And these are the risks involved. So we don't have that ecosystem here of due diligence in the country, in which case people go by more of reputation rather than actually the value of the idea. And this needs to change. I don't know. I think it's beyond this panel to get into that sort of a discussion. But as we go on, as we mature as a technologically advanced country, this due diligence part is going to come in, and hopefully we'll make a better value, better marketing of all our IP.
So I think we still have a few minutes. Maybe we can have some questions from the audience.
That's right. Yes. So we touched upon it briefly, but yes, we were talking about, starting with the provisional, going into the full pattern specification from the Indian context and seeing where all it's applicable and going international as well. But do you have any specific?
Mike.
From our academic side is concerned. So do you think, is there anything that this panel can suggest to how to make that process easier? So after that, we have probably filed 6 or 7 and we said, we don't want to go there. We'll just make it Indian. And in fact, last month, we got probably with including the one with yours, there are 3 patents, Indian patents that have come through, right? Which is much easier process. So does the committee have anything panel have anything to suggest?
Yeah, so it's a very good point that, we need to be able to have a representation of our idea with these multinationals that we are dealing with. So the IP marketing is almost unheard of as far as the Indian context is concerned. We need to be smart, getting smarter about that. I think from the IIT Madras context, the IP cell has now got a marketing person. And of course, they do a good job in terms of getting onto the social media, getting the idea out and all that. But you need to be able to do that now. IIT Madras has this formula where to file a PCT, that is this international patent, the inventors actually put in 30% of whatever the patenting cost is, and 70% is borne by the institute. So before they actually get into that investment, the institute wants to know who are all the potential customers or the end users of that idea. They want the inventors to go to those end users and talk about, potentially getting some commitment from them and all that, which is beyond us. But typically that marketing person would be doing that job and making sure that we are patenting the right ideas for PCT.
Mike, can you take the mic, please?
You have been in this job for many years. Even Professor David has been with the Ericsson for a long time. So how does it happen in the industry?
I mean, just to understand your question, did you say that an international patent was tough to get and
tough to get? The process was tougher for us to go through.
Oh, okay. Okay, I think it depends on. Okay, I can only give a personal experience here. For us, it's always been how good your patent agent is, kind of thing. Okay, if he can ease it for you, it works out better. So I don't know if you have an agent with whom you are working with, and there are some really genuinely good. I mean, these agents. I mean, I'm just for the sake of the general audience, these are not brokers and things like that. Right? These are proper legal agents who have to go and do this. So usually, what happens is I think just told earlier also, over time you'll figure out who's the right person to work with you. There is a synergy on that. But I think finding that 1 or 2 agents may be the key thing. We haven't had too much difference in how effortless it was to file in India versus any of the other places. It's only the amount of money that you need to spend. And usually what happens is these agents who are here, they will have a connection with some other agent in those target countries where you want to file with. And they work, most of the preparations will be done here so that there is a constant interaction with us and them easily. And then while filing, they go and deal with different people. But of course, the cost of that is higher in the West. That's what we have found.
So I think we have.
Sir, as just with respect to the process of patenting itself, actually, we have applicant, then IPR office is involved, then we go to attorney, then to patent office. So this is the process actually, it is a time taking also. Is there any method where applicant put his application number and see what is the status of my patent, at what state it is? Because generally that communication doesn't come back to the applicant and it takes years in some cases. So is there any method by which I can put my, generally what I need to, I write to my IPR, they will send to this attorney, generally it is in progress, nothing. So I am not getting any information about my patent, what is the application status. So is there any mechanism, sir, for this thing?
No, actually, I think I can understand your question. You want to see the status of your application. I mean, after seeing the status of application, it is saying that awaiting examination or it is in the process, something like that, right?
Generally, we from IPR office, we get is in progress only. This is what further actually, because this is also tricky process. I don't know all the steps. What generally we do, we just give a write up and help with the attorney and make it a claim form and later on is a office or your IPR people take the process on. So with respect to that, actually means what I actually need to ask to the office or status in what way. Generally, what do you want? We just want whether it will be granted me or so not. This is my only interest.
No,
So
actually, the complete processing of the entire filing to patent, we are trying to reduce from 2 years to 1.5 years. So it may be a time consuming thing. I was saying you that in that period, if you are putting the status of your application, it will be saying that under examination. So there are different levels of process: filing, publication, and examination, and second examination report. Then comes your hearing, and after that, if you are submitting all your documents, then it will be granted. This is the entire process. So till it is granted, the status will be saying that it is under process or it will be under the process. And after getting the FER reply, you will be having the controller's name and the controller's email ID and the direct phone number will be given. So you can directly talk to them. If you are an applicant or inventor with respect to the patent application, then you are the concerned person for the address for service. You can talk to him directly over the phone or by email, get the status and make it as expedited. And we are doing actually each and every application based on the request for examination. Till now, as far as the technology is concerned, it depends on the technology. But as far as the chemistry and in all forms of chemistry related applications and biotechnology, the request for examination is under 2022-23. January applications, if you have filed the request for examination, it is under process. But as far as the electronics and mechanical engineering is concerned, we are looking at because of the backlog, we are looking into the request for examination under 2018 only. So which is filed in 2018. So this is the real fact. I just wanted to say that it's because of this reason you are, even if you are contacting the concerned controller, suppose I'm the controller, I'll try to say the same thing over phone or email itself. Since we are not authorized to send any kind of email communication that this particular application will be processed at the earliest or this particular application will be granted or whatever it is like. So we never know that what will happen during the hearing. So we cannot commit anything during the official communication. Only the FER or hearing notice that these two things are official communication in which you can directly contact the concerned controller and get your doubts clear. That is the only option for the as far as the applicant is concerned to get the status clear. Till then, it will be the status will be saying that it will be pending. Even if you are having a patent attorney, we'll be saying the same thing to the patent attorney, and the patent attorney will be falsifying you, saying that it is according to the requirements of the Patent Act. It will be processed accordingly. So it is as per the Patent Act.
Mr. Raj, I think let us take 2 more quick questions because the time is very less.
Yes, sir.
I will request that the questions may be very brief, and I will request the panelists to have the answers also very brief so that we can cover more questions.
Yes. So now the ideas are coming are not by a single person; they are by multiple persons. And
can you keep it?
Most of the ideas that are coming from the multiple persons are across the nations. So if we get an idea from many collaborators from other countries, how is the patent right distributed, sir?
So.
Excellent question, especially when it comes to dealing with collaborators in the UK and the US and so on. So it comes down to what the investment ratio is. If they say we can do 50-50, then it goes down to what the proceeds, whatever proceeds in terms of royalty that we're going to get finally, how that's going to be shared. That's where the contention is. So if it is actually a joint idea and it's established that it's got to be jointly assigned to two entities, one in India, one abroad, then it comes down to how much are you willing to pay. So it so happened that one of our own patents we ended up paying all of the money because the other guy said, oh, there's a lot of process involved. They're not interested in that. So now we have the patent assignment, and then we can actually market it. And I think we still have to pay a little bit of royalty to them, but it comes down to that equation. Yeah. Did I answer your question?
My query is to Mr. Raja from Patent Office. Mr. Raja, I want to ask, when a patent is filed in your application, in your office, how do you check the genuineness of that patent? Is there any procedure or any checkpoints in your system?
You mean the novelty?
Yeah.
I mean, under Section 21J, the Patent Act, we have worldwide database which is connected with all the examiners. And the examiners, they do the examination report, or before doing the examination, they do the investigation of the entire application with respect to the novelty. If the particular application of the particular technology has been published anywhere in the world, or it has been granted anywhere in the world, like it may be granted in EP or European Patent Office or any other patent office. It might have been published in any other article also, like IEEE or any other non-patent literature also. So this kind of objections, we give it to the applicant, and the applicant or inventor has to give the reply within 6 months after giving the FER reply. Then the process goes on. So, and apart from that, Section 21J, the objections with respect to patentability criteria will also be objected towards your application, and it is the responsibility of the applicant or agent to give the reply in a timely manner, and it should satisfy the requirements of the Patent Act. If it is satisfying all the criteria, after the FER reply, you may get the patent certificate immediately.
Thank you.
Sir, if I have got the patent here, if I have got the patent, how to protect my rights? For example, somebody is misusing it. He's a foreign national or someone, or any big company. How to protect myself, my rights or something?
Maybe Himanshu ji will be the best person to answer.
I mean, I think it's just what the patent has given you is a legal right to that idea, right? So now if someone infringes that, you will have to go and fight for it. So in fact, this fact itself is many times used by some larger companies to, I mean, they build a patent portfolio so that maybe the ideas are not so required, but just because you cannot face a legal, this one, they get an advantage. But I think that's the only way to go and, I mean, you got to go prove it to the legal setup in that particular country that this is yours and you need to look for it. Now, if you are a small entity and if you have to do this, maybe you can get someone to help you on a class action or some. There are, in these kind of legally savvy countries, there are lawyers who will probably help you for a, I mean, if there is something that you win and you figure out that a company has been misusing your idea, and there is some money that has to come to you, maybe a lawyer may do that pro bono in the beginning, but for some percentage of what comes back. I think each country where you have to go through has a different norm. Maybe in India, it's smarter not to fight a legal battle, if you see sometimes, right? So yeah, it just depends on how that, I think.
It depends on the value that you can get out of that battle, right? If it's some individual that's doing that, even if you know that, you let it go. I used to work for a multinational company which had about 45 lawyers, right? And all their job was to figure out who are all infringing on their patents, and they won't do anything about it, right? It's only when those guys start to get to million and above revenue, when they are really leading the market, and when they are actually being a competitor to us, that's when they bring out all these infringement cases, and then they actually get out of court settlement and they make a lot of money out of that. So it's when you actually fight that battle depends on what it's worth for.
So I
have one short question. To professors only. In the beginning, start of that, it's mostly to be addressed to the students. I'm putting myself in the student shoes. I'm asking, they want to get the degrees because the norms of the institution is they have to publish in journals. Because they are running after the time, within the stipulated time, they have to complete their PhD or MS by research. then they cannot wait for this patent, all these things. Institution, will they change the norms? They can get the PhD or MS by research without publishing, and they can wait for the patent, getting the patent. Is there any change in the norms that institution is going to adopt?
Very quick response to that. In many of our evaluations, a patent is considered like a publication. So there is a good weightage that is given. But whether the institution can change the rule to say that, you just file a patent and then you graduate, I'm not able to comment on it. That will be, it's an important topic for discussion. But at this point, an issued patent, definitely, yes, will have weightage.
So to break that down, what we talked about actually initial part of this discussion is that you file a provisional patent that gives you a priority date on the idea, and then you go ahead and publish, right? So it's not actually coming into the way of, once you file the provisional that says the idea belongs to you, then you have a year to actually convert it into a patent. And during that time, you can go ahead and publish that also. So that may ease the pressure on the student.
I think we can take one last question from.
My question is continuous to previous question to patent Raja sir. DDG TEC once told that he is finding difficult to search the patents. And other hand, you have told that you have connected to the database of the whole world, and your examiner is searching the patents when giving the patent. How that is happening? I mean, how that search is happening?
So I am just clarifying that we are facing difficulty in looking at the databases, 3 different databases, India patent, US patent, WIPO, and then figure out which one is related to 6G or which one is related to advanced 5G. So that broad categorization. So for that, it would be very easy for us if there is some attribute and we simply click on that filter and get those patents. But what he is saying is that they are searching for that particular idea. So they have to go into the details only.
Actually, I understand that he is asking how the work has been done. Right.
Yes, sir.
So you have how we are searching, like that is a work of the job responsibility of the examiner. Like, and I hope you might be knowing that we have published some recruitment notification for from something around 553 examiners to be recruited soon. And I think if you have any probability, like after writing the examination, you can very well admit, I mean, you can come and join the office and you can come to know it. But still, anybody else, basic degrees, engineering, or I mean, in all fields of engineering, on fields, biochemistry, chemistry, or all the fields, they are asking all the fields. Like, so some 553 people are going to be recruited soon in September or November. Like, so it is going to be completed. But the process of investigation, the entire database, we actually have a connection with all the databases like European database, Japanese, Korean, with all the translations. Like, so if the examiner has been trying to look into the complete study of the complete specification, and he understands what exactly is claimed, with the claim portion, he is generating his own, not his own, based on the claims, he is generating the keywords or relevant keywords. With respect to the keywords, he is putting all the things in the database and get the relevant patents or the closest prior art. So it is like you are asking about the prior art searching, which is very much essential for an inventor or a patent attorney to be carry out, to give to draft a complete specification. So that work we are doing it meticulously, and after that the second level of checking has been done by the controllers or assistant controllers and deputy controllers. And based on that, it will be, I mean, if the controller is not satisfied with the search criteria, it will be referred back to the examiner and it will be discussed one-to-one. Sometimes if he is there in the same location. And after that, we come to a conclusion that this is a consolidated FER, first examination report. So after that, only we are sending the first examination report with all references to the documents, which is closer to that complete specification or closer to that particular technology.
Thank you.
I think we are now encroaching upon the lunch time. So more questions can be taken during the lunch. And this was a very interesting and discussion and a learning experience also. And in fact, I hope the audience would have got lots of inputs about how to file a patent, when to file a patent, and the importance of filing a patent. And I would like to thank all the esteemed experts and panelists here for their time and inputs. Thank you.
Thank you. May I now request the session chair? Thank you. May I now request the session chair to please hand over the token of appreciation to the panelists. I now invite Ms. Deepika Ambani from CDO to honor our session chair. Thank you all. Now it is time to enjoy your lunch. We have made the arrangements for the same in D6, one floor below this floor. Please be back by 2:20. And a special announcement for the participants who have not received the registration bag during the registration can please approach the registration desk during the lunchtime. Thank you.
Thank you very much. We have a limited audience. I think people are still at lunch. We may want to wait a couple more minutes before we start officially. I'll take the opportunity in the meantime to introduce our speakers. This session is on quantum key distribution, and as we were just discussing, it's a little bit of an anomaly in this workshop because in this workshop, everyone's trying to push higher key rates, higher data rates and lower cost. And if you look at quantum communication, we are at the other extreme with a very low data rate and a very high cost. However, security is something that is on everybody's mind, and quantum communications has these advantages of being able to provide us with very secure communications. We have with us in this session two speakers. We have Anandaraman Sankaran, who is a senior manager from Toshiba, Toshiba Asia Pacific. And actually, I'm very glad to have him here because Toshiba has been at the forefront of demonstrations of quantum key distribution. In fact, they are probably the only company today that has sort of a packaged solution in a reasonably small form factor that works as high as 10 megabits per second, if I'm not mistaken. Anyway, Anand Raman is going to tell you more about that. Anand Raman completed he's currently a senior manager at Toshiba and promotes the quantum key distribution technology in the APAC region. Prior to that, he was a manager at NXP Semiconductors, where he was doing near field communications. So he has a master's degree in embedded systems from Nanyang Technology University, and he evangelizes a lot on quantum key distribution. So without further ado, Anand Raman, please take stage. Yeah, I think you have a portable mic, right? Then you'll have to stand here, but if you want to move around, then you use this.
So I think I'm fine.
You're fine with this?
Yeah.
Go ahead and use this.
Yeah.
Fine. Yeah. I can't be there, then I can't see anything.
Yeah, thank you, Prof. Anil, for your kind introduction. Firstly, I would like to thank Department of Telecommunications and IIT Madras for inviting me for this conference, as well as providing hospitality for me for the past 2 days. It was a very good conference for me. Next, I would like to congratulate all of you here who can make a timely after your heavy lunch. Thanks for coming to this session. I'm going to tell you about the recent developments and activities around building large-scale quantum secured networks. Recently, we see an evolution of quantum communication technologies. Until relatively recently, there are so many implementations about point-to-point QKD links all over the world, which are primarily used to demonstrate very basic use cases such as data center interconnect as well as offline site backup. But now there is a new trend of developing quantum secured network. The definition of a quantum secured network is nothing but a classical traditional telecom network secured by quantum safe cryptography. When I say quantum safe cryptography, it includes both quantum key distribution and post-quantum cryptography. So these quantum secured communication networks are used for a variety of use cases. So now the telecom operators are developing quantum secured communications as a service to the financial, healthcare, government, and critical infrastructure sectors. What we envision after quantum secured network will be a quantum internet, which is basically a collection of quantum networks, not just providing a quantum secure communication, but as well as allowing distributed quantum computing and quantum sensing as an example. To introduce about Toshiba, so Toshiba has been having several years of contributions to quantum communications development. For example, we have demonstrated QKD over 100 kilometer in 2003, and now we have up to more than 600 kilometer or a fiber using a novel protocol called the thin field QKD protocol, which I will delve into later. Also, we made a demonstration about high secure key rate of more than 1 Mbps into around 2006 and extended to around 10 Mbps. So Toshiba is one of the leading company in the world who has such a high key rate and long distance communications offering. Apart from that, we have also done a lot of work on how we integrate the quantum communication technology into the classical telecommunication infrastructure rather than developing or overhauling your existing telecom infrastructure. So from that research perspective, we delve into concepts such as point to single point to multi-point, such as quantum access network, as well as how you can have quantum signals and the classical signals co-propagate on a same fiber, for example, using a wavelength division multiplexing. So Toshiba has worked on such aspects and developed products based on considering how to integrate quantum communication technologies into the classical communication systems. Not just from a technology development or a lab environment. Whenever there is some new research milestone happen, it has been validated in several testbeds all over the world. For example, in the very first European Open QKD initiatives, Toshiba has participated in a lot of countries' QKD testbeds where we developed use cases, which I will share later. So having all these researchers and all the test bed validations, in the year of 2020, Toshiba decided to commercialize the quantum key distribution technology so that they set up the quantum cryptography business in 2020, and they have launched commercial QKD products. And these products are now deployed in London Quantum Secured Metro Network, which is built in collaboration with BT and Toshiba, which I will share with later. So when it comes to Toshiba's commercial QKD offering, so we offer QKD systems as a starting point, where we have two product varieties. One is the long distance QKD system, and another one is the multiplex QKD systems. So since many of you here are from a technical community, so long distance system uses the 1550 nanometer channel, whereas the multiplexing uses the 1310 O-band channel. About the key rate, at 10 dB loss, our specification is 300 kilobits per second, but typically we can able to achieve 800 kilobits per second. And coming to what is important when it comes to the product specification or the performance is about the fiber loss. How much the QKD system is tolerant so that it can able to generate stable key rates, right? High secure key rates, right? So Toshiba has a specification of up to 30 dB channel loss, which is translate, if you translate the decibel to a distance, it will be about 150 kilometers as of today, right? So you can really achieve quantum key distribution over 150 kilometers from the long distance communication systems. Of course, long distance communication systems works on the C band, so you require 2 fiber. And as of today, Toshiba's QKD products are based on BB84, modified BB84 protocol. When it comes to multiplexing systems, we do have requirements where when it comes to cost, a concern where you don't want to lay expensive fiber to do the quantum key distribution, where you can use the multiplexing product from Toshiba, where you can where the quantum signals and your classical data communication can coexist in a fiber that can bring down the total cost of installation. So to talk about the performance of the multiplexing systems, so I would like to bring the recent research that Toshiba has done with the Orange innovation in France. So we have collaborated with Orange to do this technology validation of Toshiba multiplex QKD systems. So in that trial, so Orange Innovation Lab has 60 channel DWDM, which each of those channels carrying 100 gig test data traffic, which in total account to 6 terabits per second. And these 60 channels coexist with the quantum channels from the Toshiba QKD system. And at a 50-kilometer distance, this multiplexing system can able to generate a key rate of 100 kilobits per second, which can translate into, for example, 100 AES keys per second. Right, which you can use it for your upper application to secure your infrastructure. So based on this multiplexing trial, right, both Toshiba and Orange came up with a conclusion about a topic called co-propagation efficiency. So what is a factor that affects when you have multiple DWDM channels carrying with quantum signals, how the key rate is affected, right? So we come up with a metric that the performance of the system depends on two main factors. One factor is your length, the fiber length, and another factor is about the optical launch power of the each channel, data channel that carrying, as well as the total launch power of that channels used, right? So using these metrics, or these three metrics, we can able to determine what will be the key rate that we will be able to achieve from the QKD system. So that was the outcome we had from that evaluation. So this actually sets a real hope for all the telecom operators that you can really you don't need to overhaul your existing telecom infrastructure to implement, for example, a quantum network or quantum secure network or even quantum internet, right? So this really sets an example where you can both quantum and classical world can coexist on the same fiber, which brings down the total cost of maintaining the infrastructure. And as you can see from the graph that we have provided the key rates for 30 channels, 60 channels, and without any multiplexing. So the systems has been able to deliver very stable key rates, as well as the performance about 30 versus 60 channels still relatively the same. So we understand that providing just a QKD box is not going to enable operators to offer any kind of service to the end users, right? So because you need to build a network, you can't just supply a point-to-point box. So we understand that, and the team has developed a key management layer or a network key delivery layer on top of the QKD system, understanding the software-defined networking and closely working with the telco operators like British Telecom, understanding the latest software-defined architectures of how the current classical communication infrastructure is developed, having in that mind the key management system or the network key delivery layer Toshiba is developing and deploying in the UK metro network, right? And basically the key management system or the network key delivery layer is responsible to provide quantum keys or the quantum cryptographic keys to the upper layer, which is your DWDM equipment or your Ethernet equipment or your firewall equipment. So any layer of your internet technologies can retrieve the keys from the Toshiba key management system layer and can develop secure solutions at multiple layer of OSI. I thought it will be good to share with you what's happening globally around QKD deployments. So I have made this map to share with you what's happening in global when it comes to quantum key distribution. This map covers only the Toshiba implementation. Of course, there are other people in the market which has done a lot of demonstrations. So I start from when I take care of the regional Asia Pacific business development. I do see that the interest and the development from the telco operators in the East, which is the Asian countries, is much more than what is in the US or what is even in the Europe, right? So really the Korea, China, and Japan, they are leading in developing a quantum secure network. So in Korea, we have demonstrated a very long distance, about 500 kilometers between two cities, Seoul and Dijon. So we set up a long distance communication system, and we demonstrated interoperability with the local Korean manufacturers. So the objective is to demonstrate interoperability, high quality of service. Those are the objectives of those test bed where we collaborated with the Korean Telecom. And the next one is the Tokyo QKD Metro Network. That project is run by the NICT of Japan, which is the National Information Communication Technology Government Agency. So they're in a project which I will share later. So where Toshiba is deeply involved in building that quantum secure network. And when you go to Singapore, we have a business collaboration with a company called Spectral, which is a spin-off from Center for Quantum Computing, National University of Singapore. They are specialized in developing satellite QKD solutions. So we have a complementary synergy between Spectral and Toshiba, because Toshiba is specialized in fiber QKD and Spectral is specialized in satellite QKD. So together we envision to have a global quantum secure communication network, as well as Spectral position themselves as a quantum communication service provider in the region, which are envisioning to develop quantum communication services in Singapore. When it comes to UK, when it comes to Europe, we actively participate in the open QKD projects in 6 countries, with Germany with Deutsche Telekom, France with Orange, and Spain with Telefonica, and other small Baltic countries where we have worked with the local telco operators to develop use cases. In the US, the adoption is quite slow compared to the other regions, mainly because of the NIST waiting to strongly recommending or focusing on post-quantum cryptography. But the situation is changing when the Department of Energy and Chicago University set up a Chicago Quantum Exchange, which focus on quantum key distribution as well as quantum internet technologies. So it's a research testbed project by Chicago Quantum Exchange, where multi-industries can come and deploy their systems for the university researchers and the academics to learn and also research topics such as quantum memories and repeaters, right? So that's where we deployed a system for those university people to see how to deploy those systems. And main importantly, for any technologies, you need an application, right? Without an application, without a killer application, it's not going to be successful. So from that perspective, we are mainly focused on government and financial sectors. So we have been closely collaborating with the JP Morgan Chase since 2021, and we have made a first validation, applied research of how to enhance the blockchain security, because the fundamental of blockchain technology is cryptography. So where due to the quantum computing threat, right, the blockchain technology need to adapt new quantum safe techniques. So that's where we have done a validation with JP Morgan Chase together with Sienna, which I will share also later. So those are our some of the active activities in the world about QKD. I hope this information helps you to see and go later and find on each of the projects what they did and what you can do it for the Indian ecosystem. To delve into the detail of what is quantum secured network in terms of large scale. So we built this commercial trial since 2022. The objective of this commercial trial is to provide high bandwidth data services protected using QKD for customer carrying data traffic, right? Until now, we have Ernst & Young and HSBC as the first trial customers who on board into this quantum secure network, where they are developing several use cases such as a data center interconnect, as well as edge to data center connectivity, securing those transactions, as well as some secure video communications. So there are few use cases that each companies are trialing with the infrastructure or the QKD service provided by BT. So what's so unique about this quantum secured network is this network is hosted in an operational environment. It's not a laboratory project. All the equipments, software, everything used is a telecom approved product, not a prototype. It uses the BT core nodes or core exchanges for building the core networks, and access trails are used using the BT OpenReach Spectrum product. What it means is that the customers can go and buy the normal fiber that they buy for their data carrying. Now they can use that BT OpenReach fiber that they get for data carrying services to get the QKD quantum key distribution as a service, right? It uses, the network uses the QKD and the KMS, also the quantum network control software from Toshiba, and the encryption technology, because quantum key distribution is just providing you the key. It is not providing you an encryption. So you still need an encryption algorithm, where encryption is done at the optical layer using ADWA platforms, right? The BT's network management operations are also integrated into this QKD platform. And another example of quantum secure networks, the first example is driven by telco operator and industry, but this is something very different. This is driven by the ministry, which is the National Institute of Information and Communications. The objective of the Tokyo QKD Metro network is to build a test bed for users to show practical applications of quantum secure cloud. So how they define quantum secure cloud is a combination of quantum computers and high performance computers, QKD systems, which are interacting with each other in either in the research lab or the innovation parks, such as like IITM Research Park. So those research laboratories in multi-industries, being it industrial or financial, as well as government agencies. So they have selected several of those partners to involve into this project, and they build this network. The project is run by the government with the components and the systems from different vendors, which is currently in the phase of development. So once it's operational, we will have more information about who are the users and what are the test beds. Another thing that is close to India is the Singapore National Quantum Safe Network. This Singapore National Quantum Safe Network is hosted by National University of Singapore. It is also a testbed project, but it has a whole of industry collaborations as listed here. They all bring in their equipments and expertise. The main agenda is to develop a pilot infrastructure so that the local enterprises can understand what is quantum key distribution and develop quantum solutions out of it. And the scope of the NQSN also involves security framework and ecosystem development, developing local ecosystem to commercialize the quantum communication technology, as well as local standardization. What is the standard needed for Singapore? So those are the 4 topics that this project is focused on. And yeah, they have several use cases and a milestone already achieved, which you can refer from their website. Some application examples, as I said, that the point-to-point links, I think a lot of people has demonstrated, so I don't need to go into detail. So in Singapore, we have set up a 55-kilometer link between two data centers, and we demonstrated the data and quantum signals coexisting on the same fiber, as well as doing the encryption using the Ethernet encryptors from a homegrown company, ST Engineering. We did the financial use case, blockchain transactions with JP Morgan, Sienna, and Toshiba, where 2.4 Tbps of data channels, 2.4 terabytes of data, or can coexist with quantum signals, and 100 gig of data are secured using the keys generated by QKD system. Also, we have an industrial use case. So QKD can be used in industrial, such as National Composite Center and CFMS from PT. This is a groundbreaking project for translating it into a quantum secure network, because with this project, Toshiba was able to understand how the real telecom network looks like, so that they can customize the product to fit into the telecommunication infrastructure. Our recent R&D includes the twin-field QKD protocol. It is a kind of a mini quantum repeater. We have done a research prototype, but not yet commercialized, which can help you to bring really intercontinental QKD links. Of course, most of the day one of this conference was talking about integrated photonics. Yes, definitely we need the integrated photonics to adapt access networks for the QKD. So this will also enable mass manufacturing of quantum networks. So as a final note, yeah, quantum communication is a very big topic. It requires optics, electronics, mechanical, as well as the softwares, mainly the software industry, to come together to develop such a quantum secure network. It's a very interesting decade it's going to be when really we see a quantum computer and we pave the way for the future quantum internet. Today, we have the technologies for building a metro-wide, large-scale metro networks. For a city, we can able to build the quantum secure networks with our systems. We are working on the twin-field QKD to go intercontinental links, or even links between Chennai and Delhi. And then definitely, in order to have a real true global quantum communications, of course, you need the satellite QKD to be in place, which we see in 5 years, we'll be able to have some players developing satellite QKD. Yeah, that's all from my side. So please do follow the Toshiba Quantum Technology page in LinkedIn, so that you can get latest update on the updates from Toshiba. Thank you.
No, there. Thank you, Anandaraman. That was very helpful. It is good to see the kind of work that Toshiba is doing, and it's fairly encouraging that there is a commercial venture in all these countries that is doing this, right? We have time for a few questions. Have any questions for the speaker?
Thank you for the very nice talk. So as a critic of QKD, I have a question. So we can use the classical encryption algorithm, right? So the problem is, until quantum computers are developed, we are safe, more or less. So QKD is also vulnerable to many classical attacks, such as man-in-the-middle attacks. So how do you defend QKD in those perspectives?
Yeah, okay.
Thank you.
So coming to your first point about, quantum, we don't know when the quantum computers will arrive. So why do I need to adapt such a solution? So what you have seen is that the traditional cryptographic technologies that are invented are 20-25 years old, which have never foreseen the power of supercomputers, even high performance computers that you can see. So those are based on a hard mathematical computation problems, which in future you can able to break even with a high performance computer. You don't know, right? So, and what you have a threat is that though there is so much investments going into quantum computing, as you see that over the past 3 years, all the hyperscalers has get into developing quantum computer technologies, right? We don't know who will win, who will be the first one to develop such a error-free quantum computer, but the threat is real, right? It is like the encryption systems are very hard to change. In order to change from an AES 128-bit to an AES 256-bit system, it may take 5 years for some companies, it may take 10 years for some other companies. So already the today's data, confidential data, which need to be kept for 10 or 15 years are already under threat, because these mathematical problems can be solved in a 10 to 15 year time. So that's why you need a new way of encryption technologies, right? That's where quantum key distribution offers a solution. Of course, post-quantum cryptography, or there are many other ways to solve the problem, right? And each technology have their own pros and cons, right? But when you compare about the maturity of each of the technologies and vulnerability, QKD has a significant upside than other technologies that you have. I don't deny the part that QKD security analysis on QKD need to be done. It is still a very nascent stage, but since you can find one security flaws, you can't stop it, right? There are always solutions for it, right? You have to push the technology adoption rather than doing a break, right? Because as I say, the evolution, you are getting into a phase where you are seeing a quantum internet, right? So which means this technology has a much more business potential. So we must adapt rather than looking at the topics that may not be so important as of today. Yeah, thank you.
Thank you for that.
Sir,
That was a reasonably longish answer. You have another question?
Yeah. Sir, as you told that you have done this long distance QKD QS assessment. So for this assessment, apart from security, do you consider some other communication QS parameter for the assessment or analyze some other parameter?
So
I think, I think they do use secure key rate. I think in one of his plots he had
exactly
secure
So
key rate as
for the communication, security is one part actually. Okay, there are multiple QS parameters. Like we can ultimately our purpose of communication, how fast we can send data and how far we can send. Generally, telecommunication is meant for that. Security is one aspect that we can send this securely or not. So in that aspect, with respect to enhance the throughput or the range, is there any mechanism this quantum communication can help apart from security? This is what just I want to know.
Okay, so one application of quantum communication is quantum key distribution, where you can able to generate secure keys for doing encryption. That's one aspect, but it's premature to talk about other applications such as improving the throughput of your quantum signals. Of course, the multiplexing performance shows that we can able to generate high key rate, which means we are able to provide improve the throughput of the quantum channel, right? We are not just considering the security aspect, we are also considering the throughput, and not just security aspect, as well as how it should not affect the data channels, right? The classical communication, because when you add a quantum channel and a classical channel, of course, there is an interference and you have a Raman scattering effect, right? So you have to make sure that you can able to provide right amount of key rate that is required to secure secure the network, as well as it doesn't affect the latency of your communication, right? You use the keys to protect that communication. The latency should not be affected for the existing communication. If the latency is affected, nobody is going to adopt this technology. So multiple aspects has been considered.
Thank you very much. Are there any other questions? Maybe one last brief one. If not, I would like to.
Do channel impairments affect QKD on wireless networks?
Sorry, can you repeat that question? It's not
Do channel impairments affect the QKD distribution on the wireless networks?
On wireless networks. We do QKD
for wireless networks, it's a free space optics, right? Which I don't cover in this presentation, because it's my main focus is on the fiber, mostly on the fiber optics. Of course, there has been research, a lot of research on free space QKD, but that there will be a market for free space QKD, which is very niche, which may be between buildings or inside the data centers, or even within a data center rack, where you have the companies sharing the data center rack, where you can apply the free space QKD technology.
Satellite communication will be without a wire, na? How it will be done?
How do you do satellite communication? I mean, do you have a channel problem with satellite communication?
Okay, we can talk about it a lot, but the focus of this presentation doesn't cover satellite. We are mainly focusing on fiber QKD.
Thank you. Then maybe we take the discussion off.
Yeah, definitely. I can help you answer that. Yeah.
Let's thank the speaker again. Thank you, Anandaraman, once again. And I'd now like to introduce our next speaker, Amit Srivastava. I've known Amit for ever since we started doing quantum. I think I saw him first when he was in Hyderabad at CARE, and he and I cut our teeth around the same time about 6-7 years ago now. Yeah, starting these quantum communication projects. Amit has a master's degree in computer science and engineering from IIT Delhi and a bachelor's degree in computer science from Jhansi. But more importantly, he's quite well known in the DRDO circles and outside in the quantum communication field. He was instrumental in some of the demonstrations that were done through DRDO with IIT Delhi, I think 100-kilometer link. He'll probably tell us more about that. He's also the recipient of awards for the National Science Day and the Innovation Awards from NVIDIA, because he cut his teeth doing GPU and image processing. So he's taken a turn towards the quantum domain, and we look forward to hearing more from him. Thank you, Amit.
Yeah, thank you, Anil, for kind introduction. Is the quantum key distribution implementation challenges and way forward. So I would be covering my talk under following subheadings, as earlier mentioned by the session chair, that the topic is not well mixed with the theme of this workshop, which is advanced optical communication. So there might be some audience who are not from the quantum domain, and as we know that this is not using a quantum is not incremental change, it's totally paradigm shift. Okay, so how do you compare the quantum communication with classical? I think what has been discussed yesterday and today. And then some of the experiments we did at DRDO. And the next I would cover the implementation challenges and the solution, and the conclusion. So, okay, so in very abstract terms, if we see the classical communication, so we have some source, some message which has to be sent, and then we have a transmitter, and we have a carrier waves, and then we do the modulations and generate the signals which is sent on the channel, which is a physical channels, and then we receive and get the message. Okay, so there may be a noise, so we get some different message, and then anyway it is get corrected. Okay, so how do we compare the quantum communication with this classical schematic here? Okay, so unlike this here, we have same message has to be transmitted, but here we use a quantum encoder. Okay, and then we get the quantum state. Okay, so this is maybe a 2-state or 3-state. It is presented as a vector in a Hilbert space, which may be infinite dimension, and which is represented by a rho A in a pure state. And then this quantum state is sent on this physical channel. So mostly at present, we are using photonics or optical communication. So because like we call it the flying qubits. Okay, it can be done otherwise also, but mostly it is done using the optics photonics. So we have either free fiber or free space. And then when we receive it here, okay, we get a different mixed state. Okay, so this state we can represent in a Bloch sphere. And due to the channel noise and the presence of the Eve, okay, the state may not be at the surface of the Bloch sphere, it can be inside. So it is a mixed state. And then we do the measurements. So even the measurement also is entirely different than how we do the the measurement in classically. So doing it measurement here, we need to select the basis. Okay, that is different than the way we do in classical things. So how mostly we do the measurements may be most general, like positive operative measurements, or it may be only projective. So in that your basis may not be required to be orthogonal, but if you do a projective, like the both bases need to be orthogonal. So mostly we do a z-axis basis that becomes only just reading the arrival of the photon. Okay, if you want to do x-axis basis, you can measure the phase, because in the Bloch sphere, if you see, like the Z are the eigenstate of the Pauli matrices, and if you do like Hadamard basis X, this is a phase. Okay, so if you want to do phase, then you have to change into X basis, and then you can do the phase measurements. Okay, so both are possibilities are there. So how the security is done here, when we encode the message into this quantum state. Okay, so we are encoding in some basis. That information, we are doing a split of the information. When we are sending quantum, qubits, quantum state, we are not telling in which basis it's prepared. Okay, and unless and until you know those bases, and these bases are non-orthogonal. So even if you try to read, there would be like 50% possibility into collapse into any other basis also. So this is how the things are done. And as we know that Richard Feynman has told that there's a lot of space if you go bottom. Okay, so we are going like at atomic and subatomic level and creating quantum state. So it is, security is only one aspect of it. There are a lot of many possibilities. I'll try to cover some of them. Okay, so yeah, this is like answer why, what we all get, what's the motivation for doing all quantum communication. So the first is like definitely comes to the mind that it provides the novel way of doing the secure communication, and like which can expose the unbounded eavesdropping. So we assume in quantum communication that Eve is the most powerful. He is like, he has all the capability, except he has to follow the quantum mechanics principles. Okay, and then whatever security we are getting, unlike the classical things, we can verify, and we have information theoretic security proof. Coming to the next one, this thing, as we know that even the quantum random number generators also is very important. As we know in defense, like even in the communication and otherwise also, if your entropy is not good, okay, so if it leaks some information, then the adversaries may know a lot of details. Okay, so wherever random sources are required, you have to have a very good entropy. Okay, so all the classical true random source which are believed to be random, okay, but there is no proof. Okay, so unlike that, we have a more in this case of quantum, even we have a proof that whatever we are generating, it is a quantum. It is a pure random number using quantum principles. Okay, and then some of the more applications are like it provides the correlation. Yeah, so if we have a like entangled qubits, which provides the stronger correlation than the classical. Okay, so this gives rise to many more applications. Some of them are like quantum radars. So what we do, we create a quantum entangled pair, and then we convert into some microwave or radio frequency and send it, and then it hits the obstacle and come back, and then we correlate. So using this correlation provides higher information than anything possible classically. Okay, so it is believed that even it can provide like the obstacle of what material it was made of. Okay, so this gives to like many more applications, and even we can do the quantum imaging. Okay, if we, so like quantum imaging is like you creating two entangled, and you like take one photon in at your place and send another, and then you correlate. Okay, so you are doing the imaging by like with the photon which is not sent to the target. Okay, so this is another possibilities of doing quantum imaging, and this at the end, and the quantum communication helps in interconnecting all other quantum verticals. So as we know that a lot of work is being done in the quantum sensors, quantum computers. So at the end, we will have a like suppose we have a quantum clocks, okay, which is very much more accurate than the atomic clock. So if we connect this using quantum communication, like directly quantum state we can transfer, okay, and then we can have a like very accurate clock distribution. Okay, that has got many applications, and also the distributed quantum computing. So like you generate a qubit, you have at the one place in quantum computers, you transfer using quantum communication. So you can do a distributed quantum computing. So these are some of the more applications apart from the security. Okay, so coming to the like how we do it. So as I mentioned in the first slide, that we need to create a quantum state. So what are the ways to create a quantum state? So there are many, but primarily I have listed the three. So the first is a single photon state, which is called a all-Fock state here. And the second one is a coherent the squeeze state, like the Gaussian state, and then cat or GKP states. Okay, so this is mainly used for distributed quantum key distribution, and we use a coherent Gaussian state for doing a continuous variable quantum key distribution. So here we have a different degree of freedoms. So like we can encode the information in polarization, phase, and orbital angular momentum, and others. Okay, and here the encoding is done in quadrature amplitude, and this is a hybrid of these two. So as we see, we can see the channel, what effects it has. So here, like here the power is very less. So like the quantum state get erased, and the measurement is done using the single photon counters. Like this here, it is done, and like this is more like aligned with the classical thing. So we use a homodyne and heterodyne detection. So both has got some advantage and disadvantage. In the first one, in the single photon state, the security proof is like well proven and well established. Unlike that here, it's not well established. And here we can get a higher key rate, but limited range. Okay. Okay, so the next question comes, how to like, what are the ways to generate a single photons? So there are two methods, probabilistic single photon source generation and deterministic. Okay, so I think the most famous under the probabilistic single photon is a spontaneous parametric down conversion. Then we have other like four-way mixing, spontaneous emission, and attenuated coherent light source. Under the deterministic single photon source, we have quantum dots and V-centers, quantum interferences. And what we need to like take care if you are doing the QKD, what property these single photon generators should have. Like we need a high efficient and at high repetition rate. So if we are able to generate more and more, okay, and then we are able to send onto the channel, we have the more chances to get a higher key rate. Okay, and then the purity also is required, higher priority. And these all should be indistinguishable. Okay, because if they are not indistinguishable, this gives some information to the Eve to get some he may get like some other degree of freedom, some information is there, and that may be a positive plus point to the Eve to get some information. Okay, and then it should be of narrow bandwidth, and some other properties are like anti-bunching and all, so it should be equally placed. So next I will just present here what all experimental work we have done at DRDO. So before that, I'll just like to play this video here, which shows how easy it is to capture the optical communication. So here I have just placed a beam splitter here, and this is Alice and Bob. I'm doing video streaming by just putting this 1,000 almost it is 1,000 rupees beam splitter, fiber based, and then you can entirely decrypt. You can get the not decrypt, but you can get the entire video. And if you have the weak encryption, even that also can be deciphered using some of the methods. So though here we have cut the fiber and kept the beam splitter, but there are some devices in which this is called a fiber clip-on coupler. So this just bend the fiber, okay, and some energy comes, and you can read the entire data what is being communicated. So it is very easy to intercept the fiber channel. Yeah, so coming to the next, I think this question always comes, QKD work versus the PQC. So in which way to go? And there are some advantage and disadvantage with both the techniques. So here, if you see this diagram, if really we want to have a top security, information theoretic security, which can be provided only by QKD, okay, not by the PQC. So it is believed that all computational security comes with the expiry date. So whatever classically computational security is there, down the line it would be broken. So I think there's a famous this thing that Enigma, when German invented, it was believed that it never would be broken, but within a few years, that Alan Turing has broken it, and then it is believed that the World War II was ended a few months before because of he was able to identify the places of the armies of German. So it is very critical. So whatever secret information, if you want to exchange, I think you should go for the QKD, but both are complementary. So there are some of the shortfalls in QKD, it needs an authenticated channel. Okay, so for that, I think we can use a PQC. So we say that PQC and QKD works together for the final objective. Yeah, so coming to the single photon source. So this is the first we try to generate an entangled pair, because those are the ideal source which provide the secure communication. So here we did a SPDC, spontaneous parametric down conversion. Why it is spontaneous? Because it is a probabilistic. We do not know. So we have a laser source here, and we have a nonlinear crystal. So this may be a type 0, type 1, type 2. And when we pump this here, the laser, it's down converts. And when we get these two, this is the singular and idler. Okay. So if it is a type 1, we need to do the phase matching here. And so using these two photons becomes entangled if it is a type 2. So they get this two rings here. So if you put a detector here, this may be either from this cone on this cone. So it may be we get this state, HV and VH. Okay. So when you read, either you will get V or H. So we did this is our lab, some experiments to generate SPDC entangled pair source. And some of the characteristics, as I mentioned, was second correlation. So the G2 is for 1 for coherent, and we need to, if we are really doing quantum, we need to prove that it is less than 1. So we did, this is called a coincidence count. So we take this signal and idler, and then we plot on like delta t, and then if we get a peak, means we are getting both signal and idler together. Yeah, so next was after generating this like entangled pair, next to do was that some QKD. So here we have done like BPM 92 kind of scenarios. So here this is again entangled generated source, and then we have 2 PBS polarizing beam splitter, and then the 4 detectors. So and then we get a like HV and VH state, and depending upon the polarization, either it gets this detector or this detector, and then the key is generated. Okay, so as in this scheme, the SPDC, the main issue is we cannot like get the high repetition rate. So the maximum speed was around 100 kilohertz, but to do some 100 kilometer on, that was the target giving to us. So that was not sufficient. So though we have some academic collaboration to generate the better single photon source. So the first one is with IIT Delhi to generate a hybrid photon source. So in which we are trying to generate a hybrid qubit with polarization and orbital angular momentum. So another advantage with orbital angular momentum is this is independent of the orientation. So what happens when you send the polarized light? So suppose if it is a horizontal, so at the receiver also the axis has to be aligned. If axis is not aligned, then there's a mismatch, and you cannot, you will not get the proper results. Okay, so the orbital angular momentum is independent of this alignment. So that was the advantage. And another is also with IIT Delhi, in which we are trying an on-chip single photon source using lithium niobate on insulator. So in this, what we are targeting is like on-chip single photon source, which can generate both single photon and entangled photon. And we are targeting both wavelengths. And here the repetition rate is higher, around 10 megahertz, and G2G is less than like it is 0.05. So this would be a very good source. And other than this, we have this is again same as SPDC. And the last one is with IIT Hyderabad, in which we are using perovskite of material and using quantum dots to generate a quantum state. Yeah, so then actually the target was given to do 100 kilometers. So we used weak coherent pulses, and we implemented the 2 scheme the DPS and coherent one way. So these are the some of the details presented here. And this is a pictorial representation of what was our setup. So we have a laser source, and then an intensity modulator and phase modulator. This is like routinely how it is done. And so this is some of the trials we did. So the first one was did 10 kilometers between RC and DRDL at Hyderabad. Then we could get a BSNL link between Sarurnagar and Nalgonda, but that link was quite noisy. So we could get a better link. This was from RailTel, Prayagraj and Vindhyachal. So then this that was the third field testing we did. So these are some of the results. And I think these are some more results. And some of the things like we encountered where the stability was very important. So we were sending with different fibers. So this was our clock, and this was the signal. So then we came to know during field trials that there is always a drift, and then we need to correct the drift, otherwise your Q will get shifted. So also we have done a software simulation, and then we have matched our experimental data with the simulation. So these are some of the, I think, lessons learned. So I'm skipping, I think, because of short of the time. And as I know that the each QKD, the security proof, you assumes that you have a pure true random number. So in this direction, we have done some work for developing a quantum random number generators. This work is mainly done at the DYSL-QT Pune. So this was first laboratory setup, then we could have a box kind of setup here. And the next way forward is to generate if you use using the entangled, we can do the self-test. That is not possible classically. So the classically is a sufficient but not necessary condition even if you pass all statistical tests. So if you really want to prove, then you need to go for something like that entangled pair source and prove the Bell inequality. So I think some of the limitations and solutions are like at present the range is very limited here. So the solution is to try some different protocols and like integrate with, if you want some pan-India kind of network, we will have to integrate with fiber and free space. We have a low key rate. So we have to try some new protocols and then multiplex and have a redundancy. And the practical solution is also one of the major concern. I think that was also asked, that there is a some side channel attacks are there. So one approach is to like implement all countermeasures, but that is again very cumbersome. So the solution is go for the device independent protocols. Okay, so I think as we always discussed that there is always fight between hackers and developers. So is there is any end? So I think device independence provides that it can end the fight between the developer and attackers. So the next is a cost. So I think if we have an on-chip and then we can have a volume, then the cost will be reduced and deployment. Okay, so this is, I think, some more details in each of the challenge. So like how we can take care of the key rate. So like if we see the plain weak coherent pulses, the secure key rate is the T squared, that T is a transmittivity of the channel. And there are some like train field protocols in which it is a square root of T. Okay, so there are some ways to like go for the higher and higher key rate. And another option is go for the hybrid. So we have a different degree of freedom. So even if we like encode one bit in different degree of freedom, we can, with single qubit, we can send multiple bits. So as I think these are some of the assumptions. So each assumptions give some scope for the attacker. So these all have to be, countermeasures have to be invented. There is some software solutions also using this GLLP security analysis, in which we use only privacy amplifications and cut down these some of the open loopholes. So coming to the next, I think this is MDI QKD, in which we do a 2 photon interferences, and like 2 photons get projected onto the Bell state, and then we like nullifying the security loops hole at the detector. And if we come to the twin field, the 2 photon interference will become the single photon interference, and it using this principles, even the vacuum states contributes in the generation of the key. So using this, we get the higher key rate. So I'm not going into the details. I'll just briefly satellite QKD. So yeah, so I think I'll just skip. This is some feasibility study we have done. And recently DRDO has also published the 4 expression of interest because we have a limited manpower. So if anybody interested, they can get in touch for developing the OGS and the free space QKD and even the PAT, that is the most critical. And some work also we are doing on chip QKD using the indium phosphide, in which we intend to implement the entire transmitter onto the same chip. This is with IIT Hyderabad. And some more work on quantum repeaters, because that would be the ideal to do the quantum repeaters and extend the range and have a information theoretic security. So yeah, we at DRDO, we also have a some roadmap for all other quantum technologies, which are mainly the computing, sensing. So we are trying to work on all these areas. So I think this is all known to others. So with this, I think I conclude. Yeah.
Thank you, Amit. I think we have got maybe time for one very short question. Is there a question for Amit? I mean, they have been responsible for the 100-kilometer demonstration between Vidyanchal and Prayagraj. And that was a milestone for us. But DRDO itself is working on many things. So if you do have a question, maybe you can talk to him offline. And I encourage you to talk to him because he's also a storehouse of a lot of information about all the different aspects of the National Quantum Mission that he was just flashing up. So let me thank him formally.
Thank you. May I now invite Sri Deendayal Toshniwal, Deputy Director at DOT, to join us stage for honoring the session chair. Quickly, we will move on to the 9th session titled as Photonic Integrated Circuits and Interconnects. I invite the session chair, Dr. Bijoy K. Das, Professor at IIT Madras, to introduce the speakers and conduct the session.
Our speaker is ready. So welcome to the Photonic Integrated Circuit session. So I am Bijoy Krishnadas, Faculty Electrical Engineering Department here in IIT Madras. So in this session, we have two speakers. Both of them are online. And the first speaker already ready. I just want to briefly, because we are getting delayed also, quick introduction. Dr. Bill Corprana. So he is from Australian Research Council, Future Fellow and Senior Research Fellow within the Department of Electrical and Computer System Engineering at Monash University, Melbourne. His research focus is on photonics, basically photonics in optical communication systems. Bill completed his undergraduate in physics and electrical engineering at Armit University in 2006. Following that, PhD in the area of slow light in 2011. He then worked on ultra low noise optical phase sensitive amplifiers at Chalmers University, Sweden. And first he joined as a postdoc in Monash University in 2013. Following that, he is now a permanent staff member there. And in 2020, he made global news with a record super channel data rate from a tiny optical frequency comb. So he's currently the chief investigator and nodal leader for the ARC Center of Excellence in the optical microcombs for breakthrough sciences. So with this brief introduction, I invite Dr. Bill Corprana for his talk, which will excite for next 30 minutes. Thank you very much. Welcome.
Thank you very much. I'll just bring up my slides. Here we go. And let's get the slide format. Fantastic. And I can see that I'm on the screen, so that's really nice. Thank you very much for that. All right. So as introduced, and thank you very much for the introduction, Bijoy. My name is Bill Corcoran. I'm from Monash University in Melbourne. I'm part of a couple of different collaborative networks. The work that I'm going to talk about today is part of work we did with what's known as INPAC, which is a soft center that's 3 universities wide, University of Adelaide, Monash University and RMIT University. Let's try that again. All right, so my lab at Monash consists of 5 students, which is a big step change for me. I actually have a lab full of with some people now, which is very nice for me. We, as introduced, do photonics and optical communications. So what could that mean? That could be in a lot of things. So we touch on microcombs, we do optical carrier recovery, frequency conversion, free space coherent communications. There's chip-based elements involved. But I'll focus in on a little part of that work that we've been doing with the INPAC group. Now, INPAC is a soft center, as I said, so this is something where we all bring our own funding together and we talk to each other and work together. The center director is Anand Mitchell at RMIT University, and for each of these different parts, we have a theme leader. So we have people who are experts in design, fabrication and interfacing of photonic chips, and we use these chips for applications in data communications and in biomedical stuff, so lab on a chip and biosensing, things like that, and also in defense or precision measurement. I think depending on who you talk to, we can say one thing or the other there, but this is a lot for trying to see where we are in the world. One of the things we did that I popped in my bio just to give you a flavor of who I am in 2020 as part of INPAC was to show that a tiny optical chip could support very, very high data rates. And so we took a micro ring resonator, hit that with a laser, and that generates what we call a micro comb. So that's a frequency comb from a micro-sized device. And this created, from one laser, the equivalent of 80 very precisely spaced in frequency lines, so 80 clones of that laser. We were then able to successfully modulate that, put that through our field trial infrastructure in Melbourne, and get something like 40 terabits per second off this single tiny fingernail sized device. So with that, that got a lot of interest, and we've been sort of following that up ever since. So this happened in May of 2020 when we were globally realizing that perhaps the internet was important to us being able to continue to work during the first parts of the COVID pandemic. So that got a bit of a splash, and we've been working on that since. What this has turned out to be is the Centre for Optical Microcombs for Breakthrough Science. So this is an Australian government funded Centre of Excellence, again, headed up by Anand. What this is funding for a bunch of researchers in Australia and funding for us to collaborate internationally with our partner institutes. For 7 years, funded to the tune of something like 75 million Australian dollars, covering 8 universities, about 20 postdocs, and we'll have about 80 PhD students there. So if you have some undergraduates who would like to come to Australia, we will have the PhD positions for them. What this centre is involved in is they're using these tiny frequency combs for a bunch of things. So there's interest in sensing and measurement. So we're talking things like atomic clocks, spectroscopy and microscopy. So stuff like light sheet imaging and, you know, the use of frequency combs in microscopy. You can imagine this might be very useful if we can shrink, say, a Ti sapphire laser down to a very small type thing. Astronomy, turns out optical frequency combs are very important for astronomy. So things like measuring fundamental constants. You need a very stable comb running over 30 years, and you probably want to whack that in a satellite. So you probably want it to be small and lightweight. And the theme that I'm heading up is the information intelligence theme, where we're looking at not only data communications, but also thinking about processing light on frequency combs in sensible ways. So either looking at artificial neural networks or looking at the fire hose of information you get out of some of the sensors that you get with microcombs or optical frequency combs in general, and making sense of that in a nice way. So that's sort of who I am, what I've been involved in. What I want to now do is focus on using these microcombs for optical communications and sort of thinking about overcoming some barriers that we have with them and expanding what we can do with them in optical communication systems in the future. So I'll try to give a very brief overview of the use of optical frequency combs in optical communications. We've been using them for quite some time. Then we're going to want to try to figure out how to get the most out of microcombs for communication. So I'll go through our sort of step-by-step thing that's happened over the course of a single PhD. I should probably highlight Park, who's in that red dotted circle there. This is his own work, so I'm just taking credit for all of his hard work really here. And so we'll step through effectively what he was doing for his PhD. All right, so as I said, optical frequency combs have been used in optical communications for quite some time. So this started off in the days where people tried to use shorter and shorter pulses of light to carry information in a more rapid way, what was known as OTDM. This, using shorter and shorter pulses of light, you can imagine if you take a short pulse and if you take the Fourier transform of that, then that's going to be a really wide frequency spectrum, right? So turns out that optical frequency combs were being used for this at this point, used quite successfully up to about a terabit per second off a single pulse laser. And that was quite nice. After about 2006, coherent optical communications came into focus, and we were starting to really look at that. Here we've got the work from KIT, where they started looking at optical superchannels, individually modulating each of these lines to carry different data and cramming that all together. That stepped us from a terabit per second up to about 25, 30 odd terabits per second. Moving on from there, there was interest to see if we moved on to the era of SDM, at least in research. So where we started not using just one fiber or one fiber core to transmit information over, but many, many fiber cores within one preform or many, many modes. That then showed us that, hey, we can actually still use one optical frequency comb to support even more data, getting up to about 2 petabits per second in 2015, up to, I think, what still holds the total, like the record, no matter what source you're using, for capacity at about 10.7 petabits per second by the guys at NICT in 2020. In contrast, microcombs, small optical frequency combs, have a different pace of development. So when we first got really nice stable combs, and this is from the APFL labs, we're able to manage to get about 50 terabits per second from 2 microcombs. So if you look at the single comb performance from that, that's about where we were with benchtop frequency combs in about 2011. So the question then rises, how can we do better on that? The other thing that you might think of is, all right, well, we've already got optical frequency combs. Why do we need them to be micro? If I'm talking an integrated optics session, I guess some people also agree that maybe going micro is a good idea, but we should always interrogate our biases here. So why would we do this? If we're going to go to higher and higher data rates, and we're going to go to many, 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 many more channels and address more people, then we're going to want to be having more and more transceivers. Now, there's going to be a limit to what we can do there, as we found out through Moore's law, right? So only when we started to shrink things down in size, weight, and power were we able to up the total rates we have. Same thing is turning out to be a thing in optical communications as well. So we're going to really want to start to shrink down all of our elements. We're not going to want to have a rack full of lasers. We're going to want to have a chip full of lasers that can support the same thing on a small size, weight, and power, cost basis. So maybe looking at these micro resonators, looking at creating frequency combs for them might be a good way to start down that path. What do we need out of these combs for optical communications? Because every field that uses combs has a different set of parameters they really need. In optical communications, we really care about power stability. We don't want our signal power to be fluctuating all the time. That's hard to put data on. We need phase stability. We don't want the line wobbling around in phase. We need to be able to have that stable so that we can encode in phase. We want turnkey operation. We don't want to have a PhD student sitting in a rack trying to operate a optical frequency comb. That's going to be a bit too expensive, and it probably violates labor laws globally. So we want to just be able to turn these things on and run just like we do with our semiconductor lasers that we have nowadays. Other properties, optical signal to noise ratio, probably quite important. We want to make sure that our line is well out of the noise power. So one thing about this is per line comb power. So we want to make sure that we've got on each line about the same amount of power that we have for a separate laser. Feeding into that is conversion efficiency. If we're going to whack one of these devices with a laser to make this comb happen, we want most, if not all, of the power that we are sending into that device to turn into these extra lines. That's important, also hard to do. Putting the power where you want it. We don't want to be generating comb lines that are outside of our communications band. We want to keep everything where we want to be signaling. And all of these things become important when we think about upping data rates that we can achieve with these microcombs. All right, so using of optical frequency combs as WDM sources, for benchtop combs, as I went through before, we're up to about 10 petabits per second from 26 terabits per second on, over a decade. For microcombs, at about 2017, we started about 34.6 terabits per second if you drill down into that paper for the single microcomb rates that you can achieve. 3 years later, with a smaller spectrum, just only using the C-band, we were able to hit 39.2 terabits per second. And then going to SDM, we're managing to get about 2 petabits per second. So if you look at that, we're about 5 years behind the curve in terms of benchtop combs versus microcombs. So the thing is, we're probably still wanting to increase what we can do in terms of the microcombs themselves. So it's a good idea maybe to look at the difference between benchtop combs and microcombs and what is different in their parameters to try to figure out what we could be doing better. And if we do this, we have a look at all of the different things. We have a look at the spectral efficiencies we're able to achieve. Well, they're about the same. The aggregate rates, well, they vary depending on the experiment. The number of modes we're able to address, well, it's a little bit lower for microcombs than it is for benchtop combs. And why could this be? The big thing that we can really see that is a gap here is in optical signal to noise ratio. And you can't see my pen, so let's go for a laser pointer so I can gesture. There we go. So the big difference is the optical signal to noise ratio. So for benchtop combs, above 45 dB is about what you can get. Around 30 dB is what you're able to get from a run-of-the-mill microcomb. So there would seem to be some need to be able to get higher comb OSNR, and of course, to get to more and more modes, we're going to need higher power. There's also a large difference in ease of use, but we'll get to that, I think, through other means and modes. There are other groups that are working on that and doing that quite successfully. So, having said that there's a gap in the capabilities of microcombs for communications, let's go forward and try to figure out how to fix that gap. So there's a few different questions we've asked ourselves. One is, why is everybody using a certain symbol rate, a certain bandwidth per carrier for super channels in order to do their experiments? The next question we have is, okay, well, if we've got these microcombs and we want to increase their power, that's going to reduce the OSNR through amplification. The question is, what can we do to improve the effective OSNR? Can we do it through filtering? What design parameters are important for a comb filter? And then how can we predict comb filtering system impact? All right, So the first question we had was, okay, looking at everybody else's papers, everyone was using about 20 gigabaud subcarriers. So this means you've got a 20 gigahertz wide channel, and then you're smushing all of these channels together to create a full band super channel. What we figured out here is that receivers, well, somewhat unsurprisingly, receivers have a noise floor. Basically what that means for us is that any reduction in the signal that we throw into a receiver reduces the achievable SNR in that receiver. And that reduces the potential capacity that you can prove. Surely in a long-haul link, this is not really that much of an issue, but in the systems that people have been looking at with these record experiments where you're going over maybe 1,000 kilometers at maximum, then this actually turns out to be a bit of an issue. What we found was that, all right, what you then need to do is you need to restrict your channel, the frequency band of your channel, such that you've got most of that power concentrated in the smallest bandwidth that you can manage, and still get a benefit from this. So what we found out was when we threw more and more channels at the receiver, these channels off to the side would eat up your dynamic range. If you've got a filter there and you've got a relatively narrow bandwidth, you can up the rates that you work on. So how we've proved this, we made a little super channel with some independent lasers, and then we filtered the channel under test and corrected metrics. We used a off-the-shelf wavelength selective switch, which sort of came with discretized filter steps that we're able to do. Then what we then investigated was, okay, for different baud rates, at what point do we get the best operation? And what we found is as we started hitting the resolution of our wavelength selective switch, that was where we peaked up in the quality factor, the signal to noise ratio effectively, that we could measure on our channel. And so this was the same across a bunch of different modulation formats, as one might have really expected. And so we managed to peak up our ability to send information at around about a 20 gigabaud signal rate. That makes sense now why everybody was using this sort of area. So what we then showed is, okay, if we send all of our subchannels to the receiver and we've got more channels in our receiver bandwidth than we desire, we get a relatively low flat performance against symbol rate. If we then are able to filter out the channel, then we get somewhere between hitting a lot of channels and just sending a single channel into our receiver. This is able to give us a improvement of the achievable rates as measured by generalized mutual information. And what we find is as we would be trying to go up the modulation curve, this becomes more and more important in order to go to higher and higher rates. All right, so how can filtering be used to improve the effective OSNR of combs? Where did this come from? So we thought a little bit about what we had in terms of these micro rings. They turn out to be really nice, sharp periodic filters. So you're able to then use these things to then really select out these lines and knock out noise between the lines that you might have in a comb. And so this was used for more sensing precision measurement applications by NIST back in 2017. We had these rings that we were using to create combs. We thought, okay, let's see whether we can use them also to be nice precision filters for combs. So just using them as a passive element rather than an active element. And so what we then, the idea here is that when we amplify these combs to go up to higher powers so that we can then support more and more parallelism, we add in noise as you do with an amplifier. So what we then wanted to do was use this micro ring filter to basically knock out the noise between the lines. Why is that important? Because if you're then modulating a single line, you want to be just modulating that line. You don't want to be modulating noise and adding that into your signal. And that turns out is quite a limitation if you've got, when you start having a relatively noisy source, which is not often what we think about when we think about optical sources. Lasers are generally pretty good. All right, so we found out that we could filter out a lot of lines simultaneously. And we go from some situation here, which looks like we've got a lot of noise on our lines, to being able to have that noise filtered out quite well. What this turned out in terms of generalized mutual information, so more is better here, it means higher and higher data rates. And if we look at the carrier line OSNR, so the comb optical signal to noise ratio, if we don't do our comb filtering, we end up with a line looking like this, and that crosses a threshold that we set here as a 5% information loss, around 25 dB OSNR. And if you remember back to that table I had before, we're operating at rate maybe only around 30 dB OSNR. So we're really sort of right at this limit here. What this then gives us, if we have this comb filtering, is this green line here. And so that knocks down the OSNR that we have to have from our source. We're able to filter out a lot of that broadband noise and improve system performance. And this can be really important because a lot of the new devices that want to be low energy consumption start off with low comb line powers, and we then need to amplify. And so what we do is we win about 10 dB in terms of required OSNR, and we go from a constellation diagram that looks a little bit like this to looking something like this, which is nice and clean. The then question is, okay, well, we used one of our rings to do this. That's nice, but it's just what we had lying around in the lab. If we go back to the fab, what are the design parameters that are important in a comb line filter? So the structures that we use, this dual bus type thing. Oh, we've lost my signal. Maybe, not sure. Let me have a look at, oh gosh, I can't see what's going on. There we go, I'm back, fantastic. Sorry, I could just see the screen blinking there. Sorry if that was all clear for you and it just looked like me panicking. Okay, anyway, getting back to it. The micro rings that we use are dual bus waveguides. So we can have the micro ring here, we have an input going here, you have a pass port here, but if you're resonant with this ring, your light comes out the drop port here. The filter width is to do with, how lossy your ring is, and also some coupling ratios here and here, and that provides you with a transfer function that looks something like this. When we were in lockdown, which is when this was done, we asked our question, can a laptop replace a lab? And I mean, really it can't, but we can simulate our system pretty well. So we're able to simulate what we had in terms of a device, and then have a look at how the insertion loss changes with resonance bandwidth for a particular platform that we were using. We then whacked our system, basically we built it up in MATLAB, and what that showed us was that we had a really good system for matching to our experimental data. So the red and the green lines here are the fits to our experimental data, and then our simulated curves are these multicolored lines here and this black line here. So having had that, we now understand our system. We can at least get an idea when we're stuck in our lounge rooms doing science. So what we then did was measured the required OSNR benefit. Basically, what we were interested in here is what happens if you're going to different modulation formats and you're doing filtering or you're not doing filtering. Does this actually change the benefit? And the answer to that was no. It's basically modulation independent, which is very nice for us. We then had a look and tried to see if we were using different insertion losses in our devices, because sometimes fab goes right and sometimes fab goes wrong. And we showed that we could actually get a really low required OSNR for 64 QAM if we could do as best we can at about 3 dB coupling loss for our devices, earlier devices that weren't so good, 13 dB coupling loss. We're still able to reduce the required OSNR for 64 QAM down to about 10 dB and a concomitant change for 512 QAM. What we're then able to do was sweep the coupling loss, see how things changed. And within this range, we were able to, hitting on our platform, something around a 200 megahertz resonance bandwidth. So this is quite a moderate Q of about 1 million. We're really able to see quite some benefit that we would predict with our system. One of the other things that we were then interested in was, okay, well, it seems like if you go tighter and tighter, if you've got low enough insertion loss, you just get better and better results. One of the things that we also had to think of is one resonator never matches precisely another resonator. So you're always going to have a slight walk off of your filter resonances and your comb lines. And so what we found is that there's going to be a bit of a trade-off or a sweet spot when we think about the bandwidth of the resonances, and perhaps this 200 megahertz bandwidth is actually quite reasonable. So then as we go to broader and broader frequency mismatches, the OSNR benefit drops in the same line shape as the resonance, which is nice. It means we can predict what's going on and we can figure out systems from there. The last thing I wanted to talk about, and hopefully I'm not too far over time for everyone, is how can we then predict comb filtering system impact. So we know that we can filter our combs, we know we can get better OSNR. Does that translate to better signal to noise ratio of the data that we're sending down? And so having that system that we could simulate allowed us to go off and try to simulate some more about that. So what we're doing here is we've got some comb that's coming in, that's going to be at low power. We boost that up to higher power with an EDFA. We then send that through our comb filter, and then we might want to send through a WDM filter. Maybe we've got some interim amplification steps to boost up line power. What we're then wanted to quantify was the difference between the optical carrier to noise ratio at output versus the optical carrier to noise ratio into this system. And what we found is that in an ideal case, this is basically just related to the resonance width of your microring resonator with some normalization factors.
Bill,
Sorry?
Can you hear me?
I can hear you, but I'm getting a lot of feedback. Yep.
Can you hear me now?
That's perfect. Thank you. Yes.
So you have only 2 minutes left.
Fantastic. I'll wrap it up really quickly for everybody. All right. So effectively what this is then a link between the ability to change our optical carrier to noise ratio against resonance. That's nice because we then have this alpha factor that we can have a look at against resonance bandwidth. We had our closed form solutions here, numerical simulations in the dot, they match up pretty well. We then had a look at what happens when you modulate both signal and noise and included that in an SNR equation. We come up with a curve that basically shows you that that alpha factor still holds. And then what we're then able to do is have a look at the SNR is related in a system to this alpha that we came up with. And that allows us to be able to plot things like this, which then can say, okay, we're with a certain resonance bandwidth, how much optical carrier to noise ratio do you need in? Or if you want a target carrier to noise ratio, what resonance bandwidth or what alpha do you need to be able to do? What does this bias? Well, basically for the system that we were looking at, you can get about double the amount of comb lines out of the comb that you might produce. So you double the data rate, or if you look in SDM, it goes higher and higher. So you're able to just link this with the gain that you can get, and your alpha there enables you to go to many, 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 many parallel channels. So this is something where we might finally start being able to get towards those 11 petabits per second. All right, so the conclusions. Why is everyone using 20 gigabaud subcarriers? Basically because of practical equipment constraints with transceiver noise. So beware when you're thinking about interpreting results. This is going to change over time as we get better. Can filtering be used to improve effective OSNR of combs? Yep, about 10 dB is what we showed with about 1 million Q ring. What design parameters are important in a comb filter? Well, symmetric coupling is pretty good. There's a trade-off with Q on loss-limited platforms and dispersion. And if can we predict comb filtering system impact? Well, we can do this with a surprisingly simple model. I suggest you look at Park's papers for this. It's quite nice. We can get about 2 times the comb lines that we're about, so double the bandwidth that we were previously able to get, or really, really dial up the SDM. All right, at that, I'll say thank you very much, and thank you for listening to me on a Sunday afternoon. It's very nice to have you in the audience.
Thanks, Bill. Very nice, exciting talk. Now the floor is open for a couple of questions. Any question?
So, Bill, this has significance for SDM systems only, or in the current coherent systems, this can also be used?
So I guess what we've been showing is in current single mode systems, these combs can be used. I think the comb filtering should enable you to use some of the lower power devices that we see that are turnkey. So one thing that we've been noticing is a trend in the field of microcombs to produce lower threshold powers, really nice devices, but the pearled comb line power goes down, which is a problem for optical communications. So this provides a method to be able to bring them up to telecom standard, basically. The other thing, I guess, is it all depends a little bit on what you talk about SDM. If you've got parallel fibers that you want to address, this provides one source that's able to address parallel fibers. So that could be of use in a bunch of different systems. I am still skeptical as whether telecom is going to be the first place where we see microcombs commercialized. I know in telecoms, we tend to have really nice lasers and we tend to not move away from that because, hey, they're really nice, they're really well qualified, and other technology is risky. But yeah, we'll see what the future brings. It's certainly one option that we should be looking at in universities, and hopefully that'll give some ideas down the line as to whether this is going to be commercially viable.
Thank you so much.
Any other question? Okay, looks like no more question. So thank you very much, Bill, and on behalf of organizing committee, there is a memento for you.
Thank you.
We'll be couriering you.
Okay. Either I'll just have to come over and visit. Thank you very much. Bye.
Yeah, okay, that would be great. Yeah, thank you. So already offline. Okay. So now we have the second speaker. Is he online, Shankar?
Yes, I am.
Can you hear me now?
Yes.
So it's my pleasure to introduce Professor Shankar Kumar Selvaraja, who is actually Professor Ramakrishna Rao Chair Professor at the Center of Nanoscience and Engineering in the Indian Institute of Science, Bangalore. And he is also chair of the National Nanofabrication Center at ISC. He received his PhD for his work on the wafer scale fabrication technology, silicon photonics, of course, silicon photonic integrated circuit from Ghent University, IMEC, Belgium. And he is an alma mater of Bharatiya University, College of Engineering, Gindi, University of Twente, the Netherlands, and Ghent University, IMEC. So he spent over 15 years for silicon photonics technology, particularly developing wafer scale processing for IMEC. And over the years, he published more than 260 journal articles, international conferences. So his current area of research includes silicon photonics integrated circuit that will enable high-speed optical connectivity, integrated photonic-based on-chip sensor, neuromorphic computing, and lately he has started also quantum photonic circuits also. So with this, I invite Professor Shankar for your 30 minutes talk, maybe 25 plus 5 minutes question and answer.
Sure. I'm just going to keep my timer so I can have an eye. All right. You can hear me well, right? All right, good. Thank you very much, Vijay, for the kind introduction, and Deepa for this invitation. Unfortunately, I couldn't make it. I only knew it yesterday afternoon, so very unfortunate, but fortunate enough to actually give this talk online. This is going to be a contrasting talk from Bill, from systems to, we are going to look at the devices and what kind of device can enable these high-speed communication and so on. And I'm going to give a more indigenous outlook, because whatever I'm going to talk about today in all my slides, this is all fabricated, designed, fabricated, and characterized here at IISc, except for one device, which I will actually let you know. Rest of the things are cooked at home. All right. So this is the team that puts in all the effort, and congratulations to this team for working together and making all these amazing results that I could talk about. Right, I just put them into slides. So for some of you who are still wondering why and what this chip is all about, basically what we are trying to do is what electronics has gone through a long time ago. So we would like to take all these functionalities that are in bulk domain, right? All these modulators, filters, splitters, all those, and put it onto a thin substrate, right? So that is very important. It need to be a thin substrate, and we want to realize this functionality on this thin substrate. And this thin substrate that we have, where we have our functionality inbuilt, is what we call a chip. And this integration actually brings in a lot of advantage, which includes both functional integration and more often performance enhancement as well. So what do we use to build this whole chip? We go back in time, and then we also use silicon in this case. So silicon photonics is a versatile tool, right? And you can build quite a lot of interesting optical functionality using this. The reason for that is we're going to utilize the mature silicon CMOS and use the parallelism or high speed of light on chip. And this particular platform is very mature and it is scalable, right? So you can, whatever you realize on a small chip, right, as an experimental laboratory demonstration, we should be able to do it on a large 300 millimeter wafers. And also, it allows you to integrate different material systems. And that is something that I'm very excited about, and that's what I want to talk about today. How you can exploit the same silicon photonics, but bringing in these new materials and doing different functionalities or integrating them. Conventionally used silicon material can be used for photonics. And there are different, platforms, applications that you can exploit with this platform. One is, short distance and long distance connectivity, and that's, most of you are interested in that. And some of you might be also interested in microwave signal processing as well, where, photonic ICs are very well suitable. And then also for sensing and spectroscopy applications as well, because we have light matter interaction, and we can take this and then do a lot of interesting spectroscopy and sensing on chip. So what do we mean by photonic integrated circuit, right? So this is what we mean by PIC, right? We have various functionalities. Unlike CMOS, we don't have one single hero device, right? We are slowly moving towards, programmable photonics, where you can realize some of these functionalities together, right? But then at the end of the day, the light coupling, guiding, and those are all the fundamental blocks that are very different in nature, right? The functionality can be realized through some complex network of these elements. But at the end of the day, what you see here are different functional elements, right? Coupling the light, guiding the light, and filtering the light, and modulating the light, and of course, detecting and generating light. So all these functionalities we would like to have on chip. And more often, we are not blessed with a material that can offer all of this, right? So that's where we need to look for options. So as I mentioned, photonic ICs, they offer this huge potential of integrations, right? So hundreds of functionalities could be, or functional components could be integrated, and we could do this in a more power efficient way. And of course, since we are using light, you can have high speed and large bandwidth. And what this photonic ICs offers is compactness of any system, and that's what Bill was also talking about. So everything associated with system specification, right? Let it be power, let it be size, weight, all these goes down. The latency also goes down because of the bandwidth. And then as I mentioned, since you're confining the light inside a small volume, you can have this high light matter interaction, and you can use this in a variety of spectrum in general, okay, if you design and choose the material. So this is going to be broadly my outline. So we'll just dive into it. The first thing we want to just make sure is we understand the circuits, right? So when we say photonic ICs, they have a certain footprint, and this footprint comes from the wavelength that we use and the core refractive index of the material that we use. So if you're going to talk about silicon, right, it's going to be about 3.5 is the core refractive index, and then the wavelength of light. Let's say if you're going to operate in 1550 band, then you need 450 nanometer size, structures, right? You can make it smaller or larger in one dimension, but at least in one of the dimension, you want to make sure that you don't violate this. That means you need to, operate within the diffraction limit. You can use many material and you can use different configurations. So you can use silicon on insulator, that's what we call SOI. Silicon nitride can be integrated in various configurations. So it's up to us to put it together in the form that we want, right? You can be very creative in this domain, right? So all you want to make sure is you stick to the certain basics of, refractive index, contrast, and size. Then you can confine light. One of the bigger problems that we have, right? So you can confine the light in a very small space, but then you need to couple the light, right? So for the coupling between a single mode fiber and this small waveguide, you need to have some sort of funneling, right? So that funneling is done through multiple ways. The two, predominant coupling schemas, one from the edge of the chip where you can couple. The other thing is from top of the chip. So we prefer to use surface grating coupling, which is much easier, that you can do this coupling across the wafer without any issue. But if you want to do edge coupling, there is a lot of overhead involved in that. So how efficiently can we do this? We can do it reasonably well, right? So here we are talking about a 3.5 dB per coupler as an insertion loss, right? So this is on a silicon without doing, really quite a lot, right? If you do a little bit of engineering on this, you can push it down to 1.5 dB per coupler, right? So this is doable. And this is something that we have done. And you can see here, we are much better than even some MPW runs that is offered. And the other way of looking at this is, okay, I have this 3.5. How do I improve it? So there are two ways to improve it. One is by putting bottom reflector mirrors where the light goes through the chip and then it is reflected back, right? So you really squeeze out all the light that is escaping. And the other thing is to really work with the mode, right? So what is the mode profile that we have? So that's what you see here, right? So the normal fiber mode is just this green, right, line, which is very wacky here. So it's really not helpful if you look at the fiber mode, which is Gaussian in nature. So if you do that engineering, we should be able to push this limits. And this is what I was talking about. This is on a silicon nitride platform where we were able to push it to 1.2 dB per coupler. And this is coupled to air, right? So there is still a reflection that we think can be reduced. And the intrinsic, this is what you see here, right? The other thing that I would like to show here today is you have coupled the light in and it is in the waveguide, right? I just want to pick one example to show, what you can do with this device. So this is something I don't have to convince you because the losses are high as you move to higher frequency anywhere you can. So fibers are going to be the intrinsic solution to this. But the problem here is we have the resource to do it, but if you're going to send them, right, you're going to have what is called RF power penalty across the frequency spectrum. What is that, right? So when you just take a light source and then modulate it with a Mach Center modulator with an RF source, and you look at the spectrum, right? This is how the output spectrum is going to look like. So you'll have sidebands and the harmonics, right? And this is going to be sent through your fiber. Right? And when you send this through the fiber, which I call this double sideband with courier, you see here, these are all the dips, right? At particular frequency. And this is because of what is called a power fading, right? At this particular frequency, the sidebands flip sign, the phase of the sidebands flips sign. So they become out of phase. So when they become out of phase, there is no information present in the signal that you're transmitting. So that's where we prefer to use single sideband, right? And that's what you see on the right side, right? So there's a 180-degree phase shift when you use double sideband. And we thought, can we do something in a passive way? I don't want to do anything on the modulation front, like on signaling and so on. So let's take a very simple device. This is a self-coupled ring resonator, where it looks a little bit funny. It looks like an hourglass, as you can see here, where you can actually pick these resonances and create a very nice, transfer function where I can just split two wavelengths. All right. This is actually simulated, and when I fabricate this and put it through test, this is what you see. So on the left side is the architecture that you use for characterizing this, and on the right side you see the insertion loss of the sideband that we can suppress, right? So when I suppress it, then you can see here, without compensation beyond 9 gigahertz, I don't see any signal recovery at all. It becomes very bad. Right. So reason for that is this power penalty I was talking about. But when I apply in compensation, you can see that I'm able to recover signal up to 20 gigahertz. And this is recovery, after 42 kilometers of transmission, right? So that's the fiber pool that we had. We could even do it further because we don't see any reason why they should not do any further. You can do some data transmission and then show that it is indeed a workable solution, even using with a very passive device. All right. So that is the potential of using a photonic device for optical signal processing. So as I mentioned earlier, that the power of integrated circuit is you can put all these functionalities in a single chip. So the next functionality I'm going to show you is a detector. Can I put a detector on chip? Right. Here I'm looking at application in short range, right? Around 850, 890 nanometer technology. And here again, I'm going to use silicon nitride as a waveguide technology, which is transparent, and I'm going to integrate a silicon detector, right? So this is purely playing the game with silicon, CMOS material and process technology. So what you see here is a ring resonator that captures the light that I want, and then I make the detectors inside this cavity. And as the light goes through, the silicon absorbs, and you should be able to detect this light, right? And what you see here is just how much power is coupling into silicon as you increase the size of the silicon detectors. And this is actually a fabricated device. You can see on the left side is the optical image, and the center image here is actually the device within the cavity, right? So this is the silicon nitride waveguide that's carrying the light and flanked by the silicon absorbers, followed by these detectors. So we should be able to pick all the carriers that are absorbed in silicon, right? And we were able to do that. And just for your note here, we saw a 2 orders of magnitude increase in responsivity. So the responsivity is about 0.8 amp per watt, right? So this is massive, responsivity increase that we see, and this still operates at 7.5 gigahertz, right? The voltages here are primarily because we are operating at a reasonably large electrode gap because of fabrication, tolerances. But if we can move it much closer, this operating voltages can also be brought down. So this is all something that we can integrate it and demonstrate it ourselves here. Once we have done the detector, so we have put the WDM into it, right? So I have the detector now. Let me filter and then detect, right? So filtering, we are using an SL grating, which is a planar curved grating. The light comes here, the broadband light, and then it is reflected by this blazed grating, and each wavelength is spatially segregated here, right? So you can see here, this is the optical image. So it's a CMOS camera, so silicon CMOS camera. So it captures the 850 band light here. So you can see nicely see here the reflection and the output flaring out of these grating couplers. So this is how the WDM response shows. This is a measurement results, by the way, and you can design the 3 dB bandwidth and channel spacing as you like, right? And then we integrated the detector along these waveguides, right? And you can see a very uniform photo response from all of these detectors. So now you have an integrated spectrometer. So you can have a WDM, a DWDM, and then put a detector on chip, right? So this is primarily working at 850, and I don't see a reason why we can't integrate a germanium photodetector that we have initiated to develop here in my lab. This is the WDM that I was talking about at 1550. Also, you can do it, and this is again designed and developed here at our facility here. The next thing is to look at modulation. So I'm able to do this. Splitting detection is all fine, but then the primary driver, of course, detection operating at high speed is also important. But the other important thing is, how do I get this information onto my optical carrier? That's where modulation comes, right? So we are characterized by this optical constant here, and how are we going to change the refractive index, right? So that is how any modulator operates, right? So there are various effects that one could exploit, right? And there are various material systems that you can exploit to do that. Today I will show you two. One is silicon, and the other one is lead zirconium titanate, which is PZT that works or takes advantage of the pockets effect there. So this is a very simple PN junction, and this is something that we have done through MPW, right? Because we don't have implanted at home. We have made a diffusion doped system which works in megahertz, but if you want to move to high frequency, you need to have this very tight implant. Simple diode, and as I mentioned, the refractive index changes the resonance of the ring resonator that you see here, but it also changes the absorption. So that is the problem with carrier dispersion modulators. So it gives you modulation, but it also gives you absorption, right? But despite that, we were able to demonstrate optic bandwidth over 45 gigahertz, right? And you can imagine, so this is just a single device, only about 10 by 10 micron, pumping at 45, 50 gigahertz, right? So you can think about different modulation formats where you think that one device could actually pump out 50 to 100 gigabits per second, right? So this is the power of integration. So what we have also done is we took this simple PAN device, and actually you can make electro-optic comb out of it. We listened to Bill about the Kerr combs, the soliton combs that was discussed, but this is slightly different. So we are looking at electro-optic comb, right? So when you take the light and beat it with the RF, you create these sidebands, right? So that is what you see here. This is actually what you see when you beat it with an RF, right? And you can actually increase this number of lines by putting low number of lasers here. So if I take 2 lasers, I'm able to generate 10 lines out of it. And this squarely depends on how efficient your electro-optic modulators are, right? So these are all very simple silicon pin diodes. And even with this, we were able to get, workable 10 lines, right? And our hope is will migrate towards an ferroelectric type material, and there again electro-optic combs should be even better. The reason for that is you don't have to spend too much power in generating these combs, and that's where this comes, because the electro-optic effect is a material property here, right? So you are looking at the Chi2 material where your electric field should be able to change the polarization of the material that we have. This only works when the material is non-centrosymmetric. And that's why you can't do this in silicon, right? At least relaxed silicon. So this is the simple R coefficient here, right? The electro-optic coefficient. Strained silicon is rather poor, and lithium niobate, the fantastic material, the mature material they tried, is nowhere near the potential, other material system that includes PZT and also barium titanates. So these two are the material that we are interested in, moving forward. And you can use, multiple integration strategies to do that, right? I'll just quickly skip this, and then for most of you, this might be interesting, where I'm looking at this a very simple, unit cell where, the titanium atom's polarization dictates whether I have in-plane polarization or out-of-plane polarization. By exploiting this polarization, I can make electro-optic device, all right? So that is what you see. When I apply a field, right? So my refractive index is going to change, right? I can flip the polarization or orientation of this, and then I can get this. And we went ahead and then made this, sputter deposited lead zirconium titanate PZT material on top of SOI. So these are all silicon waveguides, right? And we deposited it with engineering really the buffer layers and so on. There's a lot of material science involved in this, but we worked toward that, right? As you can see here, this 100 peak is what we are, really looking for, combination of these two. And we have moved along.
Shankar?
Yeah.
Your time, 30 seconds left.
25 minutes. I see here 2 minutes left. Okay, fine.
Address some questions. Yeah?
Okay.
Go ahead.
So I just want to show you this where, oops, something froze. Yeah. All right. So this is what you see when you make a modulator, right? So you do, as I mentioned, you do a little bit of engineering, and you can see here 300 picometer per volt. And right now this is the state of the art, and you can also make this work at high speed, right? Right now we are operating at 13 gig because of our driver limitation, but I don't see a reason why this cannot be pushed even further to 40 or 50 gig, all right? So I'll close this by saying silicon photonics is a versatile platform, right? And when you're just relying on standard processing, it limits a lot of things. Heterogeneous integration is the way to go. And I have just demonstrated that we can do this all, here in our lab, and I don't see a reason why we cannot scale it up, from where we are right now. But moving forward, we want to, make these modules available for system builders, right? And that's where packaging initiatives are required, and we are putting effort in that direction. With that, thank you very much for listening.
Yeah, thank you, Shankar, for giving oversight of technological aspects, whatever you are carrying out in IISc Bangalore. So we have a couple of minutes for question. Any question? So since Shankar, you have no questions here. Which question? Online, you have a question. Can you read?
Sure, I can ask a question.
Yeah, go ahead. Hey.
That was the 3D polling was looked really cool. Is there a simple way to understand why that's so effective?
Yeah. I missed the background. So we got this, looking at the effect of domain in barium titanate. So when you deposit this ferroelectric material, right? So you are going to have these domains, and they are very effective at a certain orientation, right? So you don't expect them to be either 0 degree or 90 degree, right? So they are very effective at a certain orientation. This comes from the the unit cell that you have and how these ions are moving and so on. So for barium titanate, it was around 54 degrees or so, or whatever, right? So if you look at barium titanate, right, you don't pull it, orthogonally. The rotation is around 54, and then you make your waveguides orthogonal to it, and then you pull it, right? But in case of PZT, it was a little bit different because that is at the bulk device level, right? But we are looking at the cross section of this waveguide, where these domains are formed, on top of each other. But then, if you do a lateral pulling, right, we saw pretty much nothing. It was like 4 picometer, right? Because you have a lot of these orthogonal domains that are not responding at all. So they are just sitting dumb there. So they are not doing anything. So the moment you do a quadrature, then you create a non-zero, work, right? So you're not anymore just along the domain alignment, but now you're working, and then you're trying to flip it. So you try to engineer that, and that is how they work. And you can still make it even better. But then we thought, okay, let's try it out, and it turns out that even not sweating that much, we were able to put out 300 picometer. And I think if we do a little bit of careful design of the electrodes and waveguides, we should be nearly theoretical limit, I think.
That's super cool. Thank you very much for
Yeah,
that.
thank you.
All right, I think we are also time for next session, panel discussion, I think last session. So with this, I thanks both the speakers, Bill and also Sankar, for giving exciting talk. And as you are also online, so on behalf of organizing committee, there is memento. So you can pick whenever you are visiting your parents here in Chennai, or online we will be ending. Yeah. Thank you very much.
Thank you very much.
Very much, Sankar. So there is an announcement. The next session, panel discussion, that will be starting exactly at 5 o'clock in this room. Yeah.
Sorry, sir. May I invite Mr. Rakesh Desai to felicitate our session chair? Thank you, sir. We'll meet at 5 p.m. after the tea. Thank you.
around 10 megahertz, and G2G is less than like it is 0.
Ecosystem. Kindly allow me to invite Dr. Rajkumar Upadhyay, CEO C. to be the session chair and Dr. Deepa Venkatesh as the co-chair for the session. I would also like to invite the panelists, Mr. Badri Gomatam, Mr. Atul Gupta, Mr. Abhishek Dikshit, Mr. Kumar Sivaranchan, Mr. Bharat Goyal. Thank you. All doctors, not Mr. Sorry, all doctors.
I think, can we start? Because this is the last session and most of us have flight. So that's why we were rushing it to start at 5 because then we want to close at 6 or before 6 if possible. I think we all had very enriching sessions today and yesterday. And the basic point which was talked about is that there is a need of, optical fiber will be one of the important ingredient in setting up the telecom infrastructure. If you go by Cisco Mobility Report, the current data consumption is around 26 GB per month, which is going to be 62 GB per month within next 4 years. And therefore, to such large data, such huge data, we need optical fibers, equipments, optical fiber infrastructure. We have been importing all these years we have been importing, and even today, our trade deficit in electronics is around $60 billion of worth of. So this is the economic part, but we have security part because if we don't, if we depend on the imported system, security we some way or the otherwise compromise. Therefore, the whole system of TTDF came, Telecom Technology Development Fund. Under that, I think the advanced optical communication and 6 gigahertz, the terahertz project for 6G were the first 2 projects were sanctioned by the government. The aim of this project is to produce state-of-the-art systems, do a lot of indigenization, do sub-assemblies, assemblies, and be totally self-reliant in producing these particular equipment out of this test bed. The advantages are definitely in terms of strategic independence, in terms of security, in terms of cost, in terms of supply chain, in terms of vendor lock-in, customization, all these advantages we will have. I will only say that the beginning has been very, very good. And what we expect from this particular project is that we encourage the complete ecosystem partners. And I'm not mentioning that the partners which are in AOC only need to be associated, because the whole ecosystem should be part of it. And whatever way we can contribute in this particular journey, it will be very, very important. The thing what we are looking from it is compliance to standards. Whatever we produce should be compliant to standards. We should aim it for import substitution for domestic initially and export later. Certification is a must. It should be part of the project. All the certification, be it TEC, BIS, whatever certifications are required, should be obtained. A patent should be filed, and a lot many people should go into standardization activity and see that Indian standards, Indian inputs are built into this standardization activity. And IPR generation, of course, a lot of IPR should be generated so that some of the, at least in 3G, 4G, 5G, we have the SCPs. I am not sure whether the same thing works for optical. There we get into trouble because of SCPs, because SCPs are cornered by few countries and then others are developing. You need to make a hefty payment for utilizing them. Security by design, the design should be secure. A strong synergy among the ecosystem partners, because unless until we collaborate and, design reuse should be one of the criteria. If somebody has done one thing and it should be utilized by the other partners. Targets to be met, as in the morning it was said, that all the targets should be met. So to discuss all these issues, we have a very, very eminent panelist among us. So I would like to, and I have Dr. Deepa Madam, who is the co-chair today. I think you have heard her, you have listened to her, and she is the project lead for, she brilliantly moved the whole project. I think we are very, very confident and very sure that under her leadership, this particular advanced optical communication project will really see the light of the day in a great, and it will have grand success in terms of a lot of import substitution and generating a lot of technologies for our country. So to start with, let me just briefly, because in paucity of time, briefly read the small biodata. We have Dr. Badri Gomatam. He's the CTO Telecom at Sterlite Technologies Limited, Camarillo, California, US. He's the business and technology professional with expertise in managerial and business roles in networking, telecom systems, IC, photonics, and related industries. We have Atul Kumar Gupta, who is the head optical technology in CDOT. I think the designer of many of the technologies, right from ONT, OLT, DWDM, I think a lot of things. And he's also head of quantum communications with more than 30 years of experience. We have next one, Professor Abhishek Dikshit. I think you all know him. He is the professor in IIT Delhi. He is the Philips NXP chair professor, and in the electrical engineering department, he has published more than 30 articles in the international journal and 50 papers in the conferences. Dr. Kumar Sivarajan, I think he's again a stalwart in the industry. He holds a BTech from IIT Madras, PhD from Caltech, US. He worked at IBM Watson Research Center. Since 2000, he has been the CTO at Tejas Network, and he is the creator for 4G base station, indigenous first base station for the country also. Dr. Bharat Goel, he is Associate Vice President at Tata Communication. He completed his Bachelor's of Technology, Electronics and Communication from NIT Jalandhar. He's also he's a digital ecosystem enabler that powers today's fast-growing digital economy. So thank you all the panelists. I think what I'm going to do, because I would, I will not ask any questions for any one of you. Question asking will be done by Professor Deepa. So I can only say that since this advanced optical communication testbed has been set up, I mean, the project has started going on. So you, each one of you, I would like you to, say whatever things I discussed that we need to do patent, we do standardization. So whatever your company is doing, what area you are working in, and how it can contribute to the journey of Atmanirbharta in our country, and what are your messages to the ecosystem? What are your messages to the other partners? So we'll start, I think, the way our panelists have been sitting. So I will start with Dr. Badri first.
Thank you. Thank you, Professor Deepa, and also the IIT to host us and for the invitation for the DOT for this event. Can you hear me? So yeah, okay, good. So our participation in this panel as well as in this consortium comes after a lot of engagement with the community, within the research community as well as the industrial base inside India. We have been in the fiber optical manufacturing for now 25 plus years. Many of you may not know it, but we are supplying around 50 million kilometers per year to the global markets. And it is a large organization in terms of its capacity and so on. But largely the industry buys what is called a commodity, standard single mode fiber. On the background of all this, everything we do is indigenized, meaning our process is indigenized, our chemicals are indigenized, our engineers are from here. We hire from all these institutions mainly to develop our R&D strength. We have around 700 patents that have come up in the last 10, 12 years because we put some of the principles in the earlier panel that was discussed. So in that sense, our journey into this advanced optical test bed has been through finding ways to increase the capacity of transmission. One of the ways you can increase the capacity of transmission is by increasing the number of fibers that can be packed into a certain space. Typically, that is a cable, which is a few square millimeters in size. So our journey here is to introduce what is called a quad core fiber, meaning in a single same dimensions as a standard fiber, 125 microns. We put 4 communication channels instead of 1, which is the norm today. So if you have a standard cable, 24 strands, 48 strands or 96 strands, you can quadruple the transmission capacity for the same size. Alternatively, you can do other things with it. You can use one channel for communication, one channel for sensing. You can do many other, interesting, technology exercises around it. That's based on the imagination of the people who wish to try this type of a product out. Our aim has always been to bring such advanced technologies to the mass market. In the communication industry over the last, let's say, 30 years, there has been a growth in capacity, in transmission capacity in bits per second. In the bits per second, we have gone in leaps of 4, like OC3, OC12, OC192. Now we're in the 100 gig and multi-100 gig area. This curve has roughly followed 4x capacity increase for 2 times the cost. That's typically when the next generation gets adopted. So our aim in participating in this test bed is to bring this view for this advanced fiber. Since everything is manufactured in our premises, we think the entire connectivity ecosystem, connecting to the fiber, splitting it, and the whole piece, we wish to bring it to that. Today it is not there, obviously, because it's a new technology. But by putting it into the test bed, we hope that this cost curve can be achieved, and as more and more people end up using it. So that is sort of my starting point for this panel. Thank you.
Thank you so much. Mr. Atul Gupta.
Yeah, good evening, everyone. So thanks for this opportunity. So in CDOT, we are working in the area of optical communication technologies as well as quantum. So we have products in the access space, the core network, the DWDM, optical cross connects, QKD, and we are working in mobile fronthaul as well. So as far as optical test bed is concerned, CDOT is building a optical network test bed. The intent is that for any indigenously developed module, sub-module, or a component, there has to be a end-to-end infrastructure where that module can be tested in a field-like scenario. So for example, if we right now, all the major building blocks that we use in any core network that are imported from different vendors. Now, with this optical test bed initiative, which is funded by TTDF, some of these modules are getting indigenized, and they will need an infrastructure where they can be thoroughly tested before they can be moved to the field. Now, I believe that more such indigenous development of critical building blocks is certainly going to take place. So simultaneously, we are building an infrastructure which will have an end-to-end equipments which are actually there in the field. So so the module, anything which is getting indigenously developed can be thoroughly tested. It will have all the test and measurement equipment for the chambers for testing it from the environmental conditions perspective. As an example, if there is a development of a, let's say 100 gig coherent optical module. So one thing is that the functioning of that module itself. The other thing is that how it is affecting the other channels which are going in the network. So that cannot be tested going straight away to the field. There has to be an intermediate step where it can be ruggedized if it is affecting the performance of other channels which are flowing in the network. That can be tested. Similarly, yesterday we were having a discussion. Can we actually indigenize modules like EDFAs, wavelength selective switches, multicast switches, which form the core of the network and are not there from any, there is no competency here as such right now to build such systems indigenously. So our endeavor is to plug that gap and provide a ready platform where without, anyone is welcome to make use of that and come out with solutions which are rugged, and then move to the field, move to the next step where it can actually get integrated in the system and go to the field. So thank you very much.
So good evening, everyone. First of all, I would like to thank Deepa and organizers for giving me an opportunity to be part of this panel. So as you would know, I'm from IIT Delhi, and IIT Delhi is contributing in this optical test bed in 5 aspects. So first, we will be developing reconfigurable optical filter, which will help us to extract the carrier. And this is typically used in self-homodyne detection system. So that will be one contribution. The second contribution is that we will be designing frequency comb sources. So frequency comb sources that we are targeting to develop would be energy efficient. It would be cheaper compared to the transceiver systems that we have at the moment. Then we will be, so these are the 2 developments from IIT Delhi at the component level. Then we are designing networks also. So we will be designing Li-Fi network. So for Li-Fi, we are developing everything from the scratch. We are developing modulation schemes in FPGA and MAC protocols also in FPGA. And we are working on the optics, which will be tailor-made for Li-Fi systems to increase the user mobility. We will be developing control plane protocols and handover protocols also for the Li-Fi network. So currently we are very hopeful based on the simulation result that our protocols will be better than what is present in the standard. And hopefully we will like to improve what is existing in the standards at the moment. Then we will be developing FSO systems also. So FSO systems, you have heard the presentation. So the key differences in the FSO system that we will be designing compared to what you have seen in the earlier sessions is our FSO systems would be using laser beam engineering filter, which would be using structured light for enhancing the reliability. And then we'll be using some error control codes that we have developed over the last 4 years. And these error control codes are specifically suited to FSO systems. It's not some error control codes that we have picked up from any other standard. Then we will be, of course, for FSO systems, a good and reliable pointing acquisition tracking system is required. And we will also be designing it at IIT Delhi. So we have some ideas there as well. So with all these 3 advancements in how we shape the beam of the light and how we do the error control coding and with a reliable pointing acquisition tracking system, I'm very optimistic that finally we will be much better than the state of the art at the moment. And the last contribution would be that we will be designing a full test bed, which will be based on coherent optical communication. And at the same time, we will be integrating technologies like Li-Fi and radio over fiber over the test bed. So we will be touching on a lot of technologies in our test bed. So if you look at the test beds that are available internationally, they either work on multi-core fiber or they are focusing on software-defined networking for optical networks. But our test bed will be having radio over fiber and Li-Fi and FSO and coherent optical communication. So I believe these are all significant contributions which has the potential of taking the research of optical communication in our country forward.
Thank you, Professor Dixit. Now I hand over to Professor Kumar.
So, we've been participating or collaborating with the wireless testbed also at IIT Madras. And I think the purpose that it served was to show that 5G equipment can be built in India. Okay, both core and RAN, which 5 years ago, if you had asked somebody, they would said, why do you think we can build it? It can't be built. It's a big boys game and so on. It may not be the commercial product, but it can serve that to show it can be done. Even if it's entirely done again, it is like doing it the first time is important. Like we launched our first satellite, we did our first nuclear test, or some person climbs Everest first. Then after that, hundreds of people climb it. But doing it first to show that everything is capable, that's important. And I think this test bed, I'm sure, will serve the same purpose for optical component technology. Today, there are no optical components made here. Okay, we sell about $100 million or 800, 900 crores worth of optical equipment every year. And we import pretty much all the active components, all the optical transceiver modules, amplifier modules, and so on. So it's like you make a car here, but every auto part is imported, right? So I think this test bed can serve to show that many of the key modules can be made in India, and you can develop that to system player. And I think it's a good thing if there are other system players who also develop as a consequence of this test bed or otherwise. And we can also go to the global market, like the Indian auto components are being sold in the global market, not just to Indian car companies. I think that's what this will serve. Now, for a small company to develop a module, a transceiver module, and so on, just the infrastructure for testing is a big investment, which is out of their scope, right? They have to raise like 10x just to show that their product works than to even build the product. I think that's what this testbed can do to facilitate the development of primarily the advanced optical component companies. The system companies also come as a result. That's a good thing. And I think that's what I'm looking at. This will be the fillip to develop an optical component industry in India, just like India has a very big auto component industry. So that's what I'm looking for this testbed to achieve. And we'll play our part in evaluating the components that come out of this testbed to see if they can use their own systems, provide feedback on like product management issues, what you need to build, what applications you need to target, or where are you doing well, where you're not doing well. So I'm excited to be part of this journey and work with this testbed.
Thank you. Thank you, Dr. Kumar. As we know, Tejas is already in the forefront of optical technologies. I think wireless, we were not there. We have come now, but optical, thanks to Tejas and other such companies, that our presence is there, but the indigenization part is quite, you import. And now if you start making optical transceivers and QFSFPs, these kind of component, the value addition from the India will go up. And slowly it will help even the component industry. Just to give you a idea, the electronic component which are required in India are close to $70 billion. $70 billion. If you say the production which happens in India and the imported equipment, if I calculate the complete component, it comes to $70 billion. Thank you so much. And I think definitely the learning from each partner, because this is what our experience had been in 4G. We learned from Tejas, Tejas learned from us, we learned from Tata's, coming together, we were solving each other's problem. And individually, I think I always say individually, I was zero, they were zero, others were zero. But together we were very, very significant because we could build on to the complementaries of each other and to become made the system. Now I pass on to Goel Saab.
So first of all, I'm honored to be part of this panel. And as some of you might be knowing that Tata Communications is in the business of B2B, not B2C. And our customers are having very stringent SLAs. They are very demanding, and we always, what we promise, we deliver to our customers. So I think this testbed is definitely in that direction, that since our requirements are very stringent, we should be able to tell what exactly is the demand of the industry. And we will contribute towards giving more platform to the testbed in terms of the actual ground realities. And we can offer some part of our network for, field testing, which actually will help to make the platforms robust and field deployable in the first instance. And Dr. Deepa asked me to be part of this journey, and we will definitely do our best to be contributing in every positive way for this endeavor. And in the journey, I think I will like to learn more how we can contribute even more towards, making this project a success. I think it is a good beginning. It is a big funding to start the component manufacturing now. component testing and possibly manufacturing. Then we have to do modules, and then finally the end product should come so that we can actually make something, made in India and actually use it. So I think Tejas will be a big factor, I would say, that who can tie up these spaces. So we should make this as a good ecosystem, self-governing, and possibly doing something good for the country. Thank you.
Thank you. Thank you, Mr. Goel. I think it is very important to involve the user right from the beginning, because this is our experience. We make a product and give it out, and then the user tell, "Arey, ye to nahi diya, aapne ye specification nahi diya, wo specification nahi diya." So I'm happy that when user is also in this panel, and I am sure that Tata Communication will also will be part of this particular consortium, even though money is not paid, but they will contribute in terms of what we require. So now I hand over the floor to Professor Deepa for her opening remarks, and what she thinks and how things should go, and she will also ask the questions to the panelists related to the test bed and how it can be made best use by the industry. Thank you. Professor Deepa.
Thank you, sir, and thank you for all the comments. Just to give a background, this concept of having all the industry partners right up front came as a direction from Secretary Telecom, Sri Rajaraman. And that was a big challenge for us coming from academic institutes. We are used to writing proposals for our own projects, for our own research projects, for our own papers, and maybe a few patents and so on. So it took almost maybe more than 8 months to conceive this proposal. I have bugged Kumar a lot of times, Badri a lot of times, and IIT Delhi has been with us since the beginning. And we've had multiple brainstorming sessions with whoever industry partners we could. And I first officially thank all the consortium partners to come along with us with this journey. This is going to be an adventure for us. And I really thank all the partners, Himanshu is here, for having faith in something that is very new. And there were certain partners who did not join. We would have wished them to be there for various reasons. Certain partners whom we could not accommodate for various reasons. And I apologize to all of them if there has been somebody missed out. But like what you said, this is only the consortium is not ending here. It is only beginning here. And we really want more and more people to come and join. And we will definitely see how to expand the scope of this consortium. So that's the first remark. And I have talked about this testbed yesterday and morning, yesterday afternoon. So I'll not talk more about what this testbed is doing. But just to summarize the points from each one of you, from Badri, the key takeaway is how do we reduce a cost per kilometer for the multi-core fiber? How do we use the network testbed? How do you use the Li-Fi and FSO testbed? How do we make sure that the key modules can be made and tested? And how the user, special thanks to you, sir, for offering the fiber to our lab so that we can test out in the field. We are also contacting other service providers. This is the first positive response I have got. So we'll hopefully, we have also starting to talk about other projects that can come under the same consortium domain, right? Now, I would, more than talking further, I have certain questions from which is essentially I'm looking for answers genuinely to see how should this testbed operate? So, we are attempting certain products, certain technologically very niche products. We are very ambitious in or aggressive in trying to do that. But there are also certain mundane things we are saying. But are you aware of any other optical testbed in, of course, not in India to my knowledge, but in the world, whose constitution is like this, and also how they have gone ahead, how they have leveraged such a test bed, because I'm aware of certain other test bed we were trying to model it, but most of them were inter-university partnerships for demonstrating. So in your opinion, Badri, you have a lot of, you came from Clarify and so on. I mean, in the US, for instance, are you aware of anything like this that has happened, and what is the learning from that?
I'm actually not aware of something that integrates the passive infrastructure and the new next generation components or systems in this way. There have always been like, there are always test beds to test a cable or a component or something like that. There are labs such as the University of New Hampshire has a facility called interoperability testing. Mostly what they do is GPON testing or Ethernet protocol testing. So it's more like a at the bit level or the protocol. I think this one takes us across multiple, physical layers. And one of the things that we wanted to also sort of make people aware is that the optical communication is actually infrastructure, area. So putting things suspended in the air, buried in the ground, and all of those, interesting things, they run to the most of the cost. By the way, if you don't know about this, in a project cost, anything to do with optical communications, if you have 100 rupees, about 85 to 90 rupees goes in the civil work and the, putting things in the ground. All this, what we are talking about, is only 10% in the end, but it's the high science, the part of it. But that 85 to 90% of the cost actually influences the economics of the 10%, how it behaves and stuff like that. So to the fullest extent, we wanted to try this out, aerial, underground, TEC compliant cabling, TEC compliant, connectivity parts, and test it out under rain, under whatever, rodents, whatever, right? Because this is going to be a new journey for us. So the more the community uses it, more information comes out as to how this test bed will behave in the long run, right? So, yeah.
Deepa, can I make a comment?
Yes.
So there are a lot of international test bed like Orion and Monet and Ophelia and L'Aquila. But all these international test beds are working on few aspects of optical communications. Nothing like us. We have 12 partners, 18 work packages, more than 60 deliverables. I think if half of them can be commercialized, this will be terrific. Terrific for the country. So this is a unique test bed. I have not seen anything like this internationally. I've been in Europe and in USA, but nothing like this. So hats off, means you have pulled up a great.
No, it's not about that. It's about, how to make it more successful, right? So learn from the experience for the others. And thanks to CDOT, who has also been, especially Upadhyaji, who's been giving directions once the test bed was conceived, that this is how we need to go. This is how we need to, in terms of the operational aspects of it, the advice. So I'm looking, so thanks for that piece of information and encouragement that we have. But is there anything that we can learn from the other test beds and try not to make those mistakes?
Because I haven't seen any such a large scale test bed. So it's really hard to comment for me.
So let me ask Kumar this, since everyone seems to say that this is the first one of a kind. What do you think from your experience is the primary challenge we are going to face, and what should we be aware of?
Yeah, I think you have a lot of activities. The primary challenge you will face will be what to choose to sort of further. So let's say you do everything for 6 months, right? I mean, you might have some goals, but only few things will. So you will find that only some things are most useful. Well, you need to focus on them, and you need to identify and maybe focus on them and cut out the other activities. This happens for all companies, right? So you have a lot of ideas, you're bubbling with ideas in the beginning. You can do A to Z, 26 different things, and it's already a long list. But as you progress in 6 months, you will discover that only 2 or 3 or maybe 1 is most useful, right? And also even all the ideas that you started with, as you start working, you will find out that you need to reshape them to be really useful. Some you will have to drop. So I think the biggest challenge will be to be ready to completely revise your proposal. Okay, in terms of what exactly you will do. And this happens to us also. I mean, and that's part of this. And then there is something called a product management function where let's take something we discussed earlier. A semiconductor optical amplifier has probably 10 different users. You can use a modulator, a phase conjugator, as you said, an amplifier. So what is the one that's most useful in terms of 2025, right? Because there are also past users. And there's what will happen in 2025. And that's when you will hit the market. So you have to anticipate what is the most useful thing and then focus on that as the main application for whatever technology module that you are doing and being able to cut out.
Yeah.
So the biggest challenge is to drop things.
Do you have any inputs on that? Okay. Atul, you have any inputs on this question? What is up? You have actually built not to this bigger extent, but test beds of CDOT. So what has been your primary challenge?
So I guess in terms of going forward in actual implementation, there may be delays, unforeseen delays because of supply chain constraints. That is one of the issues that comes to my mind, and probably alternate approaches we need to keep from the very beginning so that we don't run into that. The other thing is that since there are a lot of partners, I think the communication aspect also is very important. I mean, once we move from one phase to another, particularly when the partners are changing. So there the criteria has to be defined very, very clearly so that there is no ambiguity. I mean, it should not be based on any assumption.
Right.
So I think these are the primary challenges. I believe there won't be any, there may not be too much of a challenge in implementation per se, but it's challenges which are not really foreseen in the beginning, and then we discover, and then in retrospect, we think that we could have probably done better.
I know, sir, you are chairing the session, but I would like to get your inputs on this particular aspect. What do you think we should be most careful about?
I think as Atul said, this is our practical experience. When we design something, we say that this will happen in 3 months, this will happen in 6 months, these go haywire. So how to control it? And secondly, as I was discussing in the morning, everything should be online on a dashboard. I must know what he's doing. I must know he's doing. What are the dependencies? Who is failing? Who is aggressing? I mean, many times delays happen because of the information gap. So information should be current. There should be a source of single truth. That is the dashboard. Dashboard right from funding, meeting schedules, outcomes, dependencies, what needs to be taken up. This has to go up. So primarily because your this particular consortium is 10 members are there, and few members more have joined, like Tejas and Tata Communication. So the coordination work, I think, but we are in the able hands of Dr. Deepa, who is the project leader, and I think our experience with her has been excellent, and I'm very sure that this will go through very, very well. As regards CDOT as an implementing agency, our job is only as a facilitator. But one thing I must tell, when we develop a product, from our side, it becomes 100%. But when we goes to field, to the operator network, it comes down. The 100 to it drops down to 80, 75. And there is some challenge. And I think as CDOT, we will also help because working with the operators like BSNL and now the private operators also. So I don't see any challenge because all the companies which are associated are all masters in their field. But when we do co-optation, cooperate and compete, because finally all the private, especially the private entrepreneurs who are there in this, they have business in mind. Business also has to be in mind. Otherwise, why all these organizations are there? So while we compete, we should also collaborate. And I think this co-optation among the partners will bring the systems very, very up. Now, since we have flights, and we have just 20 more minutes to go. I think I'll open up the floor to the wisdom of our audience here, our participant here. I know a lot of experts are there here, and I must thank, I was thinking that after tea, nobody will be there. I must thank the kind of interest, this community has. Hats off to all of you. You are all staying back. Really, it's really great because on Sunday, after tea, a lot. So thank you so much. So we open up the floor for the questions. So questions, you can say your questions to the whole panel, or you can, particularly pick up the panelist whom you want to address your question. Thank you.
Going to be our main coverage is getting a 30. I think we are talking about an ecosystem. We should also talk about active ones, meta ones at the same time, because what we need to enhance the coverage.
So you're talking about intelligent reflector service. I think, see, this is this project is for AOC. We have terahertz 6G project separately, and many more are coming. As our honorable minister was saying in the morning, we have budget of 500 crore from the TTDF. We have 100 crore DCIS, 100 crore CCRP. So money will not be a problem. And many of these projects, because we also took up this TTDF only last year. So it is work in progress, and we have close to 400 proposals. In fact, we have been able to process only handful of proposals till now. So, but we have learned quite a bit in this duration, and I'm sure going forward, I think our next proposal, I would also like to use this opportunity to tell the our respected participants that we have put in our TTDF website to know the proposals where you would like to work and TTDF would like to fund. So we are inviting proposals that what is the problem statement? What is that our country should do? What research? Because sitting in Delhi, we may not be aware what is happening. But if we take the collective wisdom, we'll be able to know that. Therefore, there we have opened up in the TTDF website. You give your problem statement. We'll compile all the problem statement, and this time we might come up some open proposals, like whatever you want to present, and some problem statements rather than totally opening it up. So problem statement like generation of, develop this particular product for us, develop this product. So this is how the proposals will come. So definitely different. Ma'am, you want to say something?
Yeah, just to address Ashok Kumarji's question, in the 6G consortium, there is a work element that IIT Madras is doing on developing intelligent reflecting surfaces. So that's a different consortium. Yeah, thanks.
Yeah, this is Anand. Yeah, I hope you both are much more experienced than me, but I would like to add a little comments about sharing my experience over 3 years on international academic testbeds, even though it's QKD, but here is AOC testbed. It's something similar. The objective of the testbed at the end is that, as rightly said, end user. If at the end of the testbed, if end user is not satisfied with that component that is indigenous, then that doesn't give success to the testbed. So right from the beginning, the engagement of the end user is very important, so that the component, indigenous component you develop fits their requirement. Then that component will be useful. So that's, I'm reiterating that end user validation is very important. And second, even though you may have several components and you want to build the solution, there may be some components which we have to evaluate whether we need to develop in-house, whether we have capabilities or not. Even if we develop, whether we can catch up with other developments over international markets, whether it's really going to give us an edge over international market, or it helps us to reach the market. If that development is not going to give us an edge, for India, then you can drop that. You can, of course, get that components or the element from outsourced from other countries, or you can use the existing products. So yeah, international collaboration is key, and we have to prioritize which will give the edge from a cost, from a development point of view, or from export point of view. That's two comments I would like to add for you. Thank you.
Yeah, you are absolutely right. User has to be consulted, and that is why we have Tata Communication here. And we encourage other industry partners also to join us and to tell us that what should be done and how it should be done. As far as the point you made using the internal components. So this has been the model of indigenization. First, build the system, then look at what can be replaced. So we start with maybe 60-40, then come to 50-50, and end of the day, you should be 0-100. And that's what our aim. And I'm sure this particular consortium will give us, will make us to reach close to 100% indigenization. Any more questions? Sir, जरा जोर से बोलिए.
Yeah, if I understand your question correctly, you're talking whether the startups will have access to the test bed that we are developing. Definitely, yes. So that's one purpose. So if any startup is interested in what we are doing, we welcome you. We welcome your inputs also. And I encourage you for the collaboration. So if you just write me an email, I will get back to you. Any more questions?
Sir, I'm Parmeswar here from United Telecoms Limited. With respect to test bed, so you have mentioned like there will be a number of discrete components will be there, like in the EDFA design, let us say. So this test bed will comply for all the even discrete components or the module level test compliances, or who will be the issuing the test certificate again once it is passing everything? The agency of that test certification and all required once it is passing everything. Who will issue the certificate?
So as we explained earlier, currently the work packages tell what is to be developed. And indigenization is an ongoing process. It will, as I said, it may be, we may start from like we import. So it is 0-100, then 10-90. This is an ongoing process. As far as the certification is concerned, we have TC, for example, which prepares GR. And if any international certification is required, that also will be taken wherever it is required, like CCRA or all those kind of things. So certification will be part of this definitely, because with certification, the credibility increases. So certification will definitely be part of this consortium. Sir.
Yes, sir. So thanks, Upadhyaya sir, for nicely summing up in the beginning that we have to reduce the dependence from imports. So Mr. Atul mentioned about EDFAs and WSS being manufactured. So what is the plan to actually integrate them into modules so that they can be deployed into systems and integrating with NMS, EMS? So basically my question is, while we develop discrete components, so what would be the plan to integrate into actual usable systems for commercial deployments?
So basically, what I understand is that in the current scenario, whenever we develop any indigenous solution, let's say DWDM equipment, most of the critical building blocks, they are all imported. So they simply come as a module which we use, make use of it in the system, and then we go forward. Now, the alternate approach that is being taken is that some of such modules are getting developed as part of this test bed. So the intent is that once these modules are there, then they will, instead of the imported modules, will simply add no value in terms of any attempt to indigenize them. These modules will be integrated into the solution, whether it is a DWDM equipment and an optical cross connect. So it's not going to happen straight away. So first the module has to be developed. It has to be thoroughly tested for its functionality, whether it is affecting the other channels which are flowing into the network, for example. Right. So EDFA, even if it is developed, unless it is thoroughly tested, it cannot be deployed straight away in a network because a lot of traffic is at stake. Right. So the subcomponents which are getting developed as part of this test bed, and certain more components which will probably get developed as we go forward through new proposals which are submitted to TTDF, they will all be integrated to form a solution which can go to the field. And for testing that, we are setting up an infrastructure at CDOT.
So last question of the day. So I think the last, anyway, keeping in time in mind, I think people have reserved their questions. Fine. So to sum up, it's a great opportunity for India that we are coming up with such a test bed. It will open up the facility for startups. It will open up the whole ecosystem. It will accelerate. So with these words, I hand over the mic to Professor Deepa, because she has been running this conference for last 2 days to sum up about the whole conference. Ma'am.
Yeah. Thank you, sir. But before, okay, we can do it after. So this 5 minutes I'll take to carry out this pleasant job of doing a vote of thanks for the entire conference or entire workshop. This workshop, as you know, is under the aegis of Department of Telecom, and we had very wonderful directions that we got, advice and directions that we got on what should be the goal of this workshop. It is not to bring in few PhD scholars and academicians like how we usually do. It is to bring the industry. It is to bring this people who may be interested in using this ecosystem. So I first thank Secretary Rajaraman sir for this direction. I thank the Honorable Minister of State for Communication who specifically came only for this workshop and spent a day with us and trying to understand everything that was going on. I must thank Toshniwalji, who has been silently supporting from the beginning with multiple WhatsApp messages and multiple meetings as well, and being here all through to make sure that everything is going. Along with that, I must thank Tushar, who is sitting there silently, who has been at the back, handling all registrations. I must thank Deepika madam, who is sitting there, who did all the website work, registration work, and must thank the CDOT DOT Chennai team, who has done multiple visits here to make sure that everything is fine even before the workshop. All the distinguished guests from CDOT and DOT to make us confident about what we are going to do. And locally, I would thank Vinod and Hatim, who are our conference event managers. Vinod, if you are there. Paramani Guest House and Bose Einstein Guest House, who have hosted a lot of our guests. Team from the audio video system here. And from my own team, Malati project, she has been contacting all of you. And I do not know what I would have done with the names that I'm reading now. They have done the whole show. I have not done anything here. For the small organizations to, minute to minute planning, I have not given any directions. It is their planning. It is Akhil, Anagha, Ashutosh, Geeta Krishnan, Jaideep, Madan, Mridula, Nilesh, Pavitra, Rana, Samir, Shiva, Sriraj, Vilashni, Vishwa, and Arjun. Most of them are my own students. Thank you. They got into the job from last Tuesday. Before that, I have not disturbed them at all. From Tuesday to now, they have been managing the show. If I have missed anyone, I'm sorry. I thank, I will remember and I'll send an email if I have missed someone. And okay, I cannot miss this audience who has been here until Saturday evening, almost 6 o'clock. Thank you once again. I will request Padyaji to felicitate our panel members. Who's this? This is Mandeep. As they come, I'll introduce. People leaf. Right, people leaf, gold plated. Oh, please. It's a typical IIT Madras. If the audience is wondering what is this that is being given, it is a dried people leaf, banyan trees leaf, which is gold plated. And this is a characteristic of IIT Madras. And there is some small description of what it is behind. So, this is first. Box is in there. Box is in it. Box is in it.